Hi everyone, welcome to Deep Learning tutorial series. As part of this presentation, we are going to take a look at Keras image processing tools. This is a pretty interesting thing when it comes to doing computer vision oblique image processing activity, because there is a inherent support or there is a good support in Keras. So as part of this presentation, we'll basically try to see Keras image processing tools and then how does it go with CNN. That means how can I use these image processing tools along with the CNN, convolutional neural network. So when we are trying to make use of this Keras image processing tool, basically we need to take care of the data pre-processing. So what does it mean? Like, why do you require such a Keras image processing tool? So essentially we are now trying to target something called as data pre-processing. So when you typically have say color images, then what you do is like you basically read the picture files, then you decode the JPEG content. So suppose if the files are JPEG files, then you basically decode the JPEG files and then you basically convert it to RGB grids of pixels. So that means you are actually converting from JPEG image to RGB, and essentially it's a decoding process. So obviously we don't have to go into the detail because that support is already there. Then you are going to convert this RGB grids of pixel to the floating point tensor. Why? Because the reason is we are going to work on, that means when we use the Keras, essentially it works on the tensors. So that all those details are already covered in our previous various videos. So you basically converted it to the tensors and then you need to rescale it so that you have values of pixel values between 0 to 255, and this is what we have done as part of understanding the convolutional neural network video. So what you do, you rescale the pixel values so that whatever the values are there from 0 to 255, they will basically fall in the 0 to 1 interval. Now typically you require this because when you work with neural networks, you prefer to deal with the small input values. So because normally the pixel values are between 0 to 255, so essentially you divide it by 255 so that you get a value between 0 and 1. So this is what in general the data pre-processing is supposed to be is supposed to be done, and now that is where this Keras image processing tools comes into picture. And when do I use this Keras image processing tool? So the activity where you have to do this JPEG to RGB conversion, or say the rescaling and stuff like that. So all those things I can make use of the data pre-processing, and which is part of Keras image processing tools. So how do I do that? So basically there is something called as Keras module with image processing tool, and it is called as image data generator. So it is going to make use of a Python generator. Now I have a video which is part of the Python tutorial series or Python bootcamp, where the concepts of generators are explained in detail. So here when it comes to when it comes to this Python generator, so this generator will be used for converting image files to pre-processed tensor. So that is the role of this generator module. So where is it available? So basically you can use this from keras.preprocessing.image.image. So essentially keras.preprocessing.image, and then you import image data generator class. So that is what you basically are going to make use of this existing module which is part of the Keras. So let's quickly understand Python generator. As I have told you, I have a complete Python tutorial series. It's available on Udemy, and it's essentially it's a boot camp. Like it's from the very basics to advanced, and it also has a bonus of NumPy. So in that this tutorial series, the generators are explained in detail. However, I will just try to summarize it here. So what is a Python generator? So essentially it's an object that acts as an iterator. So it's an object that can be used with the for in approach. That means you have a for loop, so you try to write a for and then you say for x in something. So that is what, so it's an object that can be used with the for in operator, then it is built. When you write a Python generator, you need to make use of something called as yield statement, or it is also called as yield operator. Then you can get these details in the Python bootcamp tutorial series, which is part of Udemy. So let's now focus on image data generator. So image data generator is basically going to take the input images, whatever the input images you give. So they are basically, it's a quite a significant database, or a large number of images are there. So those things you basically are going to give it to image data generator, and as the name suggests, is going to generate some data, and the data is basically image. So it's going to generate image data. So what is it going to do? So it's going to yield batches of 150 by 150 RGB images, because I told you whatever the JPEG image you have, you need to basically convert it to RGB, and then from there you can convert it to the tensor. So this data generator is going to yield batches of 150 by 150 RGB images, and it's going, because since it's a batch, so essentially it's a 20 sample per batch. That is what we are going to use that, and as we proceed, this point will become clear. Then the generator yields the batches indefinitely. That is the beauty. The generator is like, it continuously keeps on giving the different batches. So essentially what it is doing, it loops continuously over the images in the target folder. So because it's now a continuous loop, so essentially it's like a endless loop or a while one loop type of approach. So when you are write a program, you need to write a break. That means you need to break the operation of iteration of the loop. So that means you need to have a break of iteration of the loop is required. So that is what in general about the image data generator. So just to summarize, image data generator is going to yield batches of RGB images, where 20 samples per batch is going to be there, and the size of each image is basically 150 by 150 RGB image. So let's proceed forward. So now comes the fitting the model. Now because we have done this fitting the model concept in our all videos, various videos, including the CNN video as part of this tutorial series. So now how is it little different, or how it is different from the one that we have already done? So fitting the model to the data, that means you need to fit the model to the data using the generator. Why? Because now we are going to rely on Keras generator or image data generator. So for that, we are going to make use of a functionality or a function which is called as fit underscore generator method, which is similar to, or which is equivalent of fit, because up to now we were using fit. So here we are not going to use fit. Why? The reason is because now the data that you are going to have is basically, you need to fit the model to the data using generator, and you are going to make use of generator. That's why there is another method which is called as fit underscore generator. So how do I basically use this fit underscore generator method? So let's see the details. So it's going to generate a history, sort of like whatever you are processing is going to generate, and then basically in this usage of fit generator, so essentially you have a model object, and then on the model object you have this fit generator function, and now this fit generator method or function is going to take various parameters. So let's see this. So the first parameter is a generator. The second one is a, so this the second one is a steps per epoch, which is 100. So let's now try to understand these two parameters. So this generator, or which is also called, or which we typically use it as for training, so it is given as train generator. So it's a Python generator, which I have told you some time back. So Python generator that is going to yield batches of inputs and targets and targets indefinitely. That means that's what I told you, it's like a endless loop or a while one loop. So this is that generator which is the input to this function fit generator. Then steps per epoch, so that means how many samples to draw from the generator, because generator is going to produce you continuously, it is producing the images. So it's like water is coming from the tap, and now you decide how much flow you require, so you adjust the tap accordingly. Like some people may want it water to rush through very fast, so you open the tap completely, or you basically open it little, so so that you want it the pressure or the flow of the water to be little less, so you don't open the tap completely. So the same concept here. So how many samples to draw from the generator? So here we are going to draw batches or 20 samples. We are going to draw that. So 100 batches for, say suppose if I have 2000 samples, then typically in each batch you have 20. So 100 batches will be there. Then comes the epochs. So basically how many times, like that concept of epoch which was basically explained to you, so the same concept is here. Then comes the important thing like validation data, because you need to validate it against some data. So it is again validation data is similar to it. However, because now we are using generator, so we are going to provide a data generator. So that is basically, so generator is expected to yield batches of validation data. In the previous one it was a training data, so here it was a train data. This is what train generator. And now this, because now you are going to test it or you are going to validate the behavior, the performance or the way in which how this model has is behaving. So you need to do that evaluation. So we have seen this in fit earlier. So same concept, however now again here it is a generator. So generator is expected to yield batches of validation data continuously. Then the steps, so again same concept. So how many, that means batches to draw from the validation generator for evaluation. So the same thing, it is similar the way in which we were doing steps for epoch. So how many samples to draw, the same thing here. So it is a validation step. So this is the last parameter. So here we are going to make use of, one will be the train generator, then the second one will be the steps per epoch, which will be 100. Then epochs will be 30. You can make it, obviously we even to run 2-3 epochs itself, it takes a good amount of time on a say i3 or a i5 processor. So it's a considerably loaded activity. Then validation data, I have told you it's a validation data that is again generated from a generator, and then the steps. So all these things, because now it is little difficult to understand or go through it completely, we will anyway take a look at demo also. So as part of this demo, we are going to first understand image data generator, and then how do I use the fitting of the model. So let's try to see this in the demo. So I will now go to the code, because I am running this just now I completed it. So I will just basically try to walk through this code so that it's clear what we are doing. So we are going to make use of pet images. So again, so these pet images are like cats and dog, which we have used earlier as part of our convolutional neural network video. So what we are going to do is we are going to, these pet images there are 25,000 in number. So we are not going to make use of everything. We are going to form a small subset of this. So that's why we have created, or we are going to create another folder which is called as cats underscore dogs underscore small. That means we are going to take only few samples from that. So we are going to import operating system as well as the shell utility because we need to copy some images from the original data set to the location which is cats dogs underscore small. So for that you need to create a directory. So this is the directory for the cats, dogs and small. So again this is written in Python here, or here itself we are using the OS support. Then we are going to create train directory. So train directory will have a folder called as train. Then you will have validation directory which will be called as validation, and then you can also create a test directory which can be called as a test. So essentially we have two things, one will be train and another can be the validation or test, depending on which one you currently want to use. So ideally there are three. Then we are going to create a directory for train like for training images or train data. Similarly we will have validation directory and test directory. So let me just quickly show you this once we complete this job. Then you are going to have the folder for cats directory. Similarly you are going to have folder for dogs directory, then validation cats directory, validation dogs directory, test cats directory and test dogs directory. So let me just show you this so that this concept is clear. So you have this original data which is a pet images. So it's a huge data. So from this there are two folders, cat and dog, and in cat there are so many images are there. Similarly you have in the dog you have so many images. So we are going to basically from this pet images we are going to create a cats underscore dogs underscore small. So here you can see there are three folders are created. One is the train data which is important, and another is for validation and another is for testing. So these are the two. So let's go to the train. So again in train you have cats and dogs. So these are some small number of images. Similarly, you will have dogs. You will have this, some images are there in dogs. So that's the way this is there. So let's go to our code. So these are all the train cats directory, then train dogs directory, like that. Then I told you we have to create this directory which I just showed you. So this we need to run it only once. We can't keep on creating directory again and again. So that is what. So test, train, and validation. So this directory I have created. So train cats underscore dir. So this is what you basically I was showing you. So this is what cats, and then you have all these cats images. So here we can see it here. So these are all the data. So train, you can go to train, and then these are the train images. So these are all the things. So train cats, train underscore cats underscore dir. So all those things will be basically part of the. So here we are going to make use of original data set. From the original data set, we basically are. So these are the places where we have the original cat images. Then what do? You only run it once and you create a small folder. So I told you we are going to take 1000 images and then the whatever. So like that we are going to see that. Similarly, we are going to take dog images. So then you copy the dog images like that, and then you basically print. So let me just run it. So you can see we have taken training cat images 1000, then training dog images 1000, and validation 500, and testing 500. So that's why we have totally taken 2000 images like this. So now we need to prepare the data. So that is where now our current focus is there, because all the previous things are very simple. They are just done to ensure that we basically just copy the folder and when you copy the folder you take only a small subset. So you can see here we have taken only for I in range 1000. So you just take only 1000 images, then from that means 0 to 999, then 1000 to 1499 is for the basically validation, and then similarly that means 1500 to 2000 that means 1999 you are going to take it for the this one testing. So that's the way you take. So that means train data, validation data, and test data. So this is a no-brainer. There is nothing great that we are doing. We are simply copying the few images from the 25,000 images. So because we don't want to do that. Then we will just same thing for dog. So same code is there, only directory is changed. So one was for cat, previous one was for cat. You can see here this is cat and this is now dog. Okay, so that means we have now this 1000, 1000, 1000. Now we need to do the pre-processing, which I have explained to you. So for that we have imported Keras, and from Keras we are going to take image data generator. Then we are going to do the rescaling. So here we are going to do only rescaling, and we are dividing each this one by 255. So when you do the rescaling, so you are going to get a value which will be between 0 to 1. Then you basically have this train data generator. So you can see here it's an object which is of the type image data generator. So you can see it is clearly telling. So this is the train generator. Now what do? You basically take the data and this is the generator. So here we have just only done the rescaling. Now we are actually creating the train generator object which we are going to use. So here you can see I am using the function train underscore that means I am acting on this. So train underscore data gen dot flow from directory. That means you take the images which are of the size 150 by 150, then batch size 20, and then the classification mode is like binary because we have only two, that is cats and dogs. So if I just run this line, you are going to say that it has 2000 images belonging to the two classes. So now we are basically going to take the shape. So here you can see the shape is 150, 150 and 3. Why 3? Because it's a RGB. That's why here the color format is RGB. Now we are going to create a validation generator. Same concept here we are going to take, and now we are going to basically have the validation generator. So we are taking it from the test. That means we have two things. So one is train data. So this is the train data. So there are basically 2000 images of train data, and similarly we are going to take 1000 images for the belonging to the two classes. So here I told you like 1000 per, that means 1000 per class, that means 1000 per that means 1000 for cat, 1000 for dog. That's why you got it here 2000. Similarly here you have 500, 500, so that's why you see 1000. So validation data, that means the data that you are going to use for doing the validation. So then we are going to create a, so here we are going to create a model. So model, we are going to import layer. So this is all previously we have done. There is nothing different that we are doing here. So here you can see layer 1 is a convolutional convenant. Essentially we are taking it 3 by 3 input. So why this? Because 150 by 150 and then the RGB. Then we are using the max pooling layer. So I explained you pooling and all that on 2 by 2 size. So all those things are explained. Then layer 2 is a 64, then 3 by 3 ReLU here using again ReLU, here 128. You know the reason why I told you all these things earlier. Then layer 4, then finally you flatten. Then final layer is a dense layer. So in the dense layer finally is the you are active sigmoid. Why? Because you want to take a decision whether it is a dog or a cat. So the summary, you can see the summary. So all these things are, again, this is the same thing that we have seen in the convolutional neural network. Only thing we have, probably we might have changed this number where when we are handling the data here. That's all. Rest is the same, concept is the same. So you have the different layers. That means CNN layers, plus you have the flattening layer or flattened layer, and then the final, the dense layer, fully connected basically layer. So summary, you can see the summary. Then you compile. So we are going to compile again binary cross entropy and all that. So all those things we are going to measure accuracy. So this was again told. Now here there is a trick that we need to handle, because we are handling images which are which we are taking it from some data which is like cats and dog images. So same data, and now there is a chance that some of the images are empty. Now I have found this image was empty. So otherwise this Keras may not handle it properly. So that's why you require another library to handle such situations, because if there is a empty image, then this fit generator method, because now we are going to rely on fit generator. So fit generator method is going to basically gives error. It fails loading. So that's why you require a support, and that support is called as Pillow library. Or so you need to install Pillow. So it is called as Python imaging library. So it is abbreviated as Pillow. So you need to import. That means you need to have a Pillow installed. So you install it pip3 install Pillow, and then you import image from PIL. So this is called as PIL, Pillow, Python imaging library. Then comes the model dot fit generator, which I just explained you. So this is that model dot fit generator. Now this is very important. So here we are now going to give the train generator which we have created earlier. Then steps per epoch is 100, and then epoch. So here I have told you steps per epoch 100. Epoch 30 takes a hell lot of time. So we are just saying for the time being 3. So this itself took good amount of time for me. Okay, so this is a it takes considerable time even on a first laptop. So we have this train generator which was generated earlier, which I told you, explained you here earlier. So this is that train generator. So this was that flow from directory has actually created 150 by 150, and that is where this function comes very handy, which is going to do the job for you. Batch size 20, then target size 150 by 150, like that. Similarly, we have the validation generator. So same thing. Only thing, there is a difference here. There are 1000 images. Here you have 2000 images for training. So you pass all this data to the fit model.fit generator. So train generator, then steps for 100. You need to have obviously 30. Here I just have done sample for the time being. Then validation data again, and then validation steps 50. So all those things basically I just explained you here. So you now generate a history. Once you run, you basically get a history. Then if you want, you can save the model. Then you can plot the basically the you can save this model if you want. So you can save this under some name. Then you can reload it, because you can't keep on creating model again and again. So if you want, you can reload it and run it. Okay. Then you are creating the plot the loss and accuracy during the training. So we are importing matplotlib. Then we basically are going to have this accuracy created. So we have just because when I was explaining to you, I was parallelly running this, executing this for 3 epochs. Otherwise, it takes good amount of time. So now you got this. So you got this. So let's plot the epochs also. So we'll plot this. So you can see this. I have got the output. So here we have plot. So what we did, we basically have plot the training accuracy, So we are basically plotting training and validation accuracy, and we are also plotting training and validation loss. And here we are also basically explaining this or showing this both these things clearly. So in this training and validation accuracy, we have training accuracy and validation accuracy. Now I told you validation data is provided here. So this is what the validation data. That's why we use validation generator. And here we have used the training generator. So I'm just repeating again. So now you got this data. So you plotted both. So that's why you have this plot dot legend, then plot dot legend, and finally you plot the figure and show it. So you can see this. So there are two figures. One is training and validation accuracy. So you can see this training and validation accuracy is basically improving, and then training and validation loss. So loss is little decreasing. Obviously it's for 3 epochs, so you can't really say with so much of say confidence that right now, because unless I make it here 15 or 20 or 30, because number of epochs I have run only 3. So you can see here the accuracy loss was initially 0.68, then it reduced to 0.65, then it became 0.60. So you can see the loss is decreasing. So as we run more epochs, you can see loss decreasing, then accuracy is increasing. You can see here initially it was 54%, so now it improved. Second epoch it became 60, then it became 66. So if you have more epochs, you are going to have accuracy improving, and that is the same thing. So validation accuracy is also, you can see it is 0.59 and finally 0.63 in the 3 epochs. So like that you can see the improvement is happening. So validation loss is basically there is a validation loss which basically decreasing. You can see here it has started decreasing. In between it increase and then decrease. So like that, if you run for more epochs, say 30 or 50 like that, then we can see a better graph. So that is what basically we have seen as part of this video or as this presentation. So essentially we have seen how do I make use of image data generator. So in that there are two things. So as I explained in the program, there are two things. One is a model.fit generator, that is a very important thing, and another is which is actually helping you to do the job is actually the functionality which we have used here, which is actually the flow from directory. So what you do, you take this flow from directory, the support as part of the Keras. Again, this is, you can see this is I am using image data generator, so I am directly using it on train data dot flow from directory. So this is a help. If I do here help shift tab, then you can get all the details. It's going to take RGB and all that, you can see that. So this is a very important thing. So there are two functions. One is flow from directory, which is going to create a target size of 150 by 150, batch size 20, and then class mode binary. And this is like a generator. So you are creating a generator for training, and similarly you have validation generator. So this is the first thing which is important function, like flow from directory. And then comes the important learning from this tutorial or this video is basically about the pillow. Obviously pillow is there, but ensuring that you have a fit using you use the model.fit generator, because it's going to take generator as the input. And what is Python generator, I have explained you in summary in this video. So I hope you like this video, and thank you. Hi friends, welcome to deep learning tutorial. As part of this video, we are going to concentrate on image processing tool which are available as part of Keras. Now in the previous video we have already looked at few important things. So now we are going to take it forward, and let's try to get into this video now. So as part of this video we are going to concentrate on data augmentation with Keras. So we'll try to understand, because now our data is now an image. So we have basically set of images, so we are going to use that as a data, because we are concentrating on the computer vision oblique image processing. So here the data is basically the images. So we are going to work on data augmentation with Keras, and once we do that, then we'll try to see how can we use CNN along with this data augmentation. So let's get going. So as part of this computer vision, as I was mentioning to you, data augmentation, basically what we are doing, or rather what we have done as part of our previous video, is basically we have used few samples to carry out the training. So for example, we may use say sample size of say 1000 or 2000 like that. So for example, in our last video we have used 2000 samples. And when we are using a few training samples, so overfitting is a concern, and we already have a separate video about this overfitting concept. So overfitting basically is an issue when we have limited set of samples as part of the training. So what do they do as part of this computer vision? They basically carry out a sort of data augmentation to handle or to overcome this issue of overfitting. So now why this overfitting is happening, as I was mentioning, essentially it happens because you have too few samples which is used for learning. So because of this you are unable to train a model that can generalize to new data. That means since you are training it with say limited number of samples, so if say a sample that you are using for testing it, or say otherwise also if you want to use it for later purposes, and if that sample is not trained or such similar sample is not, the model is not trained for to handle such sample, then obviously your output is not going to be the way in which you are expecting it. That means what is happening is generalization is not going to work properly. So unable to train a model that can generalize to new data. So it's like in as a part of study, you basically let's say have only concentrated in mathematics, you are concentrated on say some portion of algebra, where in your actual exam you got a topic which you never studied or which you never bothered to basically dwell into. So because of that now obviously you are going to find it difficult, or probably you can't even solve that problem that is going to come in your exam. So same concept, you are basically overfitting is going to cause by having too few samples to learn from. So unable to train a model that can generalize to new data. So what do they do? Typically data augmentation will be tried, or it is a technique. So this data augmentation is a technique, or it's an approach of generating more training data from the existing training sample. So what would they do basically? So you are going to do augmenting the samples via a number of random transformations that yield believable looking images. Now this is very interesting concept. Like suppose if you have your own photo and now you are trying to augment your photo, so probably you will try to rotate it, or you will try to look at it. Okay, in this, suppose if I now flip the image, then how do I look in my in the as a mirror image, or suppose if I turn it say 30-degree, then how do I look like that? So typically this concept is called as data augmentation or an augmentation. You are trying to augment it. So you are augmenting the samples via a number of random transformations that yield believable looking images. That means your own image you are trying to do some transformation, but you still feel it is closer to what you yourself are looking, or your photo is. So the goal is that at training time model will never see the exact same picture twice. Otherwise what will happen? If you have limited set of data you are trying to train, then probably the same picture will come again and again, so or twice or something like that. So because of this approach, since you are transforming it, the model will never see the exact same picture twice. So what is going to happen? So this is going to help expose the model to more aspects of the data or the image and generalize it better. So this is basically a technique or an approach typically for generating the more training data. So because of this now you are trying to ensure your model can generalize, or it can handle some other data which is say testing data, or some other data which you probably want to use for evaluating. So how do they do? So basically there is a method which is called as image data generator, and in this image data generator, as the name probably is basically specifying. So what do you do? So you are going to now do the data augmentation via image data generator. So that is what you are going to do. And now the parameters that you are basically trying to pass are now going to be are such parameters which are going to play that role where augmentation is now going to happen. So let's see those parameters. So as seen in this slide, you can see that there is something as a rotation range. So what you are trying to do, it's basically a range within which you are trying to randomly rotate picture. So typically you are trying to rotate your picture say from 0 to 180 degree. Then another thing is like you are trying to do a shifting. So you either you do or you basically do width shift or say height shift. So these are typically the ranges, that is as a fraction of total width or height. So within which to randomly translate pictures vertically or horizontally. So if you do it height wise or width wise, then you are actually trying to tackle vertically or horizontally. Then there is another thing called as shear transformation. So it is typically specified as shear range. So it is like randomly applying shear transformation. So basically you are trying to, so it's like a transformation that slants the shape of an object. So typically there are two things like two shear transformations. So one will be like X shear and another is a Y shear. So it is like shifting the X coordinate values, and the another is Y shear is a shifting the Y coordinate value. That means you are actually trying to shift sort of like it's like a transformation that slants the shape of an image. So probably if it is a rectangle, then probably you will try to make it a rhombus, something like that, or a parallelogram. So again that is like a shearing transformation. Then comes the zoom range. So obviously we all use mobile phones and all that. So probably I don't think there is anything great to explain. So you are trying to randomly zoom the inside picture. That means whatever the content or the picture that you are trying to zoom. Then there is something called as horizontal flip. So randomly flipping the images horizontally. So this will be relevant when there are no assumptions of horizontal asymmetry. Like now this is little interesting to understand. So you typically will use this because when you have a real world pictures like probably some scenery and all that. So you don't have assumption of horizontal asymmetry. Then comes the fill mode. So there are some few fill modes are there like constant and nearest and all that. So it's like when you do the rotation or when you try to change the shape, then typically what will happen, you need to tackle the newly created pixels because now the shape is getting changed. So suppose if it was a rectangle, probably it become parallelogram, and obviously your boundaries are going to affect. So that way there are some concepts. So nearest is one of, because it uses the nearest pixels which are available for the handling the boundary pixels. So that is called as fill mode, or rather that is a fill mode. So normally nearest is one of the commonly used approach. So now what we will do is we'll try to see how augmentation is done. So we'll try to see some sample images as part of the displaying augmented image. So let's try to go to our Jupyter code, and we are going to continue where we stopped last time. So we are going to use the same stuff. So now I am going to concentrate only on, because we have seen this code where we basically have plotted this uh, like matplotlib. Basically we have done training and validation accuracy as well as training and validation loss. So this was the place where we stopped in our last video as part of the demonstration. So now we will try to see the augmentation. How are we going to do? So these are the some of the things like rotation range, as I explained to you in the slide. So like we are going to play with this width shift, height shift, like that. So zoom range, then fill mode is nearest, which I just told you, horizontal flip and all that. So we will just execute this now. So here now you got the data, and which is basically, so this is the data gen is actually having all these basically the configurations. So now you want to display the data using this configuration. So we will import image from the Keras pre-processing. Again this is part of pre-processing. Then we are going to take the images of cats and dog. So we'll first take cat, and then we'll just, for the time being we are going to take cat, and we'll just see how what exactly we mean by augmentation. So it's like we are trying to play with that image. So we'll just take those images. So they are basically, I have explained to you in the last video where we have this train cats directory, and I have shown you that. So from that we are going to basically join them basically. So os.path join and train cats directory, and then the name of the file. So we are actually iterating here. So for fname in os.list directory, that means whatever is available in this directory we are taking, and we are just joining the name of the file in that. So you get the actual name of the image. So let's try to see the length. So there are 1000 images, as we know last time I explained to you in the video. We have 1000 cat images and 1000 dog images. So we'll just try to take some random name of the random image. So say 100th image. So you can see it is some 189. So we have taken some 1000 images. It's not in sequence, so that's why you see some image has come. Suppose if I try to take say here 102. then you probably will get 190. So like that you are going to get. So let's, for the time being, let's use this 100 image. Now we are going to choose one image to augment. So like we know this is the path. So I have explained to you earlier what was the image path and all that. So all those was explained to you, or which was part of our previous video. So instead of now spending time on that, so we are just going to take some random image. So let's, of all these images, because there are 1000 images, we know that. So we just try to take a basically the third images. So third image. So we can probably say 3. Here I would have said 3, then probably we'll get from 100.jpg. So like that. So let's try to. So we will now take third image. So we now got the path. Now we will load this image. So we are going to make use of this image facility that is part of the Keras pre-processing. We are using image.load image. That means it's going to load the image from this particular. This is the name of the file, and it is going to do the scaling for you, which will be of the size 150 by 150. So we load that image. We loaded this image into img variable, and now we will just say plt.im show image. So we will plot that image. So now you see this is that particular image of a cat. This is that third image. If I take say fourth image, and if I just say load image, then once again I try to plot, and probably it's some different image. So as we can see now, these are the different. So let's try to take this image, third image. So we got this image. Now we are going to convert it into the NumPy array. So basically we have a basically a 3-dimensional array, that means RGB. So 150 by 150 and then RGB. So we basically are going to convert with the shape. So we are going to use NumPy facility where we are going to convert this image img here, because we have done loading. So we are going to convert it into the NumPy array using the facility img.array. So let's do that. So again, this is img.toArray is part of Keras pre-processing image. Okay, so that is very important. You need to understand, because this is img I am doing img dot image dot. So it's an image. This is what I have used, image here. Okay, so image dot, it's a functionality of image. Okay, and where I am passing img. So now we will convert it into the NumPy array. Now we will reshape it. So we want it basically for all, that means from 1 till the shape. So we will just do the reshaping. So now you got it reshaping, and now so what is going to happen now? Number of images to be yielded from the generator per batch. So we have written our own program here. So we are going to say datagen.flow. So we are going to just make use of this flow functionality, where we have this data in the NumPy format, and the batch size here is 1. That means we are taking one image by one image, and then we are trying to plot the basically figure. However, we are not going to continue because it is going to be long. So what we will do, we will show it, and then we are going to break it when I mod of 2 is equal to 0. Okay, so and then we are going to show it. So let's run this. So we will basically do the reshaping. Let me just do this conversion. And then we will basically run this. So you can see this. I have just taken only 2, that is I is equal to 0 and I is equal to 1, because it was like an infinite loop otherwise. So because as long as there are batches, there are basically the pictures are available in this, because there is a flow functionality I am using, datagen.flow. So datagen was this, I have told you just now. So this was datagen. This was the datagen, because this is what is the image generator. So we are using this image generator. So it's a generator. I explained to you in previous video what is a generator. It's going to yield pictures. So images, number of images to be yielded. So we are controlling that, and we are just breaking it. So we just are going to see 2 pictures. So what is that 2 pictures? So now you see, this was the original picture. This was a cat, which was some like this. So we are now rotating it or whatever. So some processing has been done on this. So we see this. These are the 2 samples of this rotation. Then we have done this break. Okay, so you got for I is equal to 0 and I is equal to 1, and again we are using image.array to image for batch 0. So you got this batch 0, and then basically we continued it like this. So you got 2, because our batch size is 1. So that's why you got 2 pictures. Now let's go back to our slide. So this is what we have seen, the display augmented images. So this is what. So after doing the augmentation, you can see the original image. Now this, like I have taken a photo in mobile or my selfie, and then I am trying to play with it. So I am rotating it, or I am trying to do some activity over it. Probably I am trying to change the background like that. So you can see some few changes have happened. So suppose if I would have taken here another say video, another photo. Let us say 5. Let's see how this image looks. We'll try to load this image and we'll try to show this image. Okay, so this type of cat. We'll try to convert it. Once we convert it, we are going to reshape it till the end of that. Then we are going to play with it. So you got it like this. So you see that these are the changes that have happened. So like that, this is the actual data augmentation. Now this becomes, it's more like, now otherwise if you didn't do data augmentation, then you would have got only this image, which is the original image. Now you are getting the versions of various images of those original images. Okay, so that's the way this basically works. So let's revert it to our third picture, which we are using it. Okay, so now let's go to our slides. So we have seen this augmented images. We have seen this. We have seen the picture. We have seen the method also. So we have done all those. Now we have to understand one more concept, that is how do I use a dropout with data augmentation. Now why this concept has come, or why this topic has come. So what has happened actually is that I have shown you the augmented image. So when a network is trained, or when a neural network model is trained with the data augmentation, whatever the configuration that I have told you, or you can create your own configuration. So the network is not going to see the same input twice. So that we have ensured, because there is no duplication of the input. Why? Because either you have rotated it, or you have done some flipping or whatever. So we have done a lot of those things, and that I have shown you now. But the problem is the inputs it sees, that is the network model, that the input it is going to see they are still intercorrelated. Why? Because they are going to come from a small number of original images. Why? Because let us say that you have 1000 images of cat, or say 1000 images of dog. Then from that 1000 images, say let us assume you are going to create say 2000 images, or say 3000 images. However, even from 1000, say you created 2000, they are not going to be different. They are going to be like the cat's image, however just rotated, or however probably you have done some clipping, or you have done some changes basically. So they are not going to be like different images, they are going to be intercore. So there is going to be a heavy intercorrelation. That means that is what I was trying to explain to you in this video. So or in this one. So you can see this was my original cat image, and when I done the this one, the data generator, and I have done those changes in that, like I have invoked this data generator.flow, and then I converted it and all that. Still you can find it out. Okay, this picture is still similar to my original, though it is flipped and all that. So probably there is a flip. However, still it is very similar. There is some rotation. So that is what basically I am trying to make this point. So this particular thing, like the inputs are still correlated, highly correlated, because they come from the original number of a small number of images. So not new information, but only remixing the existing information. It's like you have a song which was created, probably original song, and then you are just trying to remix it with say some other beats, or some other say some instrument or something. Okay, so you are not trying to recreate it, or it's not a new thing. It's something. It's like a remix. That's why it is called remix of a song. The same thing. So you're not remixing it. You are trying to remix it. So you're not creating new things. So not new information, but only remixing the existing information. So this may not be enough to be completely get rid of overfitting, because I told you overfitting was explained as part of our earlier videos. So what do they do then? So to tackle this overfitting problem, they add a dropout layer. So again in my previous videos I explained you the concept of dropout layer and all that. So basically you add a dropout layer which is again supported by Keras. So you add that dropout layer to the model before the densely connected classifier. So now you have a situation where you are going to make use of data augmentation, plus you are also going to add a dropout layer, and because of that, then probably in the literature they say that your accuracy of prediction when you handle it, or when you provide a new data, then that improves. So now let's try to see how this is going to work. So we are going to make use of data augmentation, as well as we are going to add dropout layer, and then we are going to make use of the function which is fit generator. Now, because we are going to use fit generator, or for that matter it's a huge amount of data, it's going to be slow, so I'll just explain you through the code, and that probably that is good enough. So we are now trying to define the model. Now you can see this is the same model that I have explained to you earlier. So we have a layer 1, so this is a sequential model. The first one is a model, model 1. I am purposefully used the model 1 variable name, it will change. Then we are going to add layer. So this is again input shape is 150, 153. So we know this, I told you last time in the last video. Then there is a max pooling. This max pooling concept was told to you. Now this becomes 64. Activation is ReLU. So this is like first layer, second layer, then third layer 128. Again ReLU. Then this is the fourth layer. This is the same model that I have told you in the previous one. However, what we have done is after flattening we have added a dropout, and my dropout concept was explained to you. So we are using 0.5 as the dropout. So what is the difference now? We have added a dropout. So let me take you to the last video's layer. So here we have said this is the layer 1. So you can see this is the same thing. Then the layer 2, then layer 3, layer 4, and then the flattening. So now what we are doing after flattening, we are before dense layer we are adding the basically this dropout layer. So that is what we are doing. So this dropout is now going to help us. So we have added the dropout layer. Then there is a dense layer which is, and then the final sigmoid which is a activation, where we want to take a decision whether it is a cat or a dog. Then again we are doing the binary cross entropy, so that we have, all those things were told. Then metrics, we are going to measure accuracy, then optimizer RMS prop, so that also we have seen earlier. So let me just basically execute all these things. So I'm going to execute this. Then we have seen dropout is added here. This I am adding. Then I am compiling the model. So model is compiled. Now I am going to generate the training data. Now try to understand these concepts very clearly. Training data, we are obviously rescaling. So you know the reason, we want to fit it within 0 to 1. Then to this we are adding this rotation, which I told you when I was doing data augmentation. So same thing is there. Rotation 40, you can play with it. Then zoom, shear range, everything is taken, flip and all that. So this is the same thing. So we are generating training data by rescaling and plus the data augmentation. However, the testing data is not augmented, it is just scaled, that's all. It's like, suppose I don't want, because it's the test data that it can be anything. It is not the one that, it's like a question paper, it's like the problem that is coming to in your exam. So there I am not going to do any augmentation, it's just rescaling, because it's like you are just converting it so that the data is within 0 to 1, that's all. However here, so training we are doing with augmentation so that we can tackle more problems, or we can, that's the purpose of data augmentation, that you play with the images and you augment the image. So we are augmenting the data which is used for training. However, the test data we are not augmenting. Why? Because that's the case, that is real case. So we are not going to do that. So we are just simply rescaling this. Then we are going to do the training data training. So that training data is the same method, flow from directory, which we have used, batch size 32 here. You use the training dir. From the training dir you take the data and you feed this basically. So you are, this is my data, this is the configuration train underscore data gen. So this was the train data, which was the image data generator, so which is going to do the job of scaling, rotation, everything. On that you pull the data, that means where the data is, that is in the train directory. So say it's a cat or a dog, whatever, and then you basically have a convert it to 150 by 150, then batch size 32, and then obviously binary, because you are having both. So this is a train generator, another is a validation generator. As we know, for fit generator you require two generators, one is a train, another is a validation. So these are 2000 images which belong to two classes. So this is, it has executed. Then validation generator. So validation generator data is not a augmented data. That's what I told you. It's not a augmented data. It's not augmented data. Just rescaled. So there are 1000 images. Now we are going to do fit generator. So again we are running it. Ideally we should run it for a large number of epochs, like 30, 40, 50, like that. However, it takes so much of time even to run 3. So we will, now fit generator we are giving train generator, which is the same thing last time we have done, because now my train generator is having augmented data. Then steps per epoch is the same like last one. Epochs 3, validation data generator, there is no augmentation used, only rescaling, and the steps are 50. So now we can simply execute it. Now you can see even to start the first epoch it takes good amount of time, so it's pretty slow. Yeah, you can see now it has started taking. So this basically will keep on happening. So what you get is history. So at the end of this running of this epoch you are going to get history, which basically is having accuracy. So it is going to have this data like loss, accuracy and all that. So you can see this loss is pretty high, and then it will over a period of time as we epochs increase it is going to improve. So overall this plays a better role compared to that. So what will be your homework, or what is the exercise will be, you have this history with augmented data, and then you know how to plot, because I have explained to you in our previous video. You can plot it like this, because now you get the history. This is exactly you are getting here, which I have done last time. This was the history. Here also same thing which I am running below in the Jupyter notebook. So this is history you are going to get. So use this history, which is now the latest history, and import the matplotlib, and then you basically plot. So what will you plot? You are going to plot training and validation accuracy. So this code remains the same, or this matplotlib, and then you see how this training and validation accuracy as well as loss is now compared to when you feed it with the augmentation. So that means without augmentation, which was shown in the last video, and now in this video which I am currently running this for epochs 3. So it will take time, because you can see there is it's very slow. So you will have to do it on your own computer, on your own laptop, and then you will have to plot the history. So this is what basically was part of this video. So in this video we have basically understood two things. One was the data augmentation with Keras, and then in that we basically understood the what is the solution, or what is the way to do that, and why you require data augmentation, then limitations of data augmentation, and then why people make use of dropout layer as well as the data augmentation. So all these things were shared as part of this video. I hope you like this video. Thank you. Hi friends, welcome to deep learning tutorial series. The topic for this video is pre-trained network. So we are going to deal this topic in relation to computer vision / image processing, and apart from that we already have seen convolutional neural network. So that also happens to be one of the integral part when we are going to deal with image processing and computer vision type of applications. So let's get going. So when it comes to deep learning, when you have a data set which is relatively small, then typically people try to make use of a pre-trained network. So let's try to understand why pre-trained. So when we talk about a pre-trained network, so essentially pre-trained network is a saved network that was previously trained on a large data set. So obviously the name itself gives us that information, like it is pre-trained, so you already have trained it. However, the important thing to note is it is on a large data set. So example can be, you have a large scale image classification task. So probably if you have a network which is already trained to classify images, and if they are large in number, that means that large data set, then that such a network or such a model is basically a saved network that we are planning to make use of. So the advantage of large data set and general data sets, now here we have added a word general data set, is because when we talk about large data set, then obviously we are trying to take a data set where you don't have only very specific images, but it spreads across the images. That means we will see that as we proceed forward, what do we mean by general data set later. So when we talk about a large data set and a general data set, so spatial hierarchy of features learned by the pre-trained network can act as a generic model. That means whatever the visual world you have, so whatever the spatial hierarchy of features I have explained you as part of the previous videos about convolutional neural network. So what is mean by spatial and stuff like that. So here the spatial hierarchy of features learned by the pre-trained network can act as a generic model. So these features can prove useful for many different computer vision problems. So for example, train a network on mostly animals and everyday objects. So we are calling this as classes. And then you can use this trained network for say identifying furniture items in images. Now let's get back to the point that I just have said, like large data set and a general data set. So suppose I am obviously going to a large data set, but general data set basically means like you are going to you are going to have such a data set where you don't have just say for example animal photos or only human beings photos, but you can have also say the furniture items or the day-to-day things that you typically see. That means that visual world, whatever we see as part of that day-to-day stuff. So you basically are going to have such photos or such images which are large in number, and we are going to consider it as a general data set. So you basically train a network on say mostly animals and everyday objects, and then use this trained network for say identifying furniture item is a good example basically to understand this concept. So another advantage is a portability advantage, because portability of learned features, because now you are talking about learning, so portability of learned features across different problems is a key advantage of deep learning compared to the shallow learning approaches. So it makes deep learning effective for small data problems. That is, anyway, this point will also become clear. What do we mean by features across the different problems? So we will also try to get into that to a certain extent. So let's now try to understand a pre-trained model, and the pre-trained model that I have given on the slide is basically titled as VGG16. Now this is one of the very popular model, and the reason to take this as an example is because up to now whatever we have studied in as part of convolutional neural network, so it is similar to that thing that we have already studied. So approach overall remains more or less similar, and it's very easy for a new person to understand how do you deal with pre-trained model. So that's why we are basically going to understand VGG16 model. So let's try to get into little details about it. So it's developed by Karen and Andrew, and they are basically part of Visual Geometry Group Lab of Oxford University. That's why this name VGG is there, and in around 2014 this model was developed. So it is simple and widely used ConvNet architecture, and it is basically part of for the ImageNet or image dataset. And the ImageNet or Oxford, it is also called as Oxford dataset at times. So ImageNet dataset basically consists of 1.4 million images, and they are basically labeled. Labeled means we can say that these are the groups of images of say furniture, these are the groups of images of say cat, these are the groups of images of dogs, like that. So like that there are basically 1000 different classes, and that's why we call it as labeled images. So it consists of 1.4 million, it's a huge number labeled images, and 1000 different classes. Then some more detail. So it achieves an accuracy of 92.7. Again, you can find this information in general when you try to Google on this, Google about VGG. Then ImageNet dataset contains images of fixed size of 224 by 224, and they are obviously 3 channel. Why? Because we have the RGB. So when you are trying to deal now with respect to images, that means the tensors, and we have studied tensors earlier. So you basically have to deal with 224 by 224 and then 3, that means 224 by 224 cross 3. So the model now processes the input image, and it's going to output vector of 1000 values. Why? Because there are 1000 different classes. Now why are we going to deal with this? So I have told you it's very popular, it is simple and all that. So another important thing is it basically comes as part of Keras, and our focus as part of this tutorial series is about Keras. So it comes as Keras application module. There are other image classification models that are available in Keras, and they are basically just told for the sake of completeness on this slide are say inception, then exception, then ResNet, then there is also VGG19, and then ResNet 50. VGG19 and VGG16, these are the basically from VGG group. 19 is not that popular, 16 is popular because it serves most of the purpose. This 19 and 16 number comes with respect to the number of layers in a particular model. So Now let's try to get into more about this VGG16 and how do we go about using it for feature extraction. So what are the steps for doing a feature extraction? Is you using the representation learned by a previous network to extract interesting feature from the new sample. So what does it mean? You are trying to build something on the top of what was already learned or what was already built by the previous network. That means using the representation learned by the previous network. So in our context, in this context, VGG is the previous network, VGG model is the previous network, so it has basically learned the things, so it has the representations, and now you use that to extract interesting features from the new data or the new sample that you plan to use. Then those features are run through a new classifier which is trained from the scratch. Now this is very important point. The features are run through a new classifier. Now here the focus is on a new classifier which is trained from scratch. Why? Because it should suit to your requirement. That is the way to put it in a very simple way. So feature, that means when we have dealt with a convolutional neural network as part of those video series, that particular time we have understood the overall concept, like you have the layers and all that. So here we are basically have the classifier which is going to be trained from the scratch. So why is it like that? So let me just recap this. So typical convolutional architecture or convolutional neural net architecture basically will have pooling and convolutional layers. So that we have seen this as part of our earlier CNN presentation. So these two things are normally called as convolutional base. So the terminology that is used for these two together, that is pooling layer as well as the convolutional layer. So they basically happen to form the convolutional base, and essentially it's a series of pooling and convolution layers. So we have seen this in detail. We also have done hands-on and all that. Apart from that, you also have a densely connected classifier, and using that classifier the decision was taken, like whether it's a dog or a cat or whatever, depending on the classes that you basically want to classify the images. So here the focus now is on the convolutional base, which is basically series of pooling and convolutional layer. So the feature extraction, now when we want to use VGG for doing feature extraction, then essentially it has sort of three steps. So first is use of the convolutional base of previously trained network, so that is but natural now or but obvious. Then running new data through the convolutional base, that is what I was explaining as point 1. So running new data through convolutional base, and then training a new classifier on the output. That means the output of this convolutional base will form as an input to the new classifier, because you are basically going to train it from the scratch. So these are the three steps essentially which are part of feature extraction when we use VGG. So why we are only dealing with reuse of convolutional base? Now that is a very pertinent question. The reason is because now I have told you we are going to concentrate, or we are going to use reuse convolutional base, but I said the classifier will be done from the scratch. So why is it like that? The reason is, it's a technical reason. So the representations which are learned by the convolutional base are more general. So they are more generic, and therefore you can reuse it. So when we say they are more general, that means the feature maps of a COMNet are presence maps of generic concepts over a picture, and which is useful information. That means like they are basically going to tell me the presence map of a generic concepts. Now it's see the way in which we are telling it, it is not an exact representation, but it is aiding me to take a decision. So it's like, that's why we have said they are convolutional base. The representations learned by convolutional base are more generic in nature. So what does it mean? The feature maps of COMNet are presence maps of generic concepts over a picture. Now these words are pretty technical, so I will explain you in the next slide in a very simple way what do we mean by feature maps. Okay, and apart from that, the object location, that means the object that you are trying to deal. So object can be the cat or a dog or a furniture item, say chair or a table or something, and within that, say probably if you are trying to deal with say face, or say a dog face, then you will have ears or you will have eye, like that. So object location is described by the convolutional feature maps. Anyway, these are little technical bullet points, so it will be explained in a very simple way as we proceed to the next slide. Now, what is the issue with classifier? So let's try to get into that also. So the representations learned by classifier is specific to the set of classes on which the model was trained. That means we have a model, and then we have used a particular classifier which was trained to cater to that particular need, and that's the reason, basically that is one of the prime reason, and we are saying that we require our own classifier. So what is going to happen now is that the representation learned by classifier is specific to the set of classes on which the model was trained. So it's going to contain information about the presence, probability of one class or the other in the entire picture. Then these layers, that means the classifier dense layer, get rid of the notion of space, because when you are dealing with images, then you need to take care of spatial feature. However, when this layer, that the classifier dense layer, is going to get rid of that concept, so no information where objects are located in the input image, and I have told you we require that information. That's why you are not going to make use of the classifier which was already part of say the pre-trained network, but we are going to make reuse of convolutional base. So let's try to understand the bullet point that I have said as a technical points for convolutional base. So let's try to get into those little detail. So when we have a model, so you typically will now know that we have a multiple layers, like multiple layers can be pooling layer, then the convolutional layers, and like that ReLU, you put ReLU and all that. So we have seen all those things. So that it basically means the depth. So the depth of the layer in the model is a very important parameter, or it's one of the important criteria. So what does it, why I am saying that segment is because the level of generality of the representation extracted by the specific convolutional layer. So the depth is going to decide, or is going to govern the level of generality. So the more the generality, or that means you can reuse it. If it is a very specific, then you can't reuse on a new data. So what you require is basically a level of generality. So let's try to make it still simple. So layers, that means you have layers in a model. Now let us say it is a 10 layer model, 11 layer model, or whatever, you have different layers. So the layers that come earlier, that means which are nearer to the input, so the layers that come earlier in the model extract local highly generic feature maps. So what are the examples of feature maps? Like edges, colors, texture. So that's why I said I will try to make it simple. So when you talk about feature maps, so essentially you are trying to deal with edges, visual edges, whatever the edges you see on a picture or a photo, then the colors, then the texture. So that is what, so the layers that are going to come earlier in the model basically are going to deal with the highly generic feature maps like edges, colors, texture. Then the layers that are higher up, they are going to abstract, they are basically going to extract more abstract concept. That means say object level, like you can have it like the eye of a cat eye, or a dog eye, or say some portion of say chair, say back of a chair, like that. So the layers that are higher up extract more abstract concepts, and the layers which are earlier basically are going to extract local highly generic feature maps. So if the new data set, now the point to note is, if the new data set is going to differ a lot from the data set on which the original model was trained, so perhaps use only the first few layers of the model to do the feature extraction, because it is but natural. Because if you have used a data set that was trained for say some X type of images, and it's not going to cater to your requirement now or your need, then in that case there is no point in using the full layers or all the depth. And that's why I said the depth of the layer is a deciding parameter, or it's basically depth of the layer in the model is going to govern that. So you perhaps use only the first few layers of the model to do the feature extraction, rather than using the entire then convolutional base. So this is a point which should be noted in general when we try to make use of a pre-trained model. So how this can be used? So basically, as I have told you, there is a support in Keras. So Keras application we need to import. So from Keras.application we need to import VGG16. Then we need to make use of the constructor, where we need to pass basically three parameters. The first parameter is a weight. So this is a weight where we are going to make use of ImageNet, because as I have told you, that is what the this VGG was basically used or was developed. So accordingly, so it was like that image database, ImageNet database. So we need to make use of that that weight file. So it's a mate file to initialize the model. So when you make use of this constructor, so automatically this weight file will be downloaded for you when this particular code will be run. And when we look at the demo, I'll explain you this a little bit more. So weight is a weight file which is used to initialize the model. That is the first parameter. The second parameter is include top is false. Why? Because false top means the classifier. So we are not going to include that classifier, as I have told you the reasons and all that. So classifier, so include or not. So densely connected classifier on the top of networks, obviously it will be false because we don't need it. So it's not needed. Third parameter is the shape, because the shape of the image tensors that is fed to the network. So we are going to feed 150 cross 150 by 3 channel. That means we are going to do some scaling and all that, so that we will see later. But the thing is, we are going to basically make use of 150 by 150 and the RGB, that is 3 channel is what that 3 is indicates. Then let's try to understand little bit of summary, because we are going to take a look at this VGG model summary. So the final output or the final feature map shape will be 4 by 4 and then 512. So on the top of which you need to connect a densely connected classifier. So this will be the final feature map shape 4 by 4 512, and then on the top of it you are now going to make use of your own densely connected classifier, and I have told you the reasons and all that. So how do you proceed now? So there are two techniques of proceeding forward to use the model. So first is you make use of a feature extraction without data augmentation, and the second or the part B is like feature extraction using data augmentation. So as part of part A, so feature extraction without using data augmentation, we have seen data augmentation in previous videos. So we now know what is data augmentation. So when we are not going to make use of data augmentation, so we are going to run the convolutional base over the new data set. That is the bullet number 1. Second is, now the output will be stored. So store its output to a NumPy array. So that means we need to convert it to a NumPy array. Then you feed this NumPy array as input to a standalone densely connected classifier. So what is the focus here is, the focus is when you are saying that you don't require, or you are not going to use, rather you are not going to use data augmentation, that means we are going to rely on converting it to the NumPy array. So converting to NumPy array happens to be the important say step as part of this. When we actually go to the demo, you will understand what I am trying to say, but the converting to NumPy happens to be important point. So this approach, that is the part A approach, requires running the convolutional base once for every input image. That means whatever the convolutional base, that is the VGG base, it will run once for every input image. So because of this approach, it's going to be fast and cheap, and because of this fast and cheap overall approach, that's why there is no data augmentation. Then we are going to make use of predict. So whatever the model, that means VGG model, that object, so model object, so we are going to make use of functionality predict to extract features from the images. So we will go through this as we proceed in the demonstration also, as part of this video, as part of the next video where we talk about demos. So as part of this demo, we will try to understand pre-trained component without data augmentation. Now when I said that I am going to have an approach where I am not going to make use of data augmentation, then obviously we need to understand how do I make use of data augmentation. So let's try to quickly summarize that before we go to demo as part of the next video. So the part B, that is feature extraction using data augmentation. So here when we want to make use of data augmentation, so what people do is, so they extend the model by adding dense layers on the top and running the whole thing end to end on the input data. That means you add the dense layer, you are going to do that job, so you need to add dense layers, then you run the whole thing end to end. So why this approach allows us to use data augmentation? Now I have told you are going to add dense layer and then you run the whole thing. So what's going to happen is every input image goes through the convolutional base every time it is seen by the model. Now there is a difference because I have explained to you here. Here I have told you that part A approach requires running the convolutional base once for every input image. That's why I said it's fast and cheap. So here every input image goes through the convolutional base every time it is seen by the model. So obviously now you can sense it, or you can very well appreciate that this technique is now going to be more expensive than the one that I explained you as part of part A, where there was no data augmentation. So what we will do in the coming videos, we will go through the pre-trained cognate with without data augmentation demonstration, and then we will go through the pre-trained cognate with data augmentation. So these are essentially demo A and demo B, which we will take a look at it as part of the coming video. Thank you. Hello friends, welcome to Deep Learning tutorial series. Myself Srirang Korde. In this video, we will understand about pre-trained network hands-on activity. That means we will make use of a pre-trained network and we will see how it performs. So as part of this pre-trained network, essentially we are going to make use of VGG16 model. So here we are going to focus on two things. One is we are going to focus on a feature extraction without using a data augmentation, and the second part is about feature extraction using data augmentation. So when we talk about feature extraction without using data augmentation, we are going to run the convolutional base over new data set, and we are going to store its output to a numpy array, and then we are going to feed this numpy array as input to a standalone densely connected classifier. The reason is because we are going to have our own classifier, and that will basically allow us to classify the images. So that essentially is a part A approach or the part 1 approach, and here when we do this approach, then essentially we are going to run the convolutional base once for every input image. So this is a basically it's a faster technique. Essentially it's a fast and cheap. That means we are not going to do any data augmentation. And here we are going to make use of this predict approach and or the function which basically will be useful. So that's essentially the part A of the demo. Then the second part will be about feature extraction using data augmentation. So here we will extend the model by adding a dense layer on the top, and we run the whole thing end to end on the input data. Now why you typically are going to take this approach? Basically, like now every input image goes through the convolutional base every time it is seen by the model, and obviously because of this approach or this thought process, this is going to be a expensive approach over the part A or the part 1. So that's essentially the second part or the demo B, which is pre-trained cognate with data augmentation. So without spending unnecessary time now, so let's get into the Jupyter notebook and we will try to understand this. So for that, first thing is that I need to import the TensorFlow. Then once I import the TensorFlow, then obviously I will make use of Keras, and the earlier old version was like we used to do keras.application and then we used to import the capital VGG16, but now here we have this keras.application and then we are importing the VGG16 which is in small. Now obviously this is a convolutional neural network which is also called as Oxford net and has been explained as part of the theory video earlier. Now what we are going to do is we will first quickly take a look at the version. So here is basically 2.8 version. Now we are going to make use of this VGG.VGG16. So essentially is the VGG16, that means the capital VGG16 is the model, and to it one needs to give the weights. So I have already downloaded the weights from this URL which is from the GitHub, and so I have kept it at some location, say whatever this is the URL d python projects and all that. So it's a big stuff, and here you can see it's a h5. So that is actually the weights. So I am giving this weights to this model which is VGG16. then I don't require the classifier which is inherent as part of this model, because I am going to have my own classifier. So that's why include top is one that we are making it false, and the shape that we plan to give basically is 150 by 150. So now that decision is ours, and it's a 3, that means you have 3 RGB or YUV. That means it's a 3 YUV or RGB image. So let me just execute this line, which is like creating the model, and here we are calling this model as con base. So it's like a base model that we have. Now once we have created this base model with the weight file and the other parameters like input shape and all that, so we can quickly take a look at the summary. So you can see now the shape is 150 by 150. That means at the input level it is 150 by 150 and it's a RGB. Then you can see it keeps on, then the first one is a 2D layer, which basically it's a convolution 2D layer. Then there is a max pooling layer. So here you can see this is 150 150. Then after pooling it is by 2. Then you have this con 2D, which is again 75 75. Then once again at the pooling level you make it half. So like that you keep on doing till in the end you basically have the last one, which is you have this 4. So that's essentially the your con base or the con base dot summary. So once we have this VGD, that means it's a VGD model. So now we are going to do the feature extraction. So for that we are going to import operating system and util activities. Then this is the place where I have the images of pet images, which are cats and dogs. So I am just giving the path. Then I am just forming the base directory where I have taken few images, which is basically called as base directory. So we have just called it as cats underscore dogs underscore very small, so that the I can show you the demo. Otherwise, showing the demo becomes difficult. Now I already have created the base directory and all that, so I'm not going to run this line because it's like creating mkdir is a command to create a directory or make a directory. So I'm not going to do because it's already been done on my machine. So I'm just now going to give the train directory. So for that I am going to join the base directory, and to it I am going to join the train folder or the train name. Similarly, to the validation directory, I am going to use the base directory and I am going to join the validation. So these are the two places where I have training images, and then the validation means it's like evaluating. Then once again I am not going to make the directory train dir and validation because I already have done it. Now I am just going to have the different directories. So like train directory where you are going to have two things like train cats directory and train dogs directory. So I'm just going to make use of this os dot path dot join, and I'm just going to join this cat and dog. Similarly validation. So this is very simple thing. The reason is because at this place on my laptop or on my computer, at the under cat I have train directory cat, similarly under dogs, and similarly for validation. So this is like just setting the appropriate paths. Then I am obviously have created this directory mkdir, so I am not going to run all this mkdir. Now I can, what I am going to do now is I am going to choose some number. So right now I am going to say that I am going to train the images uh, count as 200 and validation images is 300. So obviously I can change it here. So let's say that I want to have train images as 200 and validation images as 100. Then I'm just going to basically do this job of original directory of the cat. So you can see this is the original directory where I have the cat images like D Python projects, Jeta Keras, pet images and the cat. So all the cat images are in this. Similarly, if I want to now copy that, so I have already copied it by running this program. So this program is a simple program where I just take all the JPG format for I, and then for I in the range, that means train images dot count, and then I create this os.path dot join, and then I copy. So using this shutil.copy file, I just copy source and that means source to the destination. So obviously source and destination. So here destination is a small one. So that I already told you. This is that very small, and original is original. So I am using this base directory. I am created this. So I am doing all the jugglery. So I'm not going to run this because I already have copied it, copied the things for training data, training cats, and similarly validation cats. Then similarly for dog. So again I have created, copied this for dogs also. So let me just print this information. So now you can see total training cat images are 100 and total training dog images are 100 and validation cat images are 50 and dog images are 50. Now here basically we have chosen this count 100. So accordingly it has taken this. So validation images end was 100. So I could have done it here 300. So probably I can just do it once again. This is like a end, so it's not a count, it is end. That means 100. I will get larger or more number of this one. So let me just once again do it. I don't want to copy, and then I'll just do. Okay, so now it's good enough. So that means training cat images are 100 and validation cat images and dog images are 50. So that is what I am doing as part of this. So here you can see this is count and the validation image end. So this is again similar. So I am not running it. So already I have done. I told you. So that's why even if I changed it, it didn't impact. The reason was because I didn't run that copy portion. So I don't want to do it right now. But I can always do it and overwrite it. So right now I don't want to do that because it takes time. So that's why even if I change the number, it's not going to impact. So it's going to keep the same 100, 100 and 50, 50. That means for training, I'm using 100 images of cat, and for testing or for validation, evaluation, I'm going to use 50 cat images. Similarly for dog. Now, we have this final feature map was 4 by 4. So that is what at the pooling level, I told you this. This is that 4, 4, 5 and 5 and 12. So we should keep that in mind because we will be requiring that information later. Okay. Now once we are done with these basic things, now we want to extract the features and we are using NumPy array and we are not using any data augmentation. So what we are doing is we are obviously making use of NumPy, then we are making use of image data generator, which is part of pre-processing module of Keras. So it's a pre-processing of image. So what I am doing now to generate the data, I am dividing each image by 255. So I will have a normalized this one, and I am selecting the batch size as 20. That means 20 in one chunk will be divided. So that's the internal, that means that number will be internally used here in the generator. So now there is a function called as extract features. So to this extract features, we are going to pass the directory and then the count. That means how many count is required. Now important thing to note in this is features. Here you see the shape is 4, 4 by 4 and 5 and 12. Why? Because that's what we are going to form the classifier and we want to classify the image, and this is the sample count. So sample count will be formed. So initially all the features and labels will be zeros and the shape will be, that means the count, and then 4 into 4 into 512, and then it is the count, whatever the count we set, and then using the generator it is going to basically generate the and that generator basically is going to generate the features and the labels, and it's going to do it in a loop. So you can see this code. So here in this, so let me just show you how am I calling this. Probably it will be easy. So now train image count is say 200. I want to give 200 images. So train features and train label. So I want to create these features and label. So for that I am now going to call this function which is extract features, and to it I am just passing the train directory, then the image count. So image count is here say 200 because I told you we don't have too many images because I want to show you the demo, otherwise it slows down. So I'm going to extract feature. So what is that feature? So essentially the features and the label. That means it's like a input and the output, like it's like a y. So this is like x train and this is like a y corresponding to that y train. It's something like this. and similarly you have validation image count is 100. So here we are going to use the same function extract features, and validation image count is what we are passing, and again it's like a y, it's like a x test and y test. So that is what we typically are habituated to using that. So I am just telling you in the simple language. So now this extract feature is passing, we are passing the directory, and then the count is passed, and then it's going to take the images from this directory. So for that, flow from directory is the function which is part of data generator. So we are using that, and to that we are going to pass the directory, then it's going to it's going to size it properly, so that we are going to get 150 by 150, then 20 at a time, that's why the batch size is 20, and then it's obviously it's a binary mode, that means 0 or 1, like essentially it's a class mode is binary. So that is what we are passing here, and then we have used this I, and then we are basically just doing this feature extraction. So what do you do? So we are extracting these features, that means input batch and label batch in generator, and that is what the generator was created, and then we are using this con-base dot predict. So now the images are getting sent to the VGG model. So that is what we did earlier, and I explained to you that VGG model. So we are passing this image, the input batch 20 at a time, and then we extract the features, and then we form the features and the labels array. Essentially, it's an array that we are forming, which is a numpy array. That's why we are using this, and then it will break. That means we keep on incrementing I, and when it exceeds the batch size, I into batch size greater than sample count, then we break the loop, and then finally we basically return the features and label. So let me just do this in front of you. So okay, so I think I need to run this code. I didn't run this, so let me just run this. Okay, now I have extracted. So you can see this images, found 200 images belonging to the two classes. So that is what I told you, like we have two classes 0 and 1, or whichever, right, cats and dogs. So essentially there are two classes. So you see it is 20 at a time, so 10, that means that's why it is broken. So 20 into 10 is 200. So the moment it has become more than 200, it has broken. That's why we sample count was 200. Similarly, we are going to do for validation image count, and it should go for 5. So 1 2 3 4 and 5, and then it will break. So we got it now. So we essentially, you got train features and train labels. Similarly, you got validation features and validation labels. So now we are done. Now we just want to create a numpy array. So we will reshape it, and the extracted features are currently of the size, or shape rather, samples 4 by 4 and 5 and 12. So we are going to feed this data to the densely connected classifier, because it's our classifier. So we need to flatten it. So we will flatten this out. That means train features will be in np.reshape. Then input is train features, and it will be flattened out of the size train image count multiplied. That's what I told, 4 by 4 into 5 and 12. So it's a numpy array. Similarly here, validation features, and then the numpy array, which is validation image count 4 by 4 into 5 and 12. So we will now, once we are ready with this, so we will define our own classifier, which is essentially our densely connected model. So we will use this sequential model. Now you see here we are passing this input dimension. This is important. Input dimension 4 by 4 and 512, because it's getting added to what was the VGG net earlier we have done. Then we have a dropout layer where we have zero point 0.5. So just to get rid of overfitting underfitting problem, we have added a dropout layer, and then in the last layer we have an activation, which is a sigmoid. So which is a final one neuron, and then you compile. So you compile this, then you fit the model. So here you see I am passing train labels, which is a train labels and train features, and so essentially we are passing train features and train label, which is a numpy array, and we are giving 10 epochs and batch size 20, and we are passing the validation features also, which is again a numpy array. So that's what I told, we are using this, and we can reduce the epochs and all that, okay, because if you increase epochs too much, it will take a lot of time. I can't show you the demo then. So you see the point here to notice, it has reached 10 epochs, and the loss basically is quite reduced. It has reduced it has in between it increased and all that. So finally it is 0.0557. Accuracy is pretty good, like 0.98. So we can plot this result. So for that we will import, and then we have this history. So history essentially helps us to plot. So history we will use this. So history dot history, where we have accuracy, then validation accuracy is the history dot history validation accuracy, then loss, then validation loss, then epochs is like the range from 1 to the length, whatever the ACC range, that means accuracy plus 1, and then you plot it. So this is the normal matplotlib. So here you will see this training and validation accuracy. So this is the training data, and validation accuracy is like this, and training and validation loss. So here you see the training and validation loss. Initially it was large and it decreased, and then once again it has started. That means it is moving towards oversaturation. So we should not have too much of training. That means if we reduce, probably it will be number of here probably up to 9 is good enough. We should not have 10 epochs or something like that. That's what he's trying to convey. Now once we are done with this, now we will try to do the feature extraction with augmentation. So we will have Keras model, we will import it, then we will once again create a model, but now I have named it as model 1. So it's a new model. So now to this model we first add the convex. Now we are doing augmentation. So in our earlier one, let me just show you that. So we have created a plain dense, rather we have created a sequential model, and then we basically have made use of this input which was created, which was output of that. Here what we are doing, here we need to see this carefully. So here we have added conbase, that means VGG model itself is added as the first layer, and then to it we add a flattening layer, then we have dense layer where there is activation ReLU, and then the final layer which is a sigmoid where we need to take the decision of cat or a dog. So this is the model 1. So model 1 summary. So you can see this is that VGG1 which was part of the first layer, and then on the top of it we added flattened, then dense, and the final one. So we can simply print it. So here you can see that we are not the full model is trainable. So it is telling that this number of trainable weights before freezing the convex is 30. That means 30 are the number which can you can train. So how do you find? So you basically have length of model 1 dot trainable underscore weight is a property, and using that it tells that okay, 30 weights I can train. So I don't want to train the model now, because I am going to rely on VGG model, and I am augmenting that. So that's why I am making it false. And now once again we will print it. So it is now going to say that number of trainable weights after freezing there is only 4 now. So that is what we are interested. Okay. So once we are done with this, now we are once again doing the same thing, image data generator, we are rescaling the data, then we are rotating the image, then we are giving the width, height, that means that rotation, then the other parameters like shear range, then zoom range, horizontal flip, true whether you want to flip it, then fill mode nearest. So there are various fill modes are there, so it's going to fill according to the nearest pixel. So that is what it is. So we are going to generate the train data. Similarly, we are going to generate the uh, uh, test data generator. So image data generator, and we are not doing anything here. Then train data generator, we are basically now this is the data. Now we have to actually get the generator. So we will use this train data. Here you see the size is given 150 by 150, batch size is 20, class modes is binary. Obviously pets and dogs, there are two classes. So we found 200 images. Similarly, validation generator. So we have 100 images. So we will compile. Now you see model 1 dot compile I am doing, and now I can do the fitment. So fitment I can do doing fit generator was an older technique, or it's now getting deprecated. So model 1 dot fit. So train generator is what we will give. This is the train generator. Then we will just run for 2, otherwise it's very slow, it's extremely slow. So I'm just going to show you for 2 epochs, and let me just run that. And then validation data is a validation generator, so it is pretty slow. You can see this when I'm talking to you, it is just in the first epoch itself. So it takes a good amount of time, then it will hopefully it will go to the second epoch. Yeah, and now you see the accuracy is little increased from 0.56, it has become whatever, it is improving, it is reducing, whatever. So yeah, so it's close to 61%, so that is the accuracy. So then we can basically plot this. Obviously we have just run it for two epochs, so it's of no use, but we can just for the sake of academic purpose we can just plot it, but it's of no use because we should run it for more epochs, but I didn't do that. So what is the difference between the two? The two differences which I showed you, model and model 1, was in the model 1 we have made use of this VGG1 as the first layer, then we have added flattening directly, then we have added this ReLU activation dense layer, and then the final dense layer where we need to take the decision. And here we trained it and we kept it only for 4 weights trainable, not the full model trainable, because we are relying on that. And here we are given the augmented data, that's why it was slow. So that's why we could run only for 2 epochs. So that's essentially this particular demo where we understood the two things. One was the feature extractions without using data augmentation and feature extraction using data augmentation. So these are the two things, and the important thing, when we were doing without data augmentation we made use of NumPy array so that the processings were faster. I hope you like this demo. Thank you. Hello friends, myself Srirang Korde. Welcome to Deep Learning tutorial series. In this video, we will understand this pre-trained network, that means VGG16, which we have seen in one of our earlier videos. So we are going to improvise on this and we are going to take a look at this concept or this usage of VGG16 uh, as part of hands-on activity, and we will understand what are those improvisations that typically can be carried out as part of using this pre-trained network. So let me now take you to the Jupyter notebook. So here in our earlier video or in the earlier hands-on, we have made use of this VGG16, and in that we were having an approach where we were trying to do the feature extraction and we were trying to create the directory and stuff like that. So that was a little longer approach. So we will first have an approach where this type of directory creation or copying and stuff like that typically will be reduced. So that's a small thing. Apart from that, in this video or in this demonstration, we made use of image generator. So image data generator is what we have used. So now we plan not to use this. So that means there is an improvement that has happened as part of Keras. So we plan to use this improvement rather than making use of image data generator, which was a little older way of carrying out the things. However, we will continue to do the same thing. That means we will basically make use of a pre-trained network without data augmentation, and we will make use of pre-trained network with data augmentation. That means we will have our own classifier. So that approach, however, at the top level remains the same, but the two things, that means the directory creation approach as well as the usage of image data generator, these things are changed. So now let's try to get into the newer approach or an improvised approach. So for that, let me just import Keras as well as import the various layers, and then I'm going to import operating system as well as the utilities that I typically require. Now I'm going to have two variables, that means original dataset directory. I'm going to just put this to the path as whatever the path that I have, and I have some pet images, and then I have basically a new dataset where we have this pet images in a relatively smaller form. So there is a directory which is called as cats underscore dogs underscore very small. So let me just have these two variables, that means original dataset as well as new dataset. Then I can make the subset. That means what I can do is from these pet images I can copy few things in the source as well as, yeah, that means from the source I can copy it into the target directory. So here you can see there is a function which is make subset, and then I copy from 0 to 100, that means 99, or rather 0 to 99, that means 100 images I am going to copy from the particular folder. And what I am going to do is that I am going to have a subset which is called as training. That means I have three folders now. One will be a train folder, another will be a validation folder, and third will be the test folder. So essentially there are three folders that I can make. So I am not going to run this because I have already done this, but here what we do is that we just have two categories in this function which is called as make subset. So there are two categories, one is a cat and dog, because we have these two things. And then what we do is that from the original dataset directory which I just told you, this is that variable, that means the original place where the images are available to me, I am going to have a category. So here you can see this is original dataset underscore dir, and then slash category. So this is the org, and then dir is the local variable that I am using. So from in the new dataset directory I have a subset name. So subset name I just told you, which I will be passing. So like for example, it can be train, it can be validation, and it can be test. So subset name followed by the category, that means it will be either cat or it will be dog. So I just do that, and then I copy from that start index to the end index, and I copy, that means from source, that is original, to the destination, which is essentially like train, validation, and test, and in that you will have cat and dog. So that is what we basically I'm just copying. So there is nothing difficult thing about it. It's a very simple thing to even understand. So now I'm going to just use this, and now I'm going to rely on this technique which is going to have tensorflow.keras.utils import image dataset from directory. So you see that there is a change now that we are going to do. Earlier we were having this image data generators, and then we were using that directory and all that. So it was a little I will say roundabout approach. Now there is a simpler approach. So we will rely on this. So here I have the size of image. I'm taking the same thing which we used it earlier, like 150 by 150. So 150 by 150 is the size of image. And then I have three data sets, that means train data set, validation dataset, and test dataset. And I use this function now, image dataset from directory. That's why I have imported this, and there I just give new dataset oblique train. Then the whatever the image size I want to have, that means I want to create 150 by 150, because the image can be of larger size. So we are going to use only 150 by 150 so that the processing time reduces, and then in the batch size of 32. So that way I create these three things like train dataset, validation dataset, and test dataset. So you will see it says there are 200 files belonging to two classes, that means cats and dog. Similarly, 100 files for validation and 100 files for testing. So we can just quickly take a look at this snapshot, and it tells the same thing which I just told you. Then we want to basically show the shapes of the data and the labels that has yielded by the data set. So we can just show that. So you can say that data shape batch is 32, the image size is 150 by 150, and then 3 is for RGB. And obviously label batch is like only 32, array of 32. So that is what we just try to get an idea, because we did the batch processing here. That's why this batch size was kept 32. So once we are done with all these basic things, now we are going to use the pre-trained model. So this is similar the way in which we have done earlier. So we just import VGG16. Then we have the conbase where vgg.16.vgg16, that is the function, and to it we pass the weight file. Then we don't require the classifier, that's why it is set to false. Top is false, and then the size is 150 by 150, and 3 is for RGB. So we have this model which is a conbase, that is a base model, which is essentially a VGG16, and you can see its input is 150 by 150, and it keeps on at the pooling level, it is reduced by half, so 75, like that it will keep on till you have 4 by 4. Now we want to understand this process of how this particular thing is processed. So let's understand it. So this portion that now I am explaining to you is more for explanation or for understanding purpose, rather than we are not going to use this code. So this is more from explanation point of view. So here you have a numpy, I am importing it, and now I want to basically have this image file. So I am going to take image file from new dataset directory, from train folder, that means because I have created that earlier, then from cat some random 10.jpg. So this is that image file which is set 10 cat 10. Now I am going to use this image which is from keras.preprocessing, and I am going to pass this image which is essentially the image file, and the target size is obviously 150 by 150. So we have this, and now I am going to basically show you this image, and then tells this tell is going to tell me all the information. Now what we want is we want to understand it. Why? Because now this particular image I am going to convert into the numpy array. So this was that my image which we just showed, and which was some cat number 10. So we want to convert this image into an array which is a numpy array. So I have explained to you even here earlier that we made use of numpy array here also. So here on the similar lines we basically are going to do the thing. So this is a numpy array, and then we basically uh, expand it, and then we have this pre-processed image. So now you can see this is a pre-processed image which is using this vgg.preprocess input x, and which is essentially expanding the dimension. That means it fits into that particular size, whatever the x size is. So you can see this is that uh, that means 4-dimensional array. So here you can see this is the image which is essentially 2 dimension. So now we want to basically extract. So this was more for the understanding purpose, how you convert an image into an numpy array. We are not going to use this much later. I mean to say internally it will be used, but not directly. Now let's concentrate on the important thing. So now this is something similar where we are going to predict the images by giving the input images. So for that we are going to create a list which is an empty list, and then for features as well as the labels. That means it's like an X and this is a Y. So for images and labels in the data set. Now what are the different data sets? So you have 3 data sets like train, then test and validation. So let's say for the example we have here train. So we pass this train data set which I have shown you earlier. So which we created earlier. So let me just scroll up and show you once again. So this is the train data set where we have formed this image data set from directory which we made use, and we have this data set. So now you see we are not relying on data generator which we did it in the earlier technique. So this is the improvisation. So now let's go into this. So we are going to do this pre-processing of images. So vgg.preprocess input, and then we are going to predict. So let me just run this code and then I'm going to call this function which is extract features and labels with the train dataset. So that way I'm going to get train features and train labels. So it is going to take little time. Why? Because now using this vgg16.predict, that means in a way we are using this con base which is essentially vgg16. So the base model which is a vgg16.predict, sort of it's almost like that. So I'm predicting and I'm getting the output which is essentially features, and all those features are appended in a list which is called as all features, similarly for labels. So now you can take a look at the shape. So you can see there are 200 images. So that's what I told in training, we are 200, and then the essentially they are at the output I told you it's a 4 by 4 and 5 and 12. Now from where 4 by 4 has come? This has come because this is that con base dot summary. We have done this earlier. So let's go to that extract features now. So we have the shape. Similarly here you should get 200. Now I can similarly take validation features and validation labels and call the same function for the validation dataset. So it will take little time, because now it will be doing processing for 100 images. So now you have both. That means your train features and train labels as well as validation features and validation labels. Now we will define our own densely connected classifier. So this is similar the way in which I explained to you earlier. So you have layers flattening, you flatten it out. Then you have dense layer where you give the input. Then you have this X where you have the dropout layer, that means so that you get rid of issue related to the over this one over saturation. That means either you can undertrain or overtrain the model, so that problem will get resolved here. And then you have at the final layer, it's a one neuron where you are using the sigmoid activation. So then we have created a model keras. Then you compile with binary cross entropy and RMS prop and metrics are the accuracy. Now we are going to do the model dot fitment. Now you see this accuracy is 0.74. This is, and validation accuracy is obviously higher, but otherwise in general the accuracy is almost 0.74 at the start first, this one, and then it has reached to 0.975, that is close to 9.98 roughly. Then you can plot this. Now the problem is we have just very few epochs. So if I increase it to 5, then probably we will see it will take some more time. So you can here see the accuracy was 0.98 and then it has really improved and now it has flattened sort of. So we can plot it. So you see this, it has almost training and validation loss. So this is a very good curve. Like you can see this training loss is really reduced and validation loss is also getting reduced. And then this is a training accuracy and validation accuracy. So validation accuracy and training accuracy. So obviously we should have more this one. Then we can similarly extract features and labels for test data set. This is more for the academic purpose. So once we are done, so now here we did that extract features without data augmentation. Now we can do the same thing with data augmentation. So once again I will have a con base where I have just made it base 1 and I am not going to set it trainable is equal to false. Then I make trainable is equal to true. So it tells okay there are 26 parameters which basically can be trained, and if I just make it false then it says 0. That means I cannot train. Now I am going to do some random flipping of the image, horizontal flipping, then random rotation say 0.1 and then the random zoom is 0.2. So these are the parameters I passed. Then I have this model where I create input is equal to input shape which is size x, that is 150 by 150. Then I use this data augmentation and you see there is a difference now. So data augmentation, here these are the parameters as part of data augmentation for the input. Then we do the VGG pre-processing of the input. Then we have this Conbase 1 I just explained to you earlier. Then we have flattened, then we have dense layer and then the dropout. Once again dropout layer is used and then the dense. So this is similar the way in which we have done in our previous video. The only difference is here we are using this, again this is an improvisation with respect to the data augmentation over what we did earlier, because if you look at the earlier one with augmentation we were doing like this, like it was again the image data generator and to that we were passing all these parameters. So instead of that now there is an improvisation because we are not using the image data generator. So overall there is a the main thing that gets achieved is obviously simplicity is there of use, but apart from that I have found is without using image data generator is really faster when we make use of this Keras support, that means improvised support over the earlier one. So data augmentation, so we will execute it. Then we have this model one and then we can compile and then we can just run it for one epoch because it will take little time. When you do the data augmentation it takes little time. So this is the way you can do the model dot fit. Then you can see this accuracy is 0.71. Obviously we can improvise on epoch, so I am not improvising it because it takes little time. So then we can just evaluate the accuracy for the test data. That's why I created test data in between. So test here you can see this, it is accuracy is 0.91, so it's fairly good enough. Then we can fine tune this pre-trained model. So what we can do is that this was the model. Now let me explain to you, this concept is very interesting. So this is a VGG model. Here there is an input layer, then uh, this is a con 2D layer, then con 2D, then max pooling, like that you will see we have this that means this particular con underscore base one dot summary. Now this is a con base one underscore summary is the new thing. This is what that con base one under VGG. So here this is that base one. It's not base, it's a base one. Okay, so that's what I'm trying to highlight to you. And then we have made this trainable is equal to true, false, and all that we played with it. So let me just go to this now. So we want to fine tune it. So this is that summary. Now it says total parameters are this and non-trainable are this because we have made 0. Now we can say this trainable model to be true, and then in that there are various layers. So you see there are so many layers are there, like layers like input, then block 1 underscore conv, block 1 underscore conv2, like that there are so many layers. So we want the that means from there are total layers, so last 4 we want it. So we want it to be whole model, we want it to be trainable, but last 4s we don't want it to be trainable. This is, you can play with this. Okay, so now it will say, okay, so it says only 6 can be then possible. Earlier it was 26, then we have changed it, so like that we can play with it. So you say it becomes 8. So like that you can, because we are I'm increasing it here. Okay, so let me just keep it as it is. So then you have 6. Okay, so you can play with it and it will give you an idea. Then it tells which are those. So now you can see here total parameters are that, trainables are this and non-trainable are this. Why? Because we played with this trainable model and non-trainable model. That means it is, we are deciding or we are controlling the behavior of the model. Okay, and then we are compiling, we'll compile, then we can do the fitment with epochs. Say for example here I am just doing it for epochs 1 because it takes little more time, and here you can see accuracy is fairly enough. It is improvising or it will change in between here and there, and then basically you will get around 0.9, 0.915 or 0.91.5% is this accuracy, and then we can evaluate it on the test data, and that way you can get accuracy is around zero point 0.9. So that's good enough. Okay, so that's the way typically you can improvise or you can use this approach, which is an improvised approach over the image data generator as well as the file copying and stuff like that. So otherwise more or less the things remain same, but here the main thing is simplicity of use as well as faster. That's very important. It is faster. I have found at least faster than the using image data generator. I hope you like this demonstration. So this is what we did. Thank you. Hello friends, myself Shriram Korde. Welcome to Deep Learning tutorial series. In this video, we are going to understand an interesting thing, that is image segmentation. So let's see this image segmentation. So we can see there are few images are shown. So what we mean by image segmentation is that we would like to locate a particular image or we would like to segment it. So obviously here we are not going to do too many things, but we are going to do segmentation. So if you look at it in the first picture, there is a tiger and then there is a background or a forest. So we would like to identify or we would like to segment in such a way that we are able to identify tiger. Then if there is a photograph where there are people or persons who are standing near close to them, then we would like to identify person 1, person 2, like that. So that is again another case where we are trying to show the image segmentation. Apart from that, then we can see there is a car and then we are trying to basically segment this particular picture or this photograph so that we are able to identify this sort of yellowish car. Then there is another car which is in the background at the back, then another car in the back, like that, or a person who is trying to walk here. So all these are the examples where we are trying to do the image segmentation. So probably the tiger one that I'm showing you as part of the first picture is very easy to understand. Is like you have a jungle or a forest, and in that basically tiger is going and would like to segment it out. Similarly for the person, it becomes easier for us to understand what we are trying to achieve. On the similar lines, if we basically extend this thought process, then we would like to identify different objects. For that, the requirement is of the image segmentation. So now let's understand the concept of image segmentation by doing a hands-on activity. So let me take you to the Jupyter and let me just because I was working on it. So let me clear everything so that you understand. So here you can see there is a site by name www.robots.ox.ac.uk, and then there are basically images are available, like you have pets and dogs, then you have flowers like that. Okay, now the thing that why I'm showing you is that we need to understand a concept called as tri maps. So why is it required? Because using this tri map only we are able to extract a meaningful foreground object. Why? Because if you look at this diagram, we were trying to identify whatever is in the foreground. Why? Because the forest is in the background, and the tiger is in the foreground. Similarly, if there are people who are standing in a row, or say close nearby, then the background we are not interested, and we would like to identify person one, person two, like that. Similarly, if you look at the cars, then we are interested in the foreground image, that means of a car, rather than whatever is in the background. Now that is what basically we mean by doing this activity. So to do this activity, we need to understand something called as a tri map. So what is a tri map? So tri map is a three level map, and that's why it is called as a tri map. So to extract meaningful foreground object, so we now need to provide a tri map. That means now if you just give an image, then from that image we can't make out what is the background and what is the foreground. That means to extract a meaningful, that word meaningful is a very important thing. That means something useful you want to get out of that particular picture, then you require to provide a tri map. So what is a tri map? So in a tri map, or when the user is providing the tri map, that means it is user's responsibility to provide the tri map. So it is basically going to segment the input image into three regions. That means there is a definite foreground, definite background, and then some unknown region. So to explain this properly, the tri maps will contain a pixel value. Typically it will range from 0 to 2. That's why it is called 3. So there are only 3, like 0, 1, 2. So the pixel values are 0, 1, 2 on a scale of 0 to 255. Normally when you have an image, then you have values from 0 to 255. But when you are having a tri map, then the values are going to be from 0 to 0, 1, and 2. So typically you will have 1 means say pet, or it can be an animal, then 2 means background, and 3 means a border. So that is one of the technique, or one of the way that typically tri maps are explained. Now where do you require this? So the this technique that I was trying to tell you, essentially it is called as image matting technique. So what is image matting? So essentially it's a task of extracting interesting targets from an image is known as image matting. So if we know these basic things, I think we are good enough to proceed forward. So now let's do one thing. We will basically do understand that we would like to create some images. That means we have two stuff now. One is a actual image, and another is a tri map of that image. So these are the two things. That means for a particular image you have a original image as well as a tri map. So that means now you require to do a lot of directory processing or processing, so that you basically have this tri map as well as the original image, and it is available to you. Then you need to do the processing. So the first step of this hands-on activity, or this practical, is like we require to work on creating proper image paths, and that means the different various things and all that. Okay, so that is a part one, and a part two is like actually you have a model, and then you give the data. That means you give these images as well as the tri map, and then you predict. First you train it, that means you fit it, and then you can predict it, or you can do the evaluation. So let me just do the first part, which is sort of rudimentary. We need to do that. So I have in the input directory I have images, and which are pets, that means cats and dogs images we are using, and then in the target directory we have the tri maps. That means it is like an answer, that is from an image. This is the answer, or this is the y value. So that is the target. That means it's a target, or it's a y value, you can say. So let me just run this first, and I will show you this exactly. So for that we are going to sort all these things which are available in the input directory. So let me just do that. So it's an input image paths, and the length of input image path is there are, so that means there are close to 7390. So 7390 images are there, and let me just do the target path. So again, once again we will do this. So it is 7390. That means for each image there is a try map. Now how do you understand this properly? So let's do this understanding properly. So for that we will use this matplotlib, and then we will choose some random, choose some random image, so say 21 index. So because there are 7390, I'm just giving 21. No specific reason that I have chosen 21, we can give anything. So then we are using this function which is load image, which is available to us in Keras utils. So to that we are just passing these image paths, which is, that's what I told you, it's like the doing some sort of setting of a directory path and all that. So that is done, and then to it I pass the index say 21. So we will just do that and we will load this image. So this is that image of a cat who is trying to say drink water from a tap. Okay. So now what is the corresponding try map for it? So that we need to know. So for that I am using this display target function, and to this display target function we basically are going to give the target array. Now this target array is, first we need to load the target image, that means it's a try map, and then we need to call this function which is a display target. Okay, so that is what we will do now. So let me just run this code, and now we will pass this. So now you can see I have used this load image, and then I have given this target path idx and color mode obviously are grayscale. We are not interested, it's not a colored image. And then we are converting this image to image array and then target image, and then we call this function display target. So what does it do? Display target is essentially going to take this image, it's going to make it so that you can show it properly. So it multiplies it by 127, then you don't have an axis, and then you show this array which is a normalized array using plt.imshow, and we are showing this as a grayscale image. So you see this, so now you can see, you can make out very easily, this is the image of a or this is the original image of a cat, and now from there this is the image that we want to identify, and this is actually the try map. So this is what it means. That means now we have such collection of 7390 input images and 7390 try map. So why did I do all this? Is to just to show you how this looks. So if you are interested in say some other number, say 215 for example, so let me just change it. So this is this cat which is sitting on some mat, okay, or whatever. So now we will show this. So now you can see this, this is that. So that's what it is. So 1 2 3 or 0 1 2, I told you, like these are the, 1 means pet, 2 means background, and 3 means the border. So that is, so you can see here there is a border, cat and all that. Similarly we can play with some other number. Okay, so this is a cat sitting in a box or whatever. Yeah, so you can see this is the way. So that's the way typically this thing will happen. So this is a try map. Now for that we are going to use this random number as required. First let's understand. So the image size that we are going to take is 200 by 200, and total number of images we are going to have, we are going to use 500 only because it's a huge data. So from that we are going to choose 500 images, and from that 500 images we are going to use for training as well as for the evaluation or for testing purpose. So image size we are going to set for 200 by 200. Number of images are 500. Now we want to do some again setting of path. So part 2 input images, here we want to convert, because I just showed you like we require to convert it to the image array for doing processing. So this is a image array, you return image to array, and this is that function image to array which we used earlier also, image to array. And this was that function image to array from keras.utils, and we imported image to array. So it's converting from image to array, that means from num to numpy array. So we just return this array by doing the image load image. Similarly path to target. Here we are doing path, then target image size is image size, I just told you. Color mode obviously is a grayscale. Then here we are subtracting it by -1 because we have values which are like we want to have it values between 0 to 2, that means 0 1 2. So that's why you require to do subtraction and then you return the image. So once we are done with this, Then we are going to have this x, we form the x arrays, which is that means we first create it with zeros, fill it up with zeros. Then you see the shape, which is a 500, total 500, and each image is 200 by 200, and it's a RGB. So x dot size we can just see. So there are, you can just do the multiplication and you will get. Now you form the input images and target. So let's do that. Input images is number of images plus image size, then 3, like that you just do, and targets. Okay, so this is the simple thing that we are doing, and then we just iterate using this for loop. So for I is equal to 1 to range. So range is actually here, range is number of images. So I just told you like number of images are totally 500 are there. So that's what we gave here, number of images 500. So we are going to have input images, and for that there is a target. That means it's, we are just doing all this. These are the like a processing. There is nothing that we are doing. And this is just example, like it's now targets is like value between 0 and 0, 1, 2, like that I just told you. Okay, then we are choosing 200 of these images. 200 we are choosing, that means 300 will be used for training and 200 will be used for validation. So we will do this job. So once we have done, so let me just do, so you can see there are 300 train images. Each image is 200 by 200 and it's RGB. So length of this one is, you can see there are 300 images. Similarly target, so target is okay, so this is train targets dot shape. So I have done the same thing. Then length is 300. Okay, now validation. So length of validation is 200 images and each image is 200 by 200. So length of validation is, there are 200 images. That means 500 we have divided into 300 as training images and 200 for testing or say validation. Now we will form the model. So we will import from the Keras, the TensorFlow we will import Keras. Similarly we will import layers. Then we have written a function get model. To it we pass the image size. So image size because it's our choice, and number of classes. So number of classes here are 2, like pets, which is cats and dogs. So first you have the input layer, which is keras dot input, then the image size, and then RGB. Then we do the rescaling. That means we divide each input by 255. Then we have, one is a convolutional 2D layer. So it's a, so what is convolution 2D layer? So let me just explain to you. So this is that convert 2D layer. So to that now we are passing strides. Activation is ReLU. Then padding is same. So let's understand what is padding here. So padding is, we are using padding. There are two values of padding. So one is valid and same. So we are using same here. That means it's on both the sides, left and right. It's going to make use of padding, which is with zeros evenly padded on left and right of an image. And then strides used is basically we are using strides oscillator. So strides is 1 or 2. So what is, it's like the strides like an integer. It's essentially it's an integer or a tuple of two integers specifying the strides of convolution. That means how much you want to, like it's like convolution essentially a multiplication. So on each side when you do that, then how much stride, that means it should take a stride. We say that when we walk, right, I'm going to take a stride of 2 steps. So that means how much it should move. So that is essentially the strides. So that is what we do here. So here activation is ReLU, strides is 2, and padding is same. So that is what we give. So we have this con2D layer. So we have this 64, then 128, and then 256, and then we use the transpose. So you can find out these details, what is this con2D. Similarly you can use you can do a shift tab here, and then that tells us more details about con2D transpose. It's like a transpose convolution layer. It is sometimes called a deconvolution. That means we are doing convolution and then we are doing the deconvolution. Okay, so you can play with it again. You can read that documentation. So we have the final layer, which is layers.con2D. That means 2D convolution, and then number of classes we know 2, activation, softmax, and padding, and this is the model. So it will return a model. So now we will call this function with the image size, which is image size, and number of classes are here. Sorry, number of classes here not 2, 3. I just told you that wrongly. So there are 3 classes. That means we want to have this, not the pets and dog classes, but the try map. That means 3 classes are there in a try map. So I just made a mistake earlier. So it's a 3 1. So let's see the summary. So now you can see this is an input layer, which is 200 by 200 and then 3, and then we did the rescaling, so that is added here, so it doesn't occupy any parameters, and then all these layers are added, then transpose layers, and then the final convolution layer. So this is the Then we compile the model. So here we use the RMS prop as optimizer, then sparse categorical cross entropy and matrix as accuracy. Then we can do the fitment, and here I am just running for two epochs. Even to run for two epochs, because it's a pretty time consuming activity, it requires some initial effort. Okay, so it is executing now. So you can see this is star, and it takes little time. Now you can see, yeah, so it has started, and accuracy is relatively low, and you can say it will take time. So in the meantime, when it is executing, let me just once again recap. So main thing here is, the first is the try map. So try map is what? So essentially you are going to identify a foreground, that means it's a definite foreground, definite background, and then the unknown region will be there obviously. So that is basically depicted as values from 0 to 1. That means 1 is for say pet or some meaningful car or pet or something, then 2 is the background, and then 3 means the border. So that we have seen, and then we have done a lot of jugglery so that we are able to do the processing, and I explained to you why you require to do numpy conversion, that means to convert it into the array and all that. So I explained to you, and we have seen it working also. Now let's see whether our this thing is done. That means the fitment that we were doing. Okay, so the first thing is going on, and okay, and then hopefully after certain time. So here you can see this accuracy is 52%, and it is still going on. So it takes little time because my computer is, yeah. So it has second has started, and like that you can basically see that it will take some more time, and the second will also go through. So that is the way typically you will see. So here what I have done is I have given the train input images and train targets. So that is like an image, and this is the try map. Then I have run it for two epochs. Each batch is 64, and then I have also given the validation. Otherwise, if I didn't give validation, it will be still faster. So roughly in two epochs, you can say roughly it is close to 60% or more than 60%. It will have. So it is still going on. It is hovering around 60%. So let's wait for a minute or two. I hope it will conclude sooner, because the other activities are also going on this machine. That's why it is little slow. So now probably you will understand, when we use, even if the machines are pretty fast enough, when we are doing multiple activities, this is a deep learning activities are tasking activities. That means it loads your computer a lot. So let's see, in roughly we can say that the overall accuracy is close to 60% or 59 to 60% is in the two epochs. So like that we can continue and we can improvise. So I hope you like this demo where we understood the image segmentation, and we have made the demo, or we have done the hands-on with respect to image segmentation. Thank you. Hello friends, myself Shriram Korde. Welcome to Deep Learning tutorial series. In this video, we are going to understand a very important topic, that is residual network, which is in short mentioned as ResNet. So in this video, we will understand the details about residual networks. Coupled to it, we will also understand the sample code base, so that as part of demo later we can take a look at how a residual network can be constructed. So let's get going. So as part of ResNet, we need to first understand what's the need for ResNet. That means why typically you require a ResNet. So important observations are like, there are complex applications these days like image segmentation, classification, then image detection. That's a demand, and that's what typically we require as part of various image processing applications. So what typically people have done, or the researchers have done, is they have made deep neural networks. That means they have added more layers of convolutional neural network, and it is typically referred as a deep CNN. So why do someone add such layers, or what's the purpose? So the objective of such thing is, like, when you add more layers, then the progressive layers, or the layers, are going to learn more complex feature. That means more the layers you have, then they are going to help you to learn more complex feature. That's the thought process. Now what's the issue here? So when you add more layers, then it becomes difficult to train, and typically the accuracy saturates or it degrades at times. And why does it happen? It's essentially because of vanishing gradient or exploding gradients. That's what literature calls it. And we have various other videos which talk about gradient descent algorithm, or in general the calculation of gradients. So when we talk about those calculation of gradient, so when we have such a deep network, then in that case those gradients which typically should be propagated, they basically vanish or they explode. So these are some of the reasons that people have come up with such a architecture, which essentially is called as a ResNet. So when I want to now solve this vanishing gradient issue, how do I typically solve this? So they are going to make use of something which is called as residual blocks. So when we talk about a ResNet or a residual network, so that's what the name has been derived from. So it is now called as ResNet or residual network. So this model is made up of residual blocks. So I hope now this becomes very simple or it becomes clear. Now when you want to basically form such a residual network or a ResNet, then those blocks essentially or inherently I will say that it's going to make use of something which is called as skip connection technique. So that means now we need to understand what is skip connection. So ResNet, as part of ResNet, now we will understand what is skip connection. So as probably the name suggests, it's very easy for someone to understand. So skip connection means there is a active connection. That means the skip connection connects activations of a layer to further layers by skipping some layers in between. That means now you are going to have connection as shown in this diagram. Now you can see there is some curve path is shown. So that means if I have an input x, then in this diagram you can see this connection is shown. So the skip connections connect activation of a layer to further layers by skipping some layer in between. So now you can see here in between, when this curve is there or this connection is there, curved connection is there, so in a way it has skipped in between layers which are denoted here as say whatever weight layer and all that. So these connections are in a way getting skipped. So that means now you are going to skip, you are going to basically purposefully do this type of connections, and that's why it is called as skip connection. So the skip connections connect. So what is it going to connect? So it's going to connect activations of a layer to further layer. Now here the further layer doesn't mean it's an immediate layer, immediate next layer. It means further layer. That's what that general term is used. So it's going to connect activations of a layer to further layers by skipping some layers in between. So that's why this terminology or this skip connection is used. And when we talk about a ResNet, so essentially it's made up of residual blocks, and the residual blocks are made up of such skip connection. So let's understand more about it now. So let's keep this diagram or this figure in front of us so that we understand more about this figure. So let's get into the details now. So when we talk about the skip connection, so this skip connection is going to solve the problem of vanishing gradient, and that's what I think I have told you in the previous slide. So how is it going to help me solve this problem? So essentially it's now going to create a alternate path, and that obviously that path is a shortcut path. So that means now you have a alternate shortcut path for the gradient to flow through. So that's the way it's going to help so that you basically don't face the issue of vanishing gradient. Apart from that, such connections allow the model to learn the identity function. Now why this is done, or it's going to learn identity? Identity means one. That means why it is such a statement is made. So the objective of such a thing or the main focus here is this is going to ensure that the higher layer will perform at least as good as the lower layer and not worse. So at least as good, that means you are ensuring that because of such connection the higher layer is going to perform, or rather it will perform at least as good. That means it's not going to suffer degradation, or it's not going to suffer on the loss of accuracy, and later we will see how this helps. But the point is that so this ensures that higher layer will perform at least as good as the lower layer. That's why this is also highlighted in red. So let us say that you have a network, say which is a shallow network, and say another network is a deep network. So when we say shallow network, that means any other network up to now we have studied. So in general, when we say a network, so typically we will say okay, it's a normal network. Or at times, just to differentiate properly with respect to deep network, people may refer it specifically as a shallow network. So let us say that you have a normal network and another is a deep network. So that's what we are studying here. So you have a function hx, so which is going to map the input x to the output y. Now that is what typically it is going to do. So now that means, now what is the aim of that? So the aim is to have a deep network perform at least as good as shallow network. So that's what. So because otherwise if you have a deep network and then let's say that it's going to perform bad, then what's the use of such an approach? That means it's an unnecessary effort or unnecessary study that we are trying to do. So that's why that statement is made, that aim is to have a deep network perform at least as good as shallow network, or in general we will call it as a normal network, that means without having such connection. So to achieve this, you basically are going to have additional layers in deep network, and you are going to have additional layers in deep network, and those additional layers should learn identity function. So what is going to happen because of that? So the outputs will be equal to inputs. That means now you are ensuring that because of this approach, that the additional layers will learn identity function, so outputs will be equal to input. That means it is going to perform at least as good as the lower layer. So that is what the thought process is. Now still it sounds little difficult, so let's try to understand it in simpler way, or in a more better way I will say. So let us say that you have a normal network, which we typically will call it as a shallow network. So you don't, that means you don't have a skip connection. So here the input x, whatever the input x you have, so that typically will be multiplied by the weights of the layer, and then there will be a bias. So that let's suppose if I am where I am currently hovering the cursor, or let me just put the uh, pen here. So you can see this particular thing. So suppose if this is a particular layer that I am currently referring, and let us say that there is no skip connections and all that, then in that case input x will be multiplied by weight layer. That's why here weight layer is shown here, and it will be multiplied by the weights of the layer, and then obviously there will be bias. So this particular thing, that means hx, is mentioned as f of x. So when you say f of x, in short it will be like you have a weights plus there is a bias, and typically we will call this fx as a activation function. Now this is what typically will happen if you are going to have a shallow network. Now in ResNet, what is going to happen is you are going to have, say, fx hx is equal to fx plus x. So now that means now you have this x that is also getting added. So you can see this in this diagram, the x is getting added, and that's why this adder is shown here, or a plus sign is shown here. So this is that plus sign which basically I am referring to. So now what you have is hx is essentially, it is now fx, so which was anyway there. So this was essentially the fx that we were trying to understand. So this is fx, and then on the to it you are going to add the x. So let me just make it here this laser pointer. So now you can see this is an fx. So this was fx which I just mentioned. To it now there is an x that is fed here because of the skip connection, and because of that now you have hx is equal to fx plus x. So now if your fx is equal to 0, then what will happen is hx will be equal to x. So it's a simple thing that we can now infer from this diagram. So that is, we get x as output, which is also the input. So now what can be the issue? So when you have such a connection which is a skip connection, and that means when you have a deep network as mentioned here in the ResNet, then in that case what will happen is the dimension of input may vary compared to the output. Now that means compared to the activation function. So due to the, so why should it happen? It will happen because now you are going to have convolution layer on and or there will be pooling layers, and which we will see later as we go towards code and all that. So how do you typically solve this issue? Because now you are going to have dimensionality issue, or a not dimensionally not matching of input, not matching to the output. Then in that case what you typically are going to do is, there are two approaches. First approach typically is people are going to pad with 0,
So 0 is padded with the skip connection to increase the dimension. That means now if there is a dimensionality issue, and obviously you can increase, because when you are padding, that means you can only skip, you can only add. So obviously that's a one technique. So 0 is padded with the skip connection to increase its dimension. So that's a one approach. Another approach is, typically there will be a convolutional layer that is added. So it's like a one cross one. That means one dimensional convolutional layer is added. One cross one are added to the input to match the dimension. So then in that case, your output is now going to look at, output will be hx now. It will be fx plus w1, and w1 is the additional parameter that gets added, because now you are having this particular convolutional layer that you are adding. So this is what in general about the ResNet. Obviously everything is not clear with respect to this, but if you understand, very simple thing is like, you are going to have a deep network, and in that deep network is not going to perform badly just because you are going to add you have added layer. So that's why you basically have added a skip connection, or skip connection is there, and because of that skip connection you essentially are ensuring that your network performance, or your network is not going to be performing bad compared to the shallow network or the normal network. So if you understand this, this is good enough at the understanding level with respect to the ResNet or residual network. Now, we have seen in our previous videos, or in our earlier videos, we have seen VGG 16, VGG 19, like that. So when we talk about ResNet, so essentially it is inspired by VGG 16 and VGG 19. So here at the top you can see there is a VGG 19 diagram. I am not explaining to you here all the things. Just to, there are two more diagrams are added, or two more photos are added here. One is a 34 layer network, and another is a 34 layer residual network. That means this is a 34 layer plane network, and another is a 34 layer residual network. So here you can see this 34 layer plane network typically studied in literature. So we are not going into the theory aspects and all that. So this 34 layer plane network in the architecture is inspired by the VGG 19. Okay. Now in this, in which the shortcut connection or skip connections are added. That means people have studied VGG network, and to it they have added, first they made a 34 layer network, and then that means inspired from VGG net, and then in this 34 layer plane network they have added the skip connections. Okay, so here what they have studied in the literature is, ResNet has this particular ResNet, that means the 34 layer which we are talking about. So this has significantly enhanced the performance of neural network. And when they have checked it, so 34 ResNet, that means the plain one, or rather the 34 layered network with, that means the ResNet, that means with the skip connection, has lower error rate compared to the plain network. So that also they have studied. So just to give you some numbers, so here you can see this ResNet. There are obviously in literature there are other versions also, like A, B, C and all that. But you can see that when you have a plain 34 network, then the error rate is around 28. And if you are just a simple, or the first version or a first cut of ResNet 34, then you are 25. Then it reduces little bit and it goes till 24.19. Then there are other versions of ResNet like ResNet 50, 101 and 152. So what they have also studied is, they also have studied how much operation, that is floating point operations, that means how many CPU cycles and all that. We will not we will not get into the flops and all that, but they have compared VGG 19 with the plain 34 layer network, as well as the 34 layer ResNet, and they also have found that it can tackle complex thing, consuming the similar, I will say the similar flops. So point I'm just trying to make it is, overall what they have found is 34 layer residual network essentially is a better deal compared to the other thing. So that is what in general this slide I'm trying to depict, rather than we going into the theory, because, or other literature, because you can always do Google and get more details about all these things. So that's not the current focus of this video. So before we proceed forward, one needs to understand, is there a Keras support for ResNet? Yes, because now having said that it's a successful model, they have found it performing better, error rate is less, and so many things I just have told you. So because of that, Keras has built a support for ResNet, and there are multiple versions are there, like ResNet 50, ResNet 50 V2, then ResNet 101, then ResNet 101 V2, then 152 and 152 V2. So these are some of the various versions which are supported in Keras. So now from the academic point of view, or what exactly this is, you can always study the Keras APIs, and you can get the exact details about it. What the focus is here is, we will try to see, or we will understand the sample usage. That means when I say that there is a support in Keras, that means there is an application module, that means keras.application. So you can see here keras.application.resnet. Similarly, you can get keras.application.say resnet 101 like that, or resnet 152 like that you can get. So point I'm just trying to make it is, this keras.application.resnet is a function call. That means you have a support in Keras, and there are multiple arguments or parameters that one can use it, and we will I'll just explain to you few things here. So here you can see there is an include top, then by default it may be true, then weights are imaginate. So here include top means whether to include the fully connected layer at the top of the network, so that can be used even as a classifier, and we have seen it some similar thing we have seen, not for this function ResNet 50, but otherwise we have seen it in on 2D and other usages in other earlier videos. So include top is whether to include the fully connected layer at the top of the network. Then wait is essentially, again in previous videos we have seen the usage of ImageNet and all that. So I have told you the weights were downloaded and we have given the path and all that. So it can be like one of the that means one of the none, that means random initialization, or there can be ImageNet. So by default ImageNet is there, or you can give your own weights for the file, it can be loaded. Then apart from that, input tensor, so which is obviously here it's an optional. So optional Keras tensor, that means output of layers dot input. So if you have that, then you can always use it to use as image input for the model. Then input shape. So shape is essentially you tell only to be specified if include top is false. That means if you are not going to use include top, then you have to tell, you have to give the shape. So in the further code, that means sample code, how you typically construct a ResNet, in that I will be talking about it. So rather than understanding everything here, because you typically have to give the shape if you are not going to use the include top. Then pooling. So pooling means typically it's optional feature, feature extraction when include top is false. So you typically can have a global average pooling, or then otherwise, if you don't have any pooling, then it's going to output the last uh, output of the last convolutional block. Then if you have max, then max means the max global pooling. So essentially pooling is explained in other videos. So probably those videos are good enough for us to understand what is a pooling, rather than understanding now everything here. Then classes. So classes, it's an optional number of classes to classify any image. Obviously you have to tell how many classes you want. So only to be specified if include top is true, and if no weights argument is specified. So these are some of the parameters which you typically will pass, or will specify when you make a keras dot application dot resnet support. Various versions are there. Now the objective is that when we are now understanding this more, the objective is not to understand how this function can be used, because if I just say that okay, there is a function or there is a library support, it's like a library support, then you are not going to understand what is a ResNet. So we are not going to, as a demo, we are not going to make use of a keras dot application dot resnet function directly, but we will construct our own resnet, and we understand the fundamental things behind, or the basic things as part of resnet, rather than just making use of a direct library function of keras. So now let's see it in action. So when I want to construct a residual net, so I am showing you in a diagram. On the right hand side you can see there is a diagram. So now you see there is a shape that I am giving. That means this is a sample code, and when we go to the demo, we will make use of such demo code. So here inputs is equal to now keras dot input. So now you have an input layer. So please concentrate on this diagram on the right hand side because that is what is important. So you have this keras dot input and here you give the shape, then you have this, you form the x, so which I was explaining to you in the diagram. So this is an x. So how do you form the x? So essentially you are going to divide all the inputs by 255 because your image values are from 0 to 255. So you divide it so that they are between 0 and 1. So you do the rescaling. So you make use of this rescaling function, layers dot rescaling, and you divide 1 by 255 of all the inputs. So that these are the two things that I have shown you in the diagram. So these are the two things that I am showing you. Now we have a residual block. So that is what I was explaining to you in my previous theory slides. So this residual block is a function. To it now you are going to pass the input, then you can pass the filters, and then you can tell whether you want to make use of pooling and all that. So now you can see this residual is a variable there where I am copying. That means the input, whatever is input, I am copying in a variable called as residual. So you see how am I calling this? So you have this residual. So I am calling this function residual. I pass this input x, which is essentially this particular thing, which is a input. So whatever the input, this is that input after dividing it by 255. So this is what we have achieved here. Then you say initially the filters is equal to say 32, and then you can always play with the filters, and then you want to make use of a pooling layer. So now here you see I am forming a deep layer. So what I am doing, I first store this x in a residual, and then I have a direct connection. I will make use of this. So that is what this diagram is trying to show here. So you can see this is a diagram, and now this is like a skip. This is what we are doing this. So similarly here you will see here we have this connection. So what I am doing now, x is equal to layers.con2d. So I'm using a convolutional 2D convolution. Here I pass the filters. Then 3 is because it's a 3 dimension image, and rather RGB, not 3 dimension RGB. Then here activation is ReLU, padding is same, so it's going to pad both on the same sides. That means it's a, I have explained to you padding in my previous earlier videos or previous videos. So we'll not get into that right now. So our focus currently is on x is equal to layers.con2d. So you see this layers con2d, and here layers.con2d. Once again these are the two things. However, now if there is a if else statement used, so if pooling, then in that case you have a max pooling used. So you can see this max pooling. So here you see the pooling is true. So that means now I am showing you the final diagram or the complete diagram. So that means pooling is true. So this particular portion of where I am marking this yellow is what shown here. So this is that pooling, which is that pooling is max pooling is shown here, and then there is a add. So you see this is the x is equal to layers dot add. So obviously else if filters is not equal to, so that portion will not be executed right now because I have made pooling is equal to true, and then you have an add. So what is the addition? Addition is x, and then obviously residual addition is x comma residual. So residual is what? So residual is what basically initially I have stored it here. So that's what essentially I was trying to mention to you. So you have this residual, and then you have x, which is now x is essentially what? So it has gone through this 2D layer. Then there is a these are the after this rescaling, these are the con 2D, then con 2D1, and then con 2D2. So you see these are the two layers which essentially have come because and then so these are the things which essentially, and then you have this residual is equal to layers dot con2d, and then multiplied by the residual, and then once you have done in this pooling, then you have layers is x is equal to layers dot add, and this is where the addition is done. So this add is now, you can see this add is essentially x comma residual. And why this is residual? Because you can see this directly, this is that con2d. So residual is equal to layers dot con2d, filters one strides, and that's what I told you we are going to convolve. So that is what here one by one. So that is what here this con2d is doing. So I hope now this diagram, right hand side diagram, is very clear and it's mapped to the code that we are using here. So once we have understood this, then we will continue. So the code of on the residual side, residual block is the same. There is no change. So this code is now the same. Again, I am calling this function residual block. Here the filters are 64 and again pooling is true. So now you see these input which was shown on the previous slide. So these two add after add. So now it has come to this block. So there is a 2D filter and underscore 3. That means it's a con 2D block once again. Then con 2D 4 and then con 2D 5. So that is what two filters. Same thing. Then there is a max pooling. So this is that max pooling. So this is at max pooling, and then after the max pooling you have this residual multiplication and then the add. So why this has come? This has come because you are calling this residual block here. So now there is an add. So now there is no change. So once you have understood the diagram on the previous slide, to the same diagram, only thing there is no rescaling shown, which was shown in the to start with, because we had input and then rescaling. The remaining thing like con 2D, the same thing is there, only thing the number is changed here. So con 2D 1 2, then it has become whatever 4 and 5, because this is a 3, so rather it has become 3 4 and 5. So now once again we will have another, because we are forming a deep network. So now I am once again calling this residual block. Here again input filters 128, but pooling I don't want pooling. So now in this the if portion will not be done, but this portion will get invoked. So now you see this output of the previous one is con 2D. Then you have once again this con 2D. So these are the two things. So this is mapped here 2D 2D, the rather first one, and then it has gone into the residual network. So this is residual. So this is that this particular thing is mapping here. So this residual is equal to layers dot con 2D. So this is at con 2D, it corresponds to this else if filter. So then once again you have this add x comma residual, and then you see I am using this global average pooling, and then you have a dense layer, which is essentially where you are using the sigmoid, where there is a one neuron, so that you can make a decision, and then and you form the network. So that's essentially this residual network, where we have seen three residual blocks called one after another. In first two blocks we have pooling is equal to true, and in the last block we didn't set pooling is we set pooling is equal to false. And then we have a residual layer which was different than the one, little different than the one that we were doing in if pooling is equal to true. So in one go we can just take a look at this complete code. So this was input is equal to keras, x is equal to layers, and then you can see this is the complete diagram. So then you have this function, this is that function which is called three times. So it is called three times from here, and this three times diagram or calling is essentially shown here. So this is input rescaling, then you have this con 2D, then 2D one, then this is that 2D, this is that second one, and then you have this residual. So this is that residual, and so this particular thing is residual, and then you have add, then once again you have this con, then you have add one, then once again you add by, because three times you have called, so three times it is done, and then obviously the paths are little different when you have pooling is equal to false. And then you have a global average pooling. So this is that global average pooling shown here, and then you have a dense network. And that's essentially in one snapshot you can just take understand the deep network, which is essentially a ResNet here, and try to show you in one go, so that you understand how we call, when you call this residual block multiple times, you can get an idea how does it look. So I hope you understood, or you have you got a better understanding now what is a residual network. In the further videos we will take a look at the use of this residual block, and how we can basically give an input images and understand the output. Thank you.
Hello friends, welcome to Deep Learning tutorial series. In this video, we will go through the demonstration about ResNet or residual network. In the previous video, we have understood the concept and overview about ResNet. So in this video now, we will continue with that code base, and we will learn more about this particular demo. So in the previous video, we have understood this particular code where we have to take input. So for that, we are going to make use of keras.input, and for that I have shown you the corresponding diagram. Then we carry out a rescaling, and then we have defined a residual block which essentially plays the core of the residual network. That means it is like the heart of the residual network. Now, when we talk about residual block, we have skip connections, and that is what I have explained to you. What is skip connection and stuff like that was all explained as part of the previous video. And in that video I also explained to you like how we are basically calling it multiple times, and how essentially this diagram, which is a consolidated diagram which is shown on the right hand side, basically is mapping or is portrays the code that has been shown on the left hand side. Apart from that, I have told you like here we tend to make use of global average pooling 2D, and that's one of the commonly used these days. So we will understand various poolings, though to a certain extent we have seen in previous videos what is pooling. So here we will understand more about global average pooling, and then we will go through the program or the code as part of running or doing the hands-on activity. So now let's understand little bit about the pooling and the global average pooling. So when we talk about pooling, so there are various types of pooling. Like we can have a max pooling. So here max pooling essentially is like you have, suppose if you have chosen a 2 by 2 or 2 cross 2 filter, then or a window, essentially it is called as window. Then of these four values of the image, so let us say these are some image values, then you tend to take the maximum of this, say 2 by 2. So here max of say 3, 1, 2, 5 is 5, so which is represented as 5 here. Similarly then 1302, so which is 3 is the maximum. Similarly for this 1447, so 7 is max, and 1224, the 4 is max. So this is what basically we have as a max pooling, and essentially it is helping me to do carry out down sampling, and we have seen this even in our previous videos where we have talked about CNN and associated things related to CNN. So that is what about the max pooling. Apart from that, there is another thing which is called as average pooling. So instead of taking just the max, people tend to take average of, say for example, if I'm taking say 2 cross 2 window, then I will take a max. Say that means I'm going to do summation, say 3 plus 1, then plus 5 plus 2. So that means 4 plus 5, 9 plus 2, 11. So 11, and then you divide it by 2 and then by 2 on, that means from horizontal direction and vertical direction, and that way you get the average. So like that you compute for all these, say for example if you have say 4 by 4 matrix, then you are going to get, from here you are going to get 2 by 2. Now if you look at it, this particular operation, suppose if I want to compare say max and average, then max is preferred and it's very widely used compared to average. The reason being, average means you have to sum, you have to basically, and then you have to compute the, you have to do carry out the division operation, and on horizontal side, vertical side. So it's a pretty, compared to max pooling, it is a comparatively, it demands resources or a compute resources from the CPU, or it takes more CPU cycles. So that's why max yeah, pooling is a preferred technique. Apart from that, now we need to understand a global pooling. So let's understand, it's a global average pooling. So here you can see now you have say multiple such frames of images are there. So let us say that you have here 1, 2, 3, 4. Then from these four images, which are say for example here 4 by 4, so you are going to form a single vector. Now that means this one, each entry of this vector corresponds to a particular frame. That means now I am talking about, when we talk about a global, so essentially we are talking about the complete frame size. So suppose if your frame size is say 640 by 480, or maybe 1081920 by 181080, whatever. The point I am just trying to make it is, we are not talking about a bigger frame. When we have discussed the max pooling and average pooling, we essentially are talking about the small portions of a particular image. Here when we talk about global average, then we talk about that at the frame level, that means at the x and y level. So from that, now you are, that means four frames in a way are just represented by a single vector, and each having, that means there is only one entry for each, and that's why that word global average. So you are now going to have an average at the global level. So let's understand more about it. So when we talk about the pooling, then essentially the feature maps of the, typically when we say that I'm going to use a pooling, then in that case what will happen is that in the layered hierarchy or in my neural network, so this feature maps of the last convolution layer, because you will have a convolution layer at the last, and that will be vectorized, and then after doing the vectorization they are typically fed to a fully connected layer. That means it can be a dense layer and it is fed to the fully connected layer, and then you will have say sigmoid or a softmax regression layer. It can be softmax, I'm just giving an example here, so it can be a some layer. Essentially it need not be softmax logistic regression, it can be any other layer. So point I'm just trying to make it is like you typically give it to a layer where you may use a sigmoid activation or you may have a softmax like that. Now when you are doing this, then the fully connected layer, so what happens, like when you have this typical architecture, then in that case the fully connected layer are prone to overfitting. So the one of the technique to get rid of this problem is to have a sort of random sampling, or essentially it is normally called as dropout. So you tend to use a dropout, and then it prevents this overfitting, and this is one of the strategy. That means usage of dropout, and again it has been explained in our earlier other videos. So that is one of the strategy. Another strategy is to replace the flattening layer. That means what you are intending, you are doing is like in a way you are actually you are going to replace the flattening layers. So that particular thing is actually called a global average pooling. So instead of using a dropout, you replace the flatten layers. So when I'm saying this, you basically are going to now have a global average pooling. So what exactly it means, let's understand it. So what it is now going to do, global average pooling, is it generates one feature map for each corresponding category of the classification task in the last convolution layer, because it's obviously used after the last convolution layer. So that means as I just told you, like you have that input frame of bigger size, maybe it is like a big size of x and y. So you basically you are going to generate one feature map, and that's what I told you by this diagram. So you are going to generate it generates a one feature map for each corresponding category of the classification. Let's say this is like a classification, then you are basically generating a one feature map. So how is it going to do? So it takes the average of each feature map and the resulting vector. So whatever the vector, because now it becomes a vector, as I'm hovering this cursor, so it becomes a vector. So this vector is fed directly into the sigmoid layer, or it may be a softmax layer depending on where it is used. So that I'm not particular about that last this one, that softmax or something. So point here is that you essentially are going to have a resulting vector. That is the important takeaway. So what are the advantages of such an approach? So here literature says that it is more native to the convolution structure, because you are going to have various con 2D. So it is more native to the convolution structure by enforcing correspondence between feature maps and the categories. Apart from that, there is no parameter to optimize, because now you don't have a parameter to optimize in the global average pooling. So in a way you are basically avoiding the overfitting at this layer. So these are some of the advantages. You can always find more information how it compares with the flattening layer and all that. So there are a lot of such things available in literature, but right now that's not the focus. So our focus now will be like we are going to make use of the one that I just shown you, the reference code or this residual block, and we call this residual code block this function or this def. We call it multiple times, and then followed by the global average pooling, and then you have this layer. Last layer is, say for example, the dense layer, and where there is only one. Here you can see that there is only one neuron, and then you have an activation sigmoid. So that is what basically we are going to understand now. So having understood this pooling, then global average pooling and all that, so we are now ready to go and understand the program. So let me now just explain you the program, because it takes time for me to run this code. So we will go through this one by one. So you are obviously importing Keras. We are going to rely on Keras neural network. That means you are going to construct its convolutional 2D model or 2D layers. We are going to use that. So we are importing layer. So TensorFlow.Keras we are importing, and then you basically do this input you take the input, and from the various pictures that we have, so we are going to use this pets and pets images, that is cats and dogs. And in the previous videos I have explained to you how do you create cat directories, then how do you create a subset, and how do you copy, how do you basically take only those selected few images and all that. So all that has been told. So again the same code is here. That's why I'm not showing you that code, because it just the same code is copied and pasted so that I can give the input. So here the input is keras.input. So this is the model, and here we are restricting the shape to be 180 by 180. Otherwise we have images of dogs and cats in various dimensions. So we want to uniform it, or you take a uniform size. So we essentially are going to take 180 by 180, and then it's RGB, that is colored image. Then you do the rescaling, you divide it by 255. So that's the input. So once you have found the input, now this is the residual block. So you basically have, so I have explained to you all this code in the theory, so I'm not once again going to do the same thing because it's already done. So you have this con2 layers, con2d, then pooling. So I have explained to you pooling true, pooling false, and all that. So all those things are explained as part of the code explanation. So this is the code. Then we call this function, that is residual block, three times. Then comes this average pooling. So I just explained to you what is a global average pooling. So to it you pass this input x, and then you are going to get the output x, and then you are giving this output x to the final where you are going to take the decision, which is about the cats and dogs. That means you have to take either it is a cat or a dog. So this is one is good enough. So we have this, and then you essentially going to form the model. So now let me show you this diagram, which is the theory, in the theory that I have shown to you. So for that, what you require is you should install a py dot. So how do you do that? So for that you basically require to do pip install py dot. If you have Anaconda, then probably it may be one of the module. If you do not have Anaconda, then you will have to do it by using pip install py dot. And then you require a graphviz. So this graphviz is a executable. You can download it from this URL, which is graphviz.gitlab.io, and then download. You choose as per your computer, that means operating system that you have. It may be 32-bit, 64-bit, or Linux or Windows, depending on whatever you have. And then you download it, because only then you basically can use this to show the diagram. So why is it like that? Because this py dot is going to convert into some intermediate format, which is called as dot format, and then this dot format is basically given to this graphics, and it generates a jpg or a whatever a jpg image from that. So what you need to do is that if you are running your Jupyter, you should stop it, then you exit the command prompt after your installation is done. So that means this is after the installation. You stop the Jupyter, you exit the prompt, then once again you launch the command prompt and then Jupyter. Then only this this will work. So what it will work? So work is like you basically are going to have, say for example, here I have given the file as, I have given this name of my file as my resnet1.png. So it's going to convert into PNG. It can also, I believe it can also convert into JPEG, but I think I am always using PNG. So this is going to do dot means for the current folder. So dot slash my resnet. So this is the name of the file. You can give any name, and then you give this file. So you give this file, and how do you give that? So you basically are going to make use of keras. So in keras there is a utils.plot model function. So to that you just pass the model. So that this is the model which is which we just have created, input and output. So keras.model. So this is that model. So you pass this, and then it's going to create a file which is to file is equal to image underscore file. So if I just go there, and if I just happen to show you, then you can see this. Let me just check. Yeah, so you can see this is the file that I would have created. I just wanted to create whenever I would have run this. So it's a PNG file. So if I just double click it, then it will show you this particular thing which I just was explaining to you. So but however, you don't need to double click and open it. It will open it will open it in this Jupyter itself if you have the graphics, and you require graphics because otherwise plot model will not work. So both these things are required. So So keras.plot utils.plot model is going to convert to the PNG file and also display it to you. So this is that complete structure which I have shown you in the slide. So that's what so this diagram which I explained to you in theory was taken from this actual code only. So let's go to the, so you, this is the diagram. So we will not get into all this because this was explained in theory. Then once again, if you want to get the shape, so this was a simple diagram. If those people who are very much interested or they want to know the sizes and all that, the way in which I have given, like for input, it was 180 by 180 cross and then by 3. So it is going to show the same thing. Then rescaling, again it is going to, basically there is input and output is going to show the size. Then con 2D, it's going to take 180. Then here you can see this filter it has taken. Then here it is 32. Then here there is, and you can see this is because after this there is a by 2, so there is a 90 90 and then 32. Then it will keep on reducing, then 90 will become 45 like that. So then 45, and then in the end you will basically finally it will be 1. That is what a dense where you have. So essentially you will have this 1. So point I'm just trying to make it is, like here we have chosen the filters and all that. So all those code was explained to you in the theory. So here you can see this filters 32, 664 and 128. So that is what all those details you can see as part of the shape information. So here you can see this 32, then 64 and then 128 and all that. So you can all these things. So this diagram is the same diagram except this information also is shown. So otherwise the diagram, both these diagrams are same. It's only the shape information that is added. So it helps rather than because otherwise I have to show you in the slide. So that is what I have done separately to you. So now once we have this file, so you can take a look at model.summary. So now we can see this is the same thing, input layer, same thing. So this is what, then rescaling, then con 2D, then 2D1, then max pooling. This is that's why it has become, because of pooling layer it has become half. Then once again it will be called, so 45, then it will be then none, like then after that you have this global average pooling, so obviously it will be none. And then you have this, finally there is a dense layer. So the important thing here is that this global average pooling is a 2D activity. So this is what it's a model.summary shows. Then the remaining code is about the same code which I explained to you in the previous videos about taking the pets images and just copying it and creating the directories and all that. So we can, I don't want to generate just keep for the sake of doing it. We can basically create a subset. That means we can have two folders, cat and dog, and we can create this cat dogs, cats underscore dogs underscore very small folder, rather sub folder. In that you can have cat and dog. Then you copy, that means from this source, that means pet images is the source, then you copy. So which copy? So from 0 to 100 you copy, then 100 to 150. So that's your call, what you want to copy and all that. Okay, so obviously I'm not executed this code, so it's not going to show you this all these things right now. So I'll have to execute this code basically. So make subset, I'll have to call. So right now I'm not basically going to do this copying and all that because it will take time. So similarly I can call so let me just clear for the time being, because it will take time because it's unnecessarily going to copy, which I have already anyway copied. So what I will do is directly go to the this one, image utils, import image dataset directory. So these are some of the things which again I explained to you in the previous videos, where you have three folders like train dataset, validation dataset and test dataset. So it has 200 files belonging to two classes, because 0 to 100 I have taken. So you can see this 100 for cat, 100 for dog. Then similarly 50 for dog and 50 for cat. So that's a total 100. And similarly validation and testing. So 50 50, that means 100 100 and 200. So I can compile this model and then I can do the fitment. So you can see this I have already executed because it takes good amount of time. So that's why I'm not executing right now in front of you, because it takes good amount of time and there is nothing difficult that I'm trying to explain to you, because this has been explained to you earlier also about creating this directory and all that. So here you give this train data set. Right now I just mentioned epochs 1, and then you give this validation data, and then you basically run this. Okay, so let me just run this program. let's see. And then because I anyway have compiled this one, so let's see whether it works. Okay, so now you can see it is takes time even to start its activity, because there are other tasks which are running on this. Okay, so it is going to take time, and then you need to increase the epochs and all that. Okay, so that's essentially this particular demo, where we have basically made use of this skip connection. So I explained to you what is the skip connection in the theory itself. So same code is used here, and in the diagram also explained to you the skip connections and all that. So all those things was explained to you. So important thing here is you have the input, you have this residual block, and then in this residual blocks you essentially have the skip connections formed. When you call these residual blocks multiple times with various parameters like pooling true, pooling false and all that, then you have global average pooling that has been explained to you. Then you have the output, which is essentially it's a dense layer with only one neuron, and then you form the model, and then you simply to this image to this model you basically pass this cats and dogs, which I just did in front of you, because I copying and all that was already done, and this is the same code which was explained to you in the previous videos. So that's essentially about this particular demo where we have understood the RESTnet. So I hope you like this video. Thank you.
Hello friends, myself Srirang Korde. Welcome to Deep Learning tutorial series. In this video, we are going to take a look at a very interesting thing as well as one of the latest thing, that is depth-wise separable convolution. Then we are going to have a comparison with respect to the normal convolution. That means we will study depth-wise convolution and then we will compare it with normal convolution. So let's get going. So when we talk about a depth-wise separable convolution, why there is a name depth-wise? The reason to ask this question is because we are otherwise known about the term convolution, and in my previous video I also have spoken about convolution. So when we talk about this depth-wise, so why that name depth-wise has come? So when we talk about such a name, so it typically deals with depth dimension and not just with the spatial dimension. That means when we have a picture or a image, then you typically will have the width and the height, so that is like the spatial dimension. However, there is a depth dimension also, and that deals with the clarity of the picture, and essentially when we talk about what is the depth of the color and stuff like that. So that's where this it when we talk about depth, so it deals with the depth dimension and not just with the width and height dimension. So when we talk about the depth dimension, typically it deals with the number of channels. For example, the image can have three channels. So like we will say that it's an RGB image, so red, green, blue. So image will have three channels. So that's an example when we talk about depth dimension. So let's understand more about now channels. So when we use convolutional network, that means we are now going to carry out few convolutions, and then image can have multiple channels. Now such a channel, that means each channel has a particular interpretation of that image. So that means now you have been given a image, and from that you obviously are carrying out multiple convolutions and all that. So when you carry out say few convolutions, then image can have multiple channels, and each image can have uh, or can represent a particular interpretation. So for example, if you say there is a red channel, then the red channel interprets the redness of each pixel. Similarly, when you say that there is a green channel, then green channel is going to interpret greenness of each pixel, and similarly for blue. So an image with say 64 channels has 64 different interpretation. So that's what basically we are talking about. So now having understood these two things, that means there is a depth dimension, and when we typically talk with a depth dimension, then we are talking about say channels, and here we basically are taking example of say three channels. That means to start with you can have a three channel. However, if you carry out multiple convolutions, then you may have more than that means that number can be more. That means you can have multiple channels. Now another question is, why did I put the title of the slide as depthwise? Obviously I explained to you to a certain extent. Then why that name or word separable is used? So when we talk about separable, so depthwise separable convolution is going to split a kernel into two separate kernel, and these two kernels basically do two convolution, and that's why that name separable or that word separable is used. So that means you first need to understand that there is a depthwise convolution that we plan to do, and essentially we are going to split that. That means the depthwise convolution, depthwise separable convolution splits a kernel into two separate kernels, and these two kernels basically do two convolution, and that's why that complete name now is depthwise separable convolution. So I hope now to a certain extent you are able to understand the title of the slide, that is depthwise separable convolution. However, we will understand this now in more details. So when we talk about convolution, as mentioned to you earlier, I have a video where I talk about convolutional neural network, and in that you will find convolution aspects which are dealt in detail and along with an example. So please refer to that video. Now let's understand the convolution. So I have here purposefully used the word normal convolution. That means the word convolution, when we say, then we are typically habituated with the normal convolution. So that means now you are given the image which is typically is say 2D, but the problem is, or the thing is, here image is not what we are referring is, image is not just a 2D. That means you are not just saying that image has say width and height, but we are going to say that image also has depth. So input image, say for example there is an input image, so input image of say 12 by 12 by 3, that means 12 cross 12 cross 3 pixels, typically means it's an RGB image of 12 by 12 size. So if you are clear with this simple thought process, so when we talk about normal convolution, then we say that image is not just 2D, but here we are now referring to the depth, and that means when you say that image is 12 by 12 cross 3 pixels, then essentially we are talking about an image which is an RGB image of size say 12 by 12. So let us take an example. So convolution with 5 by 5 kernel. Now this kernel word many times is used as mask. It is also used as a filter. So you may find in literature various other words that are used. But just to make the thing simple, we will in this video we will make use of the word kernel. So convolution of an image with say 5 by 5 kernel, and if I am not going to do any padding, and if I have kept the stride 1, because stride means the movement that you carry out with respect to the movement of the this kernel, or this essentially this is a 5 by 5 window. So when you are going to do that and you are not going to do any padding, then let us say that you are given an image of size 12 by 12, then on that you are going to do a convolution with kernel 5 by 5, then you are going to get 8 by 8 image. So that means what you are doing is 5 by 5 kernel basically undergoes a multiplication, and that multiplication is a scalar multiplication, and that multiplication is done with every 25 pixels. Why? Because you have a 5 by 5 kernel, and that 5 by 5 kernel is basically moved across or moved over the image of say input size 12 by 12, then it's at upper, that means when you are using this kernel, then it's going to work with 25 pixel. So using this 25 pixels, it's going to give you one number each time. That means you have this convolution performed, and I explained to you, you should refer to my video where I explained to you the convolution. So that means here in this example 5 by 5 kernel will undergo a multiplication, which is essentially a scalar multiplication with every 25 pixels, and which will give you a one number each time. So that's what so from 12 by 12, when you do this 5 by 5 convolution, so you are going to get 8 by 8. Why? Because 12 minus 5, because 5 is the so 5 by 5 is the size of that window, that means horizontally it's fine, vertically 5. So let's say that if I just take it say horizontally, then 12 minus 5, and then you add 1. Why? Because you are going to move it by 1. So essentially you are going to get 8. So 12 minus 5 plus 1 is equal to 8 without padding. So having understood this approach, when you are going to do the convolution, now we are ready to get into more details about say depth-wise separable convolution. So first let's understand a little more aspects of convolution. So let us say that you have this diagram which is shown here. So you have been given this 12 by 12 uh, 12 by 12 image, and here it's an RGB, that's why here shown it is 3 channel or depth is 3. So you are having this kernel which is 5 by 5 and then 3. So in the end you are going to get it by it as 1. So let's understand this. So convolution kernel has 3 channels. Why? Because image has 3 channel. So we are going to understand, or we are understanding the convolution with 5 by 5 kernel. So convolution kernel has 3 channels because image has 3 channels. So actual multiplications that are carried out are 5 by 5 into 3. Why? Because now here I am showing you the 3. So essentially it's a 75 multiplication. I just mentioned to you on the previous slide that it's a 25 because you are talking about the simple width and height. That means you are not considering at that particular time. I was just explaining to you without this RGB. So that means now when you have these 3 channels, so your multiplications are going to be 75 for every kernel movement. So that means it's a scalar matrix multiplication on every 25 pixels outputting one number. That means after going through 5 by 5 into 3, that means this 5 by 5 into 3 kernel, the 12 by 12, 12 cross 12 by 3 image will become 8 cross 8 by 1. So that is very important. So convolution with 5 by 5 kernel, when you have an image which is having 3 channels, so essentially you are going to get 8 by 8, 8 cross 8 by 1 image, or 8 by 8 output will be 8 by 8 cross 1. So now you want to increase the number of channels. So how to increase the number of channels in an output image? So you should create a 256 kernels. So create 256 kernels to create 256 8 by 8 cross 1 images. And then once you have created this, you should stack them together as shown in this diagram. So you can see now here 12 by 12, 12 cross 12 by cross 3. Then you convolve it with 5 by 5 cross 3, and then you are going to get 8 cross 8 by 256. So how you achieve that? So you create 256 kernels, and that way you are going to create 256 8 cross 8 cross 1 images. So essentially let's understand it now. So you basically have 12 cross 12 into 3 by 3, and then you are going to convolve it with 5 by 5 cross 3 cross 256. So that's what I told, we are going to create such 256 kernels. So then it's going to give you 8 cross 8 by 256. Why? Because 8 cross 8 cross 1. So essentially it's 8 cross 8 by 256. So where this 5 cross 5 cross 3 cross 256 are height. That means this 5 is a height of kernel. 5 is again a width of kernel. That means 5 cross 5 is a height and width of kernel. Then 3 is the input channel and 256 is the output channel of kernel. So I hope this, where I am hovering this pointer, it should be clear now. So that means you are given 12 cross 12 cross 3 as an input image, then you are convolving it with 5 cross 5, and then you create 256 kernels. So you are essentially going to get 8 cross 8 by 256 such things, which essentially are stacked. Okay, and that's what this diagram is showing you. So having understood this convolution, that means the not the only the plain convolution, but you are talking about increasing the number of channels in the output image. So having understood this approach, so we are now ready to get into the depth-wise separable convolution. So before we get into this depth-wise, I would like to put a note. So what is that note? So note about increased number of channel. So it's not a matrix multiplication. So now I hope that's clear, and I was trying to emphasize that window movement and all that. So it's not a matrix multiplication. Then it's not multiplying complete image by the kernel, but you move the kernel through every part of the image and multiply small parts of it separately. So essentially it's a convolution process. Now let's understand the depth-wise. Having understood this approach about the convolution and then creating the more channels, now we are ready, or we will understand the depth-wise separable convolution. So when we talk about depth-wise separable convolution, which basically separates the process into two parts. So what is that two parts? One is a depth-wise convolution and another is a point-wise convolution. So let's try to understand the depth-wise convolution approach. So when we talk about depth-wise convolution approach, you convolve the input image without changing the depth. So here you are not changing the depth, because in my previous video or previous slide, rather in the previous slide, I mentioned about increasing the number of channels. But here in this diagram, I didn't change the number of channel. What I am doing is, you are given this 12 cross 12 cross 3, then you convolve with 5 cross 5, then obviously it's like each shown, that means it's essentially it's a 5 cross 5 by 1 by 1 by 1, that means we are talking about that. So you convolve input image without changing the depth, and then you are going to get the output. So let's understand now. So you convolve input image without changing the depth. So essentially there are three kernels. So you, that's why in this diagram you will see 5 cross 5 cross 1. Once again it's shown 5 cross 5 cross 1, and then again 5 cross 5 cross 1. So three kernels of 5 cross 5 cross 1 are used for convolution. Then each 5 cross 5 cross 1 kernel iterates one channel of the image. You get, and because of that you get the scalar product of every 25 pixels group. So essentially it's a 25 pixel group, you, and because of that you get 8 cross 8 image. So you stack these images together, and that's why you create 8 cross 8 cross 3 image. So that's what this diagram is showing. So essentially now we are talking about the depth wise. Why? Because here you are having a kernel which is of 5 by 5 cross 5 cross 1, and that there are three such kernels. So that's what important is, you are doing the depth wise convolution. So that means the input image, which is essentially of say 12 cross 12 by 3. So these three kernels of 5 cross 5 cross 1 are used, and each 5 cross 5 cross 1 kernel iterates one channel of the image, and because of that you get, obviously it's a scalar product, you get that scalar output of every 25 pixel group, giving you a 8 cross 8 cross 1, and that's what is shown, and then you stack them together, and you basically get a 8 cross 8 cross 3. So having understood this, so we will understand more about this detail. So now we will understand the point-wise convolution approach. So this depth-wise convolution essentially transform 12 cross 12 cross 3 image to 8 cross 8 cross 3 image, but number of channels are were 3 only. Now you need to increase the number of channels, and that's where the point-wise convolution approach comes into picture. So to increase the number of channels, so please understand this is a very important point. So to increase the number of channels of each image, we are going to make use of 1 cross 1 kernel. So essentially this is called as point-wise convolution, and that's what. So we use 1 cross 1, that means it's a point-wise convolution, and then this 1 cross 1 kernel iterates through every single point. Then 1 cross 1 kernel has a depth of many channels the input image has. So that means here, for example, here it is 3. So you iterate 1 cross 1 cross 3 through the 8 cross 8 cross 3, because 8 cross 8 cross 3 is the output of the depth wise convolution. Then there is a point wise convolution. So you iterate this 1 cross 1 cross 3 kernel through 8 cross 8 cross 3 image to get 8 cross 8 cross 1 image. So this is essentially the point wise convolution. So please understand it. Why do you require it? We will obviously understand it little later. But what we currently have done is, there is a depth-wise convolution which transforms the image into 8 cross 8 cross 3. So that 8 cross 8 cross 3 was given as an input to point-wise convolution. In the point-wise convolution, we made use of 1 cross 1 kernel which iterates to every single point. Then 1 cross 1 kernel has a depth of as many channels the input has, that means here it is 3. So essentially because of that iteration, that means when you iterate 1 cross 1 cross 3 kernel through the 8 cross 8 cross 3 image, you get a 8 cross 8 cross 1. So that means now a pointwise convolution approach, we will understand it more now. So now you create 256 such kernels. That means you are now going to create 256 1 cross 1 cross 3 kernels that are going to output a 8 cross 8 cross 1 image to get a final image of 8 cross 8 cross 8 cross 256. That means that's what this diagram is showing. So now you essentially are given this 8 cross 8 cross 3. Then you basically are going to convolve 1 cross 1 cross 3 kernels, and you create 256 such. So because of that you get 8 cross 8, and then the depth or 256 channels are there. So that's what basically we have done. What we have done, so we separated the convolution into two. That means depth-wise convolution and point-wise convolution. That means the normal convolution we could never do that, but when it comes to this depth-wise separable convolution, we actually have done this solution, or we actually have done it. That means now you have first step as a depth wise, and then you have the second one as a point wise. So that means now your original convolution was like this: 12 cross 12 cross 3, and then you have you are given 5 cross 5 cross 3, and then cross 256, and that used to give you 8 cross 8 cross 256. But you achieved the same thing by doing the depth wise separable convolution: 12 cross 12 cross 3, then 5 cross 5 cross 1 cross 1. So this is very important: 5 cross 5 cross 1, then 1 cross 1, and then here you have 1 cross 1. This is that pointwise convolution. That's why you will see small arrow is shown here. So that means this is the depth-wise convolution. This is the first step. That means input is 12 cross 12 cross 3. Then you convolve 5 cross 5 cross 1, 5 cross 5 cross 1 cross 1. So you convolve that, and then you have this pointwise convolution, and because of that you get 8 cross 8 cross 256. So you will see in the original convolution output and the depth-wise separable convolution output are the same, and we achieved that doing the two things. That means, or you separated into two by using depth-wise and point-wise convolution. So having understood this depth-wise separable convolution, now we would like to understand why I am doing so many things, or what is the need. Because at times it is at times you may find it, okay, this is difficult for me to understand, but what is the gain, or what is the mathematical thing, or what do I achieve? Because otherwise the convolution is a very computationally intensive expensive or computationally intensive approach, or intensive calculations needs to be done. It's a computationally intensive thing. Then what is the purpose that I am doing this depth-wise separable convolution? So we will carry out multiplications, and we will understand the multiplications for normal convolutions, and then we will understand the multiplications for depth-wise separable convolution. So when we talk about the convolution, that is normal convolution, that is without depth wise. So there are 256 5 cross 5 cross 3 kernels that move 8 by 8 8 cross 8 times. So that means you basically get 256 into 3 into, yes, this will do multiplication. So 256 into 3 into 5 into 5 into 8 into 8. So essentially you get so many multiplications will be done as part of that. So you will understand that if you have a 256 channels, then when you use the normal convolution, this is a very computationally intensive thing. That means you have to do so much of multiplication to achieve to get the result. Now let's see the depth-wise convolution. So let us say that I abbreviate it is by decon. So decon means there are three 5 cross 5 cross 1 kernels that move 8 cross 8 times. So essentially you get 3 into 5 into 5 into 8 into 8. So which is essentially 4800 multiplication. That means the step 1, which is a depth-wise convolution, basically can be done in 4800 multiplication. Then you do the point-wise convolution, which is a step 2. So point-wise convolution, we are going to create 256 channel. So there are 256 1 cross 1 cross 3 kernels which move 8 by 8 times. So that means you get 256 into 1 into 1 into 3 into 8 into 8, which is essentially 49152 multiplication. So now you do the sum. So you add for 4800 plus 49152. So that means the sum total of this is just 53,952 multiplication. So roughly 54,000 multiplication, and now you see how many multiplications one needs to do if you are doing the normal convolution. So that means it's a very less number, or a very less number compared to the normal convolution. So that justifies why people use depth-wise separable convolutions as part of deep learning. When we talk about this activity, that means when I want to use this, when I want to carry out the convolution, and we essentially deal with the separable convolution. So that means now how computational power is saved. So that means in the normal convolution, transforming the image 256 times happens. That means every transformation uses 5 cross 5 cross 3 into 8 into 8, that is 4800 multiplication. So that's what I told. That means transforming the image 256 times. However, in the separable convolution, you transform the image only once, and that's what is the depth-wise convolution, which is a part 1 or a step 1. Then you take the transform image and elongate it to the 250. Sorry, it's a 256 channel. Six is missing here. So it's a 256 channels. So without having to transform the image over and over again. So essentially you save the computational power. So you see it's a pretty huge gap that typically one achieves by doing the computational. That means you achieve by making use of depth-wise separable convolution. That means two steps. That is depth-wise convolution followed by the point-wise convolution. So that's a very important thing in the separable convolution, and that's why in literature or in practicals we make use of separable convolution. And we will see this in the further videos where we need to make use of such depth-wise separable convolution. So some more information about say about one cross one kernel. So now I was just mentioning to you one cross one kernel. So essentially you can have n one cross one into m kernels. That means you can have n is the number of output channels. So that means you can have 256 one cross one, and then and m is the number of input channel. So like we were having 256 and then 3. So like generally you can have n 1 cross 1 cross m kernels which can be used outside of separable convolution. That means you can use it outside of even the separable convolution. Then a 1 cross 1 kernel is used typically to increase or reduce the depth of an image. That means you essentially balance out. So if there are if convolution has too many or too little channels, then typically in reality people add 1 cross 1 kernel and it can help you balance it out. That's added information. So what typically people will do? So typically after every layer, activation layer are applied. Like for example, when we will see further videos, you will see this. So typically after layer, activation layers are used, and that activation layer can be say ReLU, softmax, like that. So activation layer is basically when we talk about this activation layer. So as we know ReLU. So for example, so activation layers are non-linear, like unlike convolution layers. Okay, so non-linear. What is the issue with the non-linear? Because if I tend to use activation layer, the non-linear layer expand possibilities for the model. So that typically people will make use of. So it makes the deep network better than the wide network. So what people will do now is people apply a 1 cross 1 kernel and add an activation layer after that, so that non-linear layers are increased without significantly increasing the number of parameters and computation. So this information which I am just giving it to, it's like an additional piece of information. It is not like you have to mandatorily know that, but that's a added advantages, and that typically people will make use of this 1 cross 1 kernel, and you add that. So you apply 1 cross 1 kernel and add an activation layer after that. Okay, so that non-linear layers are increased without significantly increasing the number of parameters and computations. These are some of the tricks that typically people do as part of carrying out the various activities. So another, just a quick note. So the depth-wise separable convolution reduces number of parameters in convolution. So that's obviously is now very clear to you, and that's what that's the reason I was mentioning to you about 1 cross 1 kernel also. So that means if your overall network, what you are trying to define, is very small or is small, then there will be too few parameters and network might fail to learn properly during the training. So this is just a additional piece of information. So when you are trying to make use of this depth-wise separable convolution, we need to ensure that you use it judiciously, and you use it for a significant size network and not on a very small network. So I hope you basically have liked this video, where we essentially talked about depth-wise separable convolution, and where we understood the normal convolution, and then we went and understood depth-wise convolution, where we understood the that means depth-wise separable convolution, where we essentially talked about depth-wise convolution and point-wise convolution, and then we showed why this mathematically, or by doing the computations, we showed that depth-wise computation takes significant lesser multiplications than the normal convolution. So that's it as part of this video. Thank you. Hello friends, myself Shri Rankorde. Welcome to Deep Learning tutorial series. In this video, we are going to understand a fairly advanced model which is called as exception with depth-wise separable convolution. In our earlier video, we have understood depth-wise convolution, we have understood point-wise convolution. So in a way, we have understood depth-wise separable convolution. So that essentially was sort of a background preparation before we consider this topic, which is exception. So let's get into the details now. So when we talk about exception, it's a model which has been given by Google. So when we talk about exception, why such a name is given, we will understand it little later. But essentially we are talking about exception, that means deep learning with depth-wise separable convolution. And it's part of one of the interesting paper which is given here as part of the URL. So this is that openaccess.thecvf.com, and then you can find this paper which is from Cholet exception deep learning.pdf. So this is one of the interesting thing which has been provided by Google. So when we talk about this exception, let's understand now this modified depth-wise separable. So when we talk about this modified depth-wise separable, essentially we are talking about exception. So when we are habituated to use, say, point-wise convolution after depth-wise convolution. But here I have mentioned to you as modified depth-wise separable. That means now you are going to have a little different thing or a modification, and there that modification is now you have a point-wise convolution which is followed by the depth-wise convolution. Because in my earlier video I have mentioned to you that as part of depth-wise separable convolution, we were having the depth-wise convolution followed by the point-wise, but here it's a modification or it's a modified version. So when we talk about exception, so essentially when we talk about exception, it's basically it's a modified depth-wise separable. So that means you have a point-wise convolution followed by the depth-wise convolution, and here also you can see in the diagram or in this picture you can see this. So there is a pointwise convolution, say you have 1 cross 1, and then you can have this which was explained to you earlier. So the same thing here, you have this point 1 cross 1, and then you can have such sequence of that, and then you basically have this depthwise convolution, and here you have this n cross n, which may be 5 cross 5 or 3 cross 3 or whatever depending on your need. So that's essentially at the top level when we talk about the exception. So why that name is given as exception? Essentially it's an extreme version of inception. So there was a model which was given by Google, again it's given by Google, and it was called as inception, which were having various versions. So v3 is one of the popular version. So this modification was inspired, whatever the modification that I just explained to you, this modification is inspired by the inception v3 which was given by Google. So here we do 1 cross 1 convolution is done as the first step, and then you can have the n cross n, that means you will have 5 cross 5 or 3 cross 3 convolutions. So that means you perform 1 cross 1 convolution first, then channel wise spatial convolution. So as part of stack setting, that means typically when you use the TensorFlow, only small differences appear at the beginning and at the end of the all change inception module. So that's an information rather I am sharing to you. So and then there is no intermediate ReLU or a sort of an activation where there is a non-linearity. So there is no intermediate ReLU, that means ReLU non-linearity compared to the inception, and which basically helps to get a highest accuracy. So here there are two things to learn. One is the overall structure of exception is inspired by inception. So we don't need to understand really inception in detail, because this is what the thing is. Because if you are able to understand the depth-wise separable convolution, then that is good enough for us to understand what exactly is happening in exception. So exception is, though it is inspired by inception, here you have the point-wise convolution, and then there is a depth-wise convolution. So that's what at the top level. Then when you are going to implement it, that means when you are going to make use of the TensorFlow libraries, then typically it is noticed that only small differences appear at the beginning and at the end of the chain inception model. So it's an input from the inception. Okay, and when we talk about exception, so there is no intermediate ReLU non-linearity has been added. So when it comes to the inception, obviously they have made use of ReLU non-linearity and all that, but in exception module they didn't use that, and because of that you can see in this diagram there is a highest accuracy, and that's what is the literature says. So here you can see there is a on the database which is say ImageNet. So in that you can see against the gradient descent steps, you can see there is, if there is no intermediate activation, then the accuracy is better, and if there are intermediate ReLUs or there is any other ELU, then obviously it is accuracy is less. So that's again an advantage when we are trying to make use of exception over say the earlier things like say inception. Okay, so the overall structure of exception is looks something like this, and this is available in this paper which I just given you once again, which is the openaccess.thecvf.com, and you can find this structure. Now in this structure, essentially there are three parts, like one is an entry flow, then the middle flow, and then the exit flow. So we will understand this at a simple level or at the smaller level about this exception in the further videos. But the point is that it's going to work on say 299 cross 299, and then obviously 3 is that for RGB, but it's going to work on this 299 cross 299 input image, and then it also makes use of the skip connection. So now let's try to quickly take a look at this structure. So these separable convolutions are placed throughout the architecture. So you can see where I am hovering the cursor or the pointer, you can see there is a separable convolution, there is a separable. So that means there are such separable convolutions are placed throughout this exception net architecture. Apart from that, what we have learned earlier, like the skip connections or the residual block, that means the ResNet that we have studied. So again, this is inspired from that also. So here the skip connections are placed for all the flows. So you can see here these are the skip connections. You can see this, there is a path, and that are essentially which is having the skip connections, and which is part of entry flow, middle flow, and then the exit flow. So now when we talk about such a structure which is the exception structure, then the validation accuracy is higher with the skip connection. That means you can have an exception model without skip connection, and then you can have the exception model with the skip connection. So literature says that against the gradient descent steps, the exception which is shown here in the red, uh, that means this is with residual or with skip connection, it is giving, red is giving better accuracy for the ImageNet database compared to the exception without skip connection. Apart from that, in the literature you can find the accuracy. So for say for example the VGG16, which we have basically in the earlier videos we have seen VGG16, which was the older or the earlier versions or the earlier model. So which gives say for example the top one accuracy is 0.715, then compared to that ResNet was giving 0.77, and then exception is giving you close to 0.8 or say 0.79. So that's again a important thing with respect to the accuracy, which is much higher in exception net over the other versions or other models. So this was in general the overview of the exception, which essentially is inspired by the depth-wise separable convolution, and obviously it is inspired by inception net and all that, so that's fine. But at the fundamental level you will have the depth-wise separable convolution, which essentially is a depth-wise convolution and the point-wise convolution, and here you carry out the modification. So that's about this video about the exception module or exception model. Thank you.
Hello friends, myself Shriram Korde. Welcome to Deep Learning tutorial series. In this video, we are going to take a look at demonstration of something which we call it as mini exception. Why we are going to do like this? Because up to now we have studied overview of exception, and as part of studying exception, we have seen what is depth-wise separable convolution. So that we have seen. Now in this video, we will concentrate on understanding the concept behind exception. The reason being because there is a API support in Keras library. However, that doesn't help us to understand the intricacies of exception. So that's why we will try to form a model and we will understand how this works. So let's now go to the demo, because I can always put a code on slide, but that doesn't help. So we will go to the code and we will understand it one by one, and whenever required we will take a proper support. So now here we have imported TensorFlow, and rather we have from TensorFlow we have imported Keras, and then we have imported layer. So let me just run these two things and then I can explain to you the code. Now we have going to define a model. Now let's understand it. Now when we talk about exception net, then essentially we will be making use of the concept that we have studied earlier as part of RESTnet, and that is skip connection. And even in the overview of exception net video, I have explained to you about the usage of skip net. So skip connections essentially. So that we are going to do. Then on the lines of RESTnet video, this particular code is basically built. Now the important thing here is that we are going to write a loop, and that loop essentially will take care of the filters that we would like to be given, and so that we create layers, because otherwise writing the code one below another will become a huge code. However, that can be optimized by writing a loop. So let's now understand this approach. So first thing is that we are going to make use of keras.input, and we have seen it earlier, and to that we basically specify the shape. So here it is, the shape is 180 by 180, that is the pixel or image size, and then it's the 3, that is 3 means RGB, that is channels, that is what we are giving. Then we are going to have a rescaling. So that means whatever the pixel values are there, I am going to do the rescaling by 255, so that the values are between 0 and 1. Then I make use of a convolutional 2D. Now here you can see we provide the filter size, that is 32. Then we provide the kernel size as 5 by 5, and in my depth-wise video, that means depth-wise separable convolution, I have taken the example of kernel size 5. So I hope now you will be able to correlate it when you go through that video coupled to this demo video. So here the kernel size is 5, and here we say that use of bias is false. That means we don't want to make use of any bias. So essentially it's like bias that we typically provide as part of the perceptron. So that is, again, this is something at the very initial level or at the basic videos we have covered this bias. So essentially it's a bias vector. So right now we don't want it. So that means now we have layers rescaled, that means layers dot rescaling. So we carry out the rescaling of the input, and then we have the convolutional layer. So once we have this, then we have written a loop. So here you can see there is a loop, and the loop essentially can be changed. So right now I am just putting it in only one number, that is 32, and let's see how it works. Then I am saving this x, that means whatever the x I have, the input after rescaling and all that, in the residual variable. So we do that, because I explained to you in the overview of exception net, we would be using skip connection. So that is what this plays the role. Now then comes the batch normalization. Now what is batch normalization? I will explain to you little later, but essentially it's one of the training approach. So let's first concentrate on this code, and then we will go through the batch normalization. So here you can see x is equal to layers dot batch normalization, and then you provide the input. That means after doing the training or sort of normalization, rather it's used as part of training. It's used as part of training. So here you are going to normalize the input. So we will understand batch normalization little later. Then you have an activation layer where you basically tell that you want to introduce a non-linearity, and by the way of making it ReLU, so you essentially are adding a non-linearity. Then we are going to make use of a separable convolution, which is 2D. Here you provide the size, that means the size is now 32. So initially it is 32, then we will change it little later. And then this kernel size is 3 by 3. So many times we use it as a kernel or filter or whatever. So here we are giving 3. So if I just want to tell you the proper details of the separable 2D, because we have seen how separable convolution works as part of depth-wise separable convolution. So we have seen that in our earlier videos. So let's try to understand the parameters here. So let me just show you this. So here you can see this is the first parameter is a filter, then the kernel size. The second parameter is kernel size. So you don't need to give like whatever. You don't need to give the complete this one. You can always provide it at a single value, because that is what we are planning to use here, that is 3 by 3. And then you have this padding which is same, and that means you use the same padding on both the sides, and that is what is the default behavior. And then you don't want to make use of a bias vector. So let's see this properly. So here we will go through this documentation properly. So separable convolution consists of first performing depth-wise spatial convolution followed by the point-wise. Okay, so that is what, because we are currently doing this approach. Okay, so that's why I told you we are not directly using ExceptionNet API, but we are going to mimic, or we are going to replicate that approach. Okay, so here that is what basically the separable convolutions can be understood as a way to factorize. So we have seen this in the theory. So here you can see this is a filter, so which is an integer number. Then kernel size is a tuple, is an integer or a tuple, and it can be a single integer to specify the same value for all spatial dimensions. Okay. Then strides, right now we are not using, but strides is the way in which you move your kernel. Okay. So then padding is same. That means there is no padding. Otherwise, same results in padding with 0 evenly to the left and right or up and down. Okay. And then we are not using the bias. Otherwise, its default value is, we can see this. So default value otherwise is true. So we can see this here. So bias here is true. Default value is true. So you don't want to use the bias. Okay. So this is the layer. That means this is the first this one first block, I will say, group rather. And then once again you carry your batch normalization, you do the activation, then once again you have this second group, then you have the max pooling layer. So I have explained to you as part of ResNet video what is pooling and what is max pooling and all that. So you can take a look at that. Right now we will not get into the pooling, but it was explained to you in detail with theory video. So we are going to use this max pooling, and then we are going to make use of this con 2D, where you provide the size, then that is the pointwise convolution, which is 1, and then strides padding same. Then you don't want to use the bias, and it is multiplied by residual, or rather there is a residual is the input. Then you add, that means you add the input as well as x, as well as the that means the processed x, which is an input, and then there is a residual which we have stored earlier. Then you carry out the global average pooling. So again, this was explained to you as part of pooling when we tackled ResNet, so residual net, where we concentrated also on pooling. So we make use of this global average pooling, and I explained to you when do you use global average pooling and all that. Then you have a dropout layer, so that you don't have the issue of overfitting or underfitting. Then you have the last layer, which is a dense layer, so that you can decide, it's a one layer, whether you want to what is the final result. Now to this model, that means this is such a big model. Now to this model we will obviously give our standard data set that we are giving, which is of dogs and cat, and that's why we have used here one neuron. That means you can make a decision whether it is a dog or a cat. So this model is basically done. So let me just execute these, or let me just, and then you can see I have just given this for size in. Now here it's a list. So I'm just giving only one. So you can, and I'll tell you why I'm doing like this. Then you have found this global average x, then output, and then the model. So model is input and output, that is keras dot model. Now we will be plotting this, how does it look, and that's the reason I have made it. So you can see this is an input layer. So that is the model that I was trying to show you. So let me just
make it little small so that we are able to. So you can see this is an input layer, then there is a rescaling, so that was explained to you in the code just now. Then we have a convolutional con 2D, that means input con 2D, and then we have saved it in the residual. So and then there is a batch normalization. So let me just show you this. So this is the batch normalization. So this is the batch normalization, then activation, then separable con 2D. So all these things essentially will be shown in that diagram, and that is the reason I wanted to show it directly instead of putting it on the slide, because it becomes difficult to explain this code. So then there is a batch normalization, then you have activation layer, which is essentially a ReLU, then you have this separable con 2D. So that is what this separable con 2D, that is a depth-wise, this is a depth-wise convolution, this is a depth-wise convolution, and then this is a final point-wise convolution, that is what it is, and then you add. So that is the structure. Now this is the inception structure essentially, because we want to tell the concept. Now when we do the exception, first we do in point wise and then followed by the depth wise. So there is no change as such, and I explained to you in the theory video. So we do this like you have this rescaling, then con 2D, then batch normalization, activation separable con 2D, then you have this batch once again batch normalization, activation separable, then you have this max pooling, then you add. Then you have this global average pooling, then you have a dropout layer and dense. Now that is, and then now you can see this is that skip layer. So here we have this con 2D, and then that is what I was explaining to you here. So this is the con 2D which was in the residual, and then you directly give the add, you give it to the add. So that is what here you can see, this is that, and then you provide it to the add, and then you have this global average pooling. Now the reason I have shown you this code with only 32 is because this code otherwise is a difficult one to understand just like that. So what now I will do is I will basically make it here 64, and once again I will show you this. So let me just run this. So you can see the size I am going to give, it's going to get executed 2 times now, because earlier it executed, or rather it was compiled only once. Now I am going to compile this program, rather it will be because there is a loop. So that means now this whole block up to this that means this particular from here onwards, that means residual till this portion which I am currently hovering. So this portion will be appended once again for 64, then it can be appended for 128 to 56 like that if I have that in the array, that is in this list. So currently there are only 2. So let me just have this global average pooling, then dense, and then the model. Now we will once again plot this. So if you plot it now, you can see this. So this there is a one add. First thing is this is a add 1 2. That is the first add. And once again you have the same thing getting added, like apart from the residual. So this is what now. So this essentially is the input now. So you can see this is like a residual. Then all that batch normalization, activation, separable con 2D, and once again batch normalization, activum separable to the, then max pooling, and then second add. So this is one add 1 2 was the first one, add 1 3 is the second one. Then you have global average pooling, dropout, and then the dense. So that is what the final dense layer is. So that means now if I do it 2 times, that means this filter, then I can have this 2 times. So I can keep on doing it like this. So let me just now, I can always increase it to 1024 and all that. Okay, so that is not an issue. So I can always have 5 and 2 comma 1024 and all that. So here I can have 1024 and all that. Okay, so that is the standard way, and we have done this earlier. Only thing is that we didn't write it in a loop because it was only done in that means in sequence. But here it's a deep network, that's why we have to do it in a loop. That's the only reason. Otherwise there is no other reason that we did it in loop. Okay, so let me just now show it. So now you can see 32, 64, 128, 256 and 5112. Then we will have this global average pooling, dropout, dense, and then we form the model. Now once again we will plot this. So now it takes little more time. So you have this input layer, then rescaling, then the first convolution, then your this one starts. That means now your batch normalization, then activation, separable, con 2D, then once again batch normalization, activation, separable, then max pooling. That means 2 times those groups, then max pooling, then add. So here you can see this is 1 4. It takes the running number. So add 1 4, then you will have second one, add 1 5, it will be there. So sorry, add 1 6 is there. Then because earlier number was used, so then you will have once again add 1 7, and then third one, that means you can see then add 1 8. So let's do it one by one. Okay, so let me take it properly. So let me use this. Okay. So now input, then I'm just scrolling it down. So input, then the first add 1 4, okay, then there will be add 1 5, yeah, so there is add 1 5, then second one, that means then third one, and then there is a fourth one, and then there will be fifth one. Why it is fifth? Let's see the reason. So here you can see 32, 64, 128, 256, and 512. So there are 5 things. That's why you can see this 5 times it is done. Now if you are interested in getting the details, I shall explain to you in the ResNet. So same way you can do, and you can just enable the show shape option of this. So you can see this with this size dimension, you can see the diagram. You can see that it starts with 180 cross 180 image, then you do the rescaling, and then you have this filter. So you can see this becomes that means here you have this 176, then that way it will, then 32, then it will become 64. Yeah, so it is 64, then 64, 64, then you will have 128, then 128, then 256, and then 512. Last one is 512. So that way you can take a look at this complete diagram. So that is what this pictorially it looks, the code that I explained to you. Then we can always take a look at summary. So let me now increase this. Okay. So we can take a look at the summary of this exception. Essentially, it's an inception module, but I just wanted to explain you the concept. So it's like a mini exception. So now this is the model, and then model is like you have the input layer, then rescaling, and then all those things like con 2D, then batch normalization, then activation, then separable con. So this is like the first group. Then once again batch normalization activation second time, that means 2 times separable con 2 we do. That is what I explained to you in the diagram also, or in the image just few minutes back. Then you have this max pooling layer, then you have this con 2D, which is essentially the so this is that max pooling, then con 2D. So like that, then add 1 4. So like that you will have so many things in the end. Like that we will have. Then there is a before global average pooling. We will have this last layer, and then where you carry out the point wise this one convolution. So that is what we do here as part of this. So this is that point wise convolution. So that's essentially this model dot summary. So you can always take a look at this because it is available. I mean to say, you can, once you see this code you will understand it. Okay, now comes the giving the data. So here I am just doing the same job which I have done earlier multiple times. So I am just going to take the pets database, that is pets images, and I have created a folder where I have selected a few dogs, cats and dogs small. That means there are 100 images like that, and then there are 50 images for 50 images of each category. That means 50 for dog and 50 for cat, like that for testing and evaluation. That means for mainly for evaluation. So let me just go to the code, and because I'm not executing this code, because this already I have created this subset and I already copied the file. So this is the same code which was explained to you earlier. So we will now skip this portion, it's not needed. Then we create this train dataset directory where you have the batch size of 32, and then validation dataset, and then the test dataset. So you can see this, there are 200 files, that means 100 each of a class. That means that's why there are two classes, cats and dog. Then we compile our model, So here you can see this, there are 100 files for evaluation as well as 100 files for testing, that is validation and testing, 100 files, 50 each. Then I can always do the fitment. So I'm just giving it for the sake of right now, so because it takes time otherwise. So epochs are one, just epochs, only one epoch, otherwise you should have large number of epochs, at least 10 or to 10 to 100 you should have. So you can say this accuracy is only 50%. So that to just to demo you. Okay, now we can understand the batch normalization, because I didn't explain to you what is batch normalization. So we need to now understand what is batch normalization and why I am doing that, and what is the advantage of doing batch normalization. So let's now go to the presentation, and let me explain to you what is batch normalization. Okay. So what is a batch normalization? So essentially it's a technique for training very deep neural networks. And that's why I first shown you the neural network or the deep neural network, and I have told you like we have we created it for 5 times. That means 10 times. That means the batch normalization essentially was invoked 10 times because we were having 5 ads. I explained to you that a few minutes back. So essentially it's a technique for training very deep neural network. That's a very important point. And why do you require that, or what does it do? So it standardizes the inputs to a layer for each mini batch. So that means we are doing batch by batch we were doing, and that's what I explained to you just now. Like we were giving the batch of 32, and that is what I explained to you here. You can see this. So this was the, so let me just show you this this one. So you see this train data set and validation. So batch size was mentioned as 32, and that is what we gave here, train data set. Okay, so which was essentially in a batch of 32, we were giving this 200 images in a batch of 32. So let's go here. So it standardizes the inputs to a layer for each mini batch. So because it's a 32, it's a much smaller size. So what is the effect of this? So it stabilizes the learning process. That is the first point. Second one is it reduces, or it significantly reduces, I will say, it significantly reduces the number of training epochs required to train the deep network. So that's a very advantage or a very important point. So because otherwise why do I require this? Because it sounds little difficult for someone to understand why do you require a batch normalization. So it is going to significantly reduce the number of training epochs required to train the deep network. So that's what I told you, like you should have a epochs at least to 10 to 100, like otherwise in you have to have a large number of epochs like in a normal say without using this depth wise and point wise convolution. So that's a advantage when you and that's why you require batch normalization. So what is the overall algorithm? So algorithm is like it is implemented during training. So I just told you. Apart from that, it is used during evaluation. Why? Because I just shown you that, and once again probably I can you can go to the code and you can see this. So we were using it for training. Obviously, we just run for epoch, but we wanted to also check what is the validation accuracy. So that is what I told you, that accuracy. So that's what this validation data set was used. So this validation data set, that means which is essentially made up of 50 cat images and 50 dog images. So that's what I told you, like 100 images for validation, that means 50 each. So that essentially I just wanted to highlight. So it is implemented during training and oblique evaluation. Then it, what does it do? So essentially it calculates the mean and standard deviation of for each input variable to a layer per mini batch. So that means whatever the inputs are given, that means the input pixels are there or images are there, is going to calculate the mean and standard deviation. Then it uses these statistics to perform, that means after calculation of mean and standard deviation, it uses these statistics to perform the standardization. So how does it look? So it looks something like this. So you have this input values of x over a mini batch, say batch of b, say m values, say 32. Then parameters are there, say 2 parameters needs to be learned like gamma and beta. So you are going to get an output which is yi, which is denoted as b and y gamma or and then of xi, gamma and beta of xi. So here you see, that's what I told you, like you have this mu b, which is essentially the mean, and then standard deviation is a mini batch variance. So this is a mini batch mean, so essentially it's a mean, and so you can say this is the mean calculation and this is the variance calculation, and then you have this normalization. So this is that actually equation. That means you take the pixel value, you subtract this, you divide it by the sigma square, and there is a small constant which is just added for the numerical stability. And then finally you get yi, which is essentially gamma into xi plus beta, which is essentially given as b by gamma beta of xi, so which is scale and shift. Okay, so I'm not going into this algorithm because that's not the focus of this presentation. So essentially this is a support directly available in Keras. So, so now you can see this algorithm as such, there are a lot of computations that needs to be done. So now obviously when I'm giving you this presentation, then in that case you can see this, like multiple computations needs to be done. So obviously my training will get affected because it is going to it requires computation which are large in number now, or which is a significant computation. So what are the advantages? Let's see this now. So why you want to use batch normalization? Let's denote it by Bn. So one is, though I was telling you like you have to do a lot of computations and all that, and they are complex computations, like you have xi minus ub upon sigma square and then take a square root and all that. So these are all complicated or complex equations. So comparatively, so here, but still the training is faster. Why? Because the training iteration will be slower because of extra normalization. That is what I told you. During the forward pass and additional hyperparameters to train during backup. But because of this, it is going to converge quickly. So that's a very important point. So though it is, you require more computation, but because of this approach, converging becomes very quickly. So you may feel like you have to do a lot of computation, but those computation helps you to converge the algorithm quickly. That's a very important point. So first bullet is training is faster. Second is, like as we know, like it uses the deep neural network model uses a gradient descent algorithm. So this gradient essentially becomes smaller or they vanish, and I explained to you in earlier videos what is the vanishing gradient problems and all that. So gradient becomes small for deeper network. So here when it comes to batch normalization, higher learning rates can be used. So that's a very plus point. So because of that, the speed of the training increases. So that's a very important point, because now you can have higher learning rate. So there is a less chance of gradient becoming very small values or vanishing, and because of that you basically are going to get higher training increases. So speed of training increases. Then the third bullet or third point is, many times the weight initialization is difficult for deeper network. So this batch normalization essentially reduces the sensitivity to initial starting weights, because otherwise when you have deeper network, assigning the weights becomes difficult. So this reduces the sensitivity. That means now you can see this batch normalization, though the complex calculation needs to be performed, and obviously it is provided to your Keras support, but the advantages or the plus points are much more than the other approaches. So that's why people use batch normalization when we want to do the processing in batches or in small groups. So let's now go to the code. So let me take you to the code. Okay, so that's what I had shown you, like you can increase the epochs and then we can do. So let me just highlight to you important things here now. So what can happen is, now what can happen is, like I have given you the inputs, plain input, but I can always do a data augmentation. So what is a data augmentation? That means you transform the data or input and then you provide it and see how the model is behaving. So how can you do? So you can have a data augmentation, you make use of this keras.sequential, and then you do the random flip horizontally, then you carry out some rotation on data, then you can do the random zoom, and that such a data can be also be fed to this particular neural network model, which is essentially the sort of we are trying to understand a mini exception net. So that's the again just additional piece of information. So let me just summarize now. So as a part of this mini exception net, essentially the core thing is, here we do the depth-wise convolution, and then we have this point-wise convolution. That is what essentially we are doing here, and we are understanding this complete structure. So that way you see this, and then we have put it in a loop, and then we create a big deep network, and I have explained to you in this diagram. And then to understand this model, or to use this model, we have provided the cats and dog images, which we are using it even in our earlier videos. So I hope you like this demo. Thank you. Hello friends, welcome to Deep Learning Tutorial Series. Myself Shrirang Korde. Up to now we have seen exception net model, and in that we have understood the concept behind exception model. So in this video we will understand more about the exception model, and we will see how that model can be used, and then we will understand more about this model. Then apart from that, we will try to visualize the convex filters which are part of exception models. That means typically when you talk about extracting the features, then how this convex filters learn. So that is what we would like to understand. So let's get going. So this is the diagram which was shown to you earlier, where we have this exception model, and it is divided into three parts, that is entry flow, middle flow and exit flow. And as part of this model, the separable convolution are placed throughout the architecture, which was mentioned earlier, and then it makes use of the residual connections. That means the skip connections are placed for all the flows. Apart from that, this convolution essentially starts from 32 and then 64, then 128, like that till it goes to 2048. And then you basically have in between these separable convolutions, which is, and we have seen these in detail as part of depth-wise separable convolutions as well as the point-wise. So we have seen this overall structure earlier. Now, if I want to use this exception model, which is part of Keras library, then in that case, what I can do is I can have my own model. That means I can import exception, and then from there I can invoke this call, which is exception function, and then I can pass the image net, which otherwise will get downloaded, or I can pass it if I had downloaded it earlier. So this is a variable where I can initialize it, and initialize it to a wait file. Then I don't want to make use of the classifier, and that's why I will say include top is equal to false. Now the important thing here is there are going to be multiple layers. So let us say that if I give the name of a layer, and which we will see how to find it out. So suppose if this is the name of the layer, say block 3 underscore separable, that means sepcon1, then I am going to use this name, and then I give this name and make use of this function which is available to me as part of this model object, and I call this function get layer. So this get layer is going to give me the layer specific to this particular name, which is say block 3 underscore sepcon1. Now from where this name has come, so we will quickly take a look at the demo. Now once we have got this layer, then I can create my own object. Suppose if I name this object as a feature extractor, because I would like to see how this particular learning happens as part of this exception model, then I can have this, say name of the variable is feature underscore extractor, and then I essentially form this model, which is where I provide the input as well as the output, which is layer dot output. So model dot input and layer dot output essentially will be my feature extractor, and the reference for this slide or this particular information, especially this architecture, is in this openaccess.thecfe.com, and then this is the PDF link. So now we will try to see this exception model, and we will try to plot it, and we will understand more about it. So let me now take you to Jupyter notebook, and here I will first import TensorFlow. That means I will import Keras from TensorFlow. Then I am going to import exception. So that is what I have told you, that from Keras.application I am going to rely on exception module. Then I have this image file, which I have downloaded it, and it is an exception weights underscore TF, that means TensorFlow dimension ordering TF kernels no top. So that's what we have given, include no top is equal to false in the code that was shown to you in the slide. So then we will have this model which is exception dot exception. So this capital exception is the function call, and here we pass the weight file, and I don't want this include top, and that's why you will see in this weights it says kernels under, that means tf underscore kernels underscore no top. So this no top is very important. Why? Because we are not including the no top. Now I can basically take a look at how this model looks. So I can just simply do model dot summary. Now you will see this, it has an input layer which then we will use this little later, but right now we are just forming the model. So as part of summary, you can see this is the input layer. Then block 1 underscore conv1, which is a convolutional 2D layer, and so you can see this is an input underscore 3. So these are all connections which are mentioned here. Then block underscore 1 underscore con1 underscore bn. That means it is there is a batch normalization, and I have explained to you what is batch normalization in detail in earlier videos. Then there is an activation layer, then there is a block con 2D, then there is a block normalization, then block 2 sep con 1 con 1, that is separable convolution, then again batch normalization. So like that you can see this summary is a pretty big summary. Okay, now in that you can see these are the names like block 2 underscore sep con 2, like that. So suppose if I go back to the slide, then I was saying block 3 underscore sep conv1. That means you can see this, there is a block 3, then block 3 sep, you can see this name block 3 sep conv1, which is essentially a separable convolution, and we would like to understand the features for that. So the point here is, when we go to the slide, so here you can see this is a layer name, and that's why this feature extractor output is essentially layers dot output. So layer dot output, so this is that layer. That means I am interested in this particular layer, which is block 3 underscore separable con. Otherwise I would have, otherwise we don't do it like this by layer, but typically it will be like models dot input and models dot output. So the point I'm just trying to make it is, we are using this model and understanding how the or visualizing what COMNET filters learn. So let's go to Jupyter. So this is the model dot summary. So you can give the other names also. This is just a block 3. Then there can be block other blocks like block 4 sep con 1. So we can give that name also. So that's okay. So like that you can see. So this is that big stuff. So it's a very big stuff which is model dot summary. So if I want to show you the diagram, or if I want to plot it, then I can simply uncomment these lines, and I will have a, so let me just uncomment these lines, and I will show save this model or this picture into this PNG file, which is exception view.png. So this is something similar which we have done earlier, where we make use of py dot as well as graphviz. So this was explained to you even in earlier videos. So now let it save this file, so which is exception view.png, and now you can see this is a pretty big file or a very detailed file. So let me just, yeah, so I can always I'm not sure whether, yeah, I think it's too bad to see it here. Okay, so let's go to the, so here you can see this is that input layer, then there is a con 2D which is exception model, and then you have batch normalization, then activation, then con 2D, then batch normalization, then activation, then there is a separable con, then this is that layer in between where you have the skip connections, which is a con 2D where you do the pointwise convolution and all that. Then here you can see on this left hand side there is the batch normalization, then activation, then separable con, then batch norm max pooling, and then you have the add. So like that you can see. So if I just take you to once again this slide, then this is that something. So con layer, then this con convolution, then this is that one by one, that is pointwise convolution, then this is that separable con ReLU, separable con max pooling, like that. So this is shown here in I mean to say in a very small font, but this is actually the big, this is that diagram which I am trying to show you here by plotting it. So if I just plot it with shapes, so suppose if I just plot it with shapes, and if I for the time being, let me just uh, comment out this line, and I will make shapes is equal to true, then you are going to get the shapes also. Yeah, so I think this is much more, it is little difficult to read now, but at least you will appreciate what I am trying to show you. Yeah, so here you can see this is an input layer, then block 1 2D, block 1 con. So let us go to the block 3, block 2, then block 3. Yeah, so this is that block 3, and this is a block 3 sep con 1. So that means I can so instead of doing it like this, because here you see all the shapes and all that, so let us say that I am not interested in shape because it is a very clumsy diagram or a very small diagram. So let's go to the block 3. Yeah, so block 3 separable convolution, so separable con 2D. So that is what I was trying to explain through the slide. So this is that separable con, and then here you can see these are the separable cons and all that. Okay, and then there is an add and all that. So all this add was there earlier. Here you can see these are the adds. So this is that block 1, block 2, block 3, like that. So this is a big diagram. You will have to do on your own and understand it to a certain extent, because otherwise it's a very big diagram. So that's what I wanted to highlight to you. So this is the way you typically look at the complete diagram, and it's a very big diagram. I'm keep on scrolling, and you will see it keeps on going on till finally you will have this. Let me show you the final one. Yeah. So here now this is that final, which is a block 14 sep con 2D and activation, and then there is a separable con 2D. So which maps to this final one where you have this separable con 2048. So if I basically enable the shape is equal to true, then you will see this filter, that is that shape which is essentially shapes is equal to true, that also can happen. So if I just copy this and add it here one more line, and here if I just view here with shapes, and let me just save this, run this. Yeah, so now it is very small in font, but you can see the final one goes to 2048. Yeah, so 1536, then 12048. So that is what I wanted to highlight to you, like this is that final block 14 subcon, and here you can see this is 2048. That is what. So that's essentially this particular activity where we understand how typically you basically can make use of this exception net model. Now what we will do is we will understand the other things, why are we doing this activity. So let's quickly do that now. So let me just hide this because it is little difficult for every time to scroll. Then even I will, for the time being, I will now comment out these lines. Similarly, I will comment out these lines. Okay, now we are going to, so let me comment out this line also. Okay, now we are well placed to handle the program. Okay, so that is what essentially we have done as part of this. So that means we have this architecture, and then we have made use of this exception model, and we are interested in how this particular thing with respect to visualizing how each layer or what is part of the learning. So now what I will do is in the next video we will understand the code where we will focus more on visualizations. Thank you. Hello friends, welcome to Deep Learning Tutorial Series. Myself Srirang Korde. So up to now we have seen how we can make use of exception model, and we have seen it by plotting the model also and understanding the overall architecture. And now we are interested in visualizing the convolute filter. So for that we would like to concentrate on a particular layer of the exception model, and we will see how typically the visualizations can be done. So this is the overall architecture and we have spoken about it earlier. Now we will concentrate on visualizing the convolute filters. So when we talk about the deep learning models, we essentially say that deep learning models are black boxes. So that means the learning representations, that means when you have these different layers by layer as part of this deep learning model, then those layers essentially learn. What do they learn? They learn the representation. So these learning representations are difficult to extract and present. When you make this statement is partially true for certain types of deep learning model, but when it comes to COMNET, it's not true. Why? Because there are ways to visualize COMNET filter. So there are multiple ways. So when we talk about this visualizing, or when we talk about understanding more about how this learning happens, so visualizing COMNET filters happens to be one of the technique, and it's a very interesting technique. So it's a technique which is useful for understanding precisely what visual pattern or concept each filter in a cognate is receptive to. That means you are trying to understand when you give this pattern, or when you when you have this as an input, then whether it is receptive or not. That means whether it is activating. That means the further layers should get activated. So that is what the focus is. That means it's a technique. So this visualization, so when we talk about this visualization, so this visualization is done with gradient ascent in the space, in the input space, because you are given the input. So this visualization is done with a gradient ascent. Now up to now we were used to word which is gradient descent. So what exactly we mean by that? So let's understand it. So that means now you are going to apply gradient descent to the value of the input image of a cognate so as to maximize the response of a specific filter. That means you start from a blank input image. So that means you start from a blank input image and then you apply gradient descent, and you basically try to see at which point or at where there is a maximum response of a specific filter. That means you are now ascending. That's why it is essentially it becomes a gradient ascent approach. So visualization is done with a gradient ascent in input space. That means you apply gradient descent to the value of input image so as to maximize the response of a specific filter. And when you say that you want to maximize, that means you start with a blank input image. So then you essentially get a resulting input image. So this resulting input image is one that is chosen that means that the chosen filter is maximally responsive to. That's why when you say that it's a maximally responsive, that means it has reached the peak, or that's why we call it as a gradient ascent. So when we talk about this visualization, so there are steps for visualization. So it is broadly divided into two steps. One is you have or you define a loss function which maximizes the value of a given filter in a given convolution layer. That means you choose a convolution layer, and that's what in my previous video I was telling you, like we are going to understand about exception net, and so we have defined a model which is exception net model, and then we provided a particular name of a layer and we were interested in that. So you define a loss function which is going to maximize the value of a given filter in a given convolution layer. That means you are going to tell which convolution layer you are interested in. Then second point is you have this method, that means you use the gradient descent to adjust the values of the input image so as to maximize this activation value. So essentially we are now talking about a gradient ascent. That means there are two things at the broad level. One is a loss function and another is a gradient ascent. That means in a way you are making use of gradient descent in that so that it maximizes the activation value. So now having laid out these steps for visualization, now what we can do is we will just quickly summarize the thing that was mentioned to you earlier. Like you have this exception model where you provide the weights and then you specify the layer, and then you form this object, or essentially which is a feature extractor, where your input obviously is a model dot input, but output is this particular layer where you are interested in. So you can change this layer name accordingly you can have the outputs, that means you can do the gate layer, and then you have this output is equal to layered out output you can always do. So this is the general way or a way to visualize the convolute filter or a starting activity as part of the visualizing the convolute filter. Now we are going to have a function which is going to compute the loss, and I just told you. So it takes two parameters, one is an image and another is a filter index. So you essentially because now you have this feature extractor which is a model, so or an object, so you pass this, that means it's a functor, so you pass the image to that and you get the activation, and then using this activation you basically get the filter activation, and then you calculate the mean using the TensorFlow's reduce mean function. So here what is important to understand is this loss will maximize simply the mean of the activation. So this is the mean of the activation of a specific filter in a target layer. That means you have specified the layer, say for example block 3 underscore step con 1. So this is your target layer and you are interested in the loss, that means the loss which will maximize the mean of the activation of a specific filter in a target layer. So that's the first function, which is compute loss. The second function where we have decorated it with tf dot function. So that means now the second function I have mentioned to you in the previous slide is a gradient ascent. So here you can see the name of the function is gradient ascent underscore step, which takes three parameters, that means image, then the index of the filter, and then the learning rate, because now we are talking about the learning rate which will be passed as part of this input. Then we are going to make use of this thing which is a gradient tape. So now let's quickly understand all these things as part of the this function which is the gradient ascent underscore step. So this gradient ascent underscore step computes the gradient of the loss, that means this is the loss function, compute loss I told you. So it computes the gradient of the loss above with regard to the input image. So what do you mean by gradient calculation? I will explain to you shortly, but for the time being just understand that this is going to compute the gradient of the loss which you computed with this function compute loss with regard to the input image, and then you update the image so as to move it towards a state which that will activate the target filter more strongly. So that is what I have tried to mention you as part of overview also. Now how do you achieve that? So for that in the TensorFlow there is a support that is provided as part of gradient tape. So the gradient tape is a hook. So it provides a hook. That means like you can put this hook and then use this hook. That means what it is going to do. So it gives the user control. To what? So it gives a user control to what that can be watched and what that cannot be watched. That means you are in a way it's like a monitor. So you are going to monitor or you are going to do a watching. So the gradient tape is like you are taping the activities. It's like you in the olden days there used to be a tape, magnetic tape, and then it used to record. So on the similar lines here it's going to do the watching or observation of that, and that's why this word gradient tape probably is used. So here tape dot watch is a way to do that. So this is going to record gradients. That means to record the gradients you need to make use of this function which is gradient tape dot watch. Then it can be used to write custom training loops also. Why? Because you can use this function and then you can write your own custom loops also. Then this gradient function is a very important thing. That means step dot gradient. So this probably should have been in a small case, not the first letter gradient capital is there, but it is a small case. So gradient function, this is going to compute the gradient using the operations recorded in the context of this step. So essentially as the name says gradient, that means is going to compute the derivative of loss with respect to image. So essentially gradient is a derivative and I will show you that little later. So gradient, this is going to compute the gradient of the loss which was computed by this function which is compute loss, and then with respect to the image. Then once you have computed the gradient, now you want your gradient descent algorithm, because essentially you are trying to do the gradient descent. Only thing is that we want to maximize it, that's why we call it as a gradient ascent. So for that you basically are requirement is your gradient descent should work smoothly, otherwise it may not work properly. So for that what do? You do the L2 normalization. So L2 normalization is like you are taking the square root of the average of the square of the values in the tensor. So this is something very basic thing which we normally learn in our early college days as part of mathematics. So here you basically compute this L2 norm, and then you have this whatever the gradients it has computed, you compute the normalization or L2 norm of that, and then what you do is you make use of these gradients. So this L2 normalization ensures that magnitudes are within a range, and that's what I wanted to convey to you, so that gradient descent goes smoothly. Then once you got these gradients, then there is a learning rate which has been provided to this method as an input. So you multiply that and then you update. That means in a way what you want is, so that is what, so this particular function, it computes the gradient of the loss with regard to the input image, and then you are going to update the image. So that is what this line is. So you update the image so as to move towards a state that will activate the target filter more strongly. So you are interested in that. So this is that updation line, which is image is equal to image plus learning rate into grads. So when we talk about now computing gradient, so let's take a simple example so that those people who are completely new will understand it. So you can have in the TensorFlow, you can have a variable, say by name called as x, and say suppose if the value of x is say 6, and you want to make it trainable. So this is just a way of giving, otherwise it can be a constant, and then there are limitations on watching and all that. So variable otherwise is a watched, that means gradient tape can watch it. So that's why here trainable is true, nothing more about it or nothing difficult about it. So you have this variable say 6, then within this with tf dot gradient tape, that means you want to watch this variable as tape. So this is that as tape, and then you have this equation which is y is equal to x cube. So you are going to take a derivative. So how do you take? So that means tape dot gradient. So here you see I am printing tape dot gradient y comma x, and then you convert it into the numpy array, and then you get the answer. So what is that? So x to the power 3 derivative, when you differentiate it, this x to the power 3, that means dy by dx is 3x square. So 3x square, that means 3 into x, that means 3 into 6 into 6. That means 36 into 3 is 108. So that's what you are going to get an answer as when you say tape dot gradient, that means gradient y x, that means dy by dx is essentially, and then obviously is a numpy value, so you should get it as 108.0. So that is a quick explanation for those people who are completely new to usage of gradient tape and the gradient functionality itself, that means tape dot gradient. So that is what we have used it as part of this code, which is gradient ascent step. So tape dot gradient, that means you are going to compute derivative or gradient of loss with respect to image. Then comes the line which I just quickly explained to you earlier. So image is equal to image plus learning rate into grad. So that means you adjust the image, input image in the direction that maximizes the loss. Then there is another function or a method which is called as deprocess image. So it's like a helper function or a utility function. So which is going to do some computation, and it is going to do what? So it's going to convert, it's like a helper function, and it is going to convert a tensor into a valid image. Why? Because when you are doing processing like various functions which I just told you, so there will be case where you need to convert finally into the valid image. So that means the resulting image, because of that conversion, that means this function, the resulting image tensor will be a 200 by 200 by 3, and it will be a that means the shape will be this, it's like a one image of 200 by 200 comma 3 RGB. So this post, so this, that means you what is this conveying? So the post process this tensor to turn it into a displayable image, so that values are between 0 to 255. Why? Because when you want to display an image, then you want pixels values to be between 0 and 255. So this function, that means now there is another function where you are going to generate the filter patterns. So suppose if your image width is 200 and height is 200, then you are going to make use of a function which is a user defined function which takes filter index, and the name of the function is generate filter pattern, and you want to run it for 30 iterations. That means these iterations are 30. Then I told you learning rate is what we will provide, that is 10, and you can change and play with it. Then there is a function which is random dot uniform. So this random dot uniform, it outputs random values from a uniform distribution. So uniform distribution will be from 0.4 to zero point 0.6, and then the shape of the image is given, and which is a image width, height, and then 3 for RGB. Then what you do in this loop, that means for I in range iterations, so these iterations are 30, you call this gradient ascent function which I explained to you in the previous slide, where you pass all these parameters like image, filter index, and learning rate, and then this is going to compute it, that means it is going to run for so many iterations, say 30 here, and then in the end you get image dot, that means this image essentially you get it as an image, and of that the important or the useful information is in the 0th, this one. So you essentially make use of image 0 dot numpy. So here this function generate filter pattern generates filter visualization. So that is what I wanted to tell. So this helps me to generate the various filter visualizations, and then uniform random dot uniform outputs random values from a uniform distribution. So now what we will do is we will take a look at this code, which basically and we will understand how these patterns are generated. So let's go to the program now as part of the Jupyter environment. So let me take you to the Jupyter environment, and so let me run this code. So we have this model. Now you can see this model otherwise is we have given this weights and the include, then model dot summary I have commented out because I explained to you earlier. Similarly, we have plotted this image, so we will not get into that now. So we will build a feature extraction model. So we will give this name of the model name layer name as block 3 underscore separable con 1. Now we can change this name. Right now we will give this name, and how do you change it? I had told you, like you can do model dot summary, and which will give you all the names of the layer. So you can take the names, important names, not the underscore bn and all that batch normalization, but the major names. So here you can see this layer block 3 underscore sep con 1. Then you will form this, using this you form the feature extractor. Then we have this function which is compute loss, which I explained to you just now. Then you have this gradient ascent. So I explained to you this tf dot gradient tape watch, then compute loss function you call, then you do the normalization, and then you update the image. So we will do that. Then you generate the filter visualization. So this is that, just few minutes back I explained to you. This is that function which is image 0 dot numpy, which is important here. So and then we have this deprocessing. So I explained to you this deprocessing. Why do you require it? So let me just quickly show you this deprocessing, the function to convert tensor into a valid image, and I explained to you that earlier. So now you can see I will call now this function. So let me just clear this. So you can see this plot, I have imported matplotlib as plt. Then I call this image show. In the image show I call this function generate filter pattern, and I pass this filter index is equal to 2. We can play with it, we can change the other filter index, and then you do the deprocessing of the image. So if you just do it, then you can see it takes time, and it is plotting this particular, that means this particular layer which is this block what is this block 3 underscore sepcon is what it is going to learn. So this is that thing that gets learned. So suppose if I change this, now how do I change it? I don't know the names right now, so I don't know. So I can always do a model dot summary, or I can always do this plotting by, so let me uncomment it, and I can plot it. Yeah, so you can see this, the names are available to us. So block 3, then I can always do say block 8 separable block 8 underscore sep con 3. Let us do that. Block 8 sep con 3. So we generate filter pattern, and then we have this function, and now we will plot it. So it's a complicated one. Now you can see the pattern here. It has taken more time. So this is that pattern which essentially is learning. So now the question is, how do you know what exactly is done completely? So for that you can always write a code where you can generate a grid of all the filter responses patterns in a layer. So let us say that we have done it for just because it takes time. So suppose if I revert it back, suppose if I just revert it back, you can play with it like that. So I'll revert it back and I will do it. We have already done it for this block layer. So let me just this particular block, then we have to run this. Okay, it's not needed to run everything, but I'm just okay. Now you can see this same thing which was, so now for this what I have done is already plotted it, because otherwise it takes good amount of time. So let me just take you here, and then this is that block 3 underscore sep con 3. So you can see I'm opening this my image viewer, and this is what typically it looks. So that means for 64 such 1 2 3 4 5 6 7 8, and then 8 horizontally and 8 vertically. So you can see this is the way the pattern looks. That means these filters are learning these things. So what exactly it is learning? So it goes and learns some of the things which are edges and all that as part of the understanding the image. So let's go back to this. So now I can always generate such things. So if I just run this program, so here I am just calling this function dprocess image, and here you can see this filter index in range 64, that means 0 to 63. It is going to do that, and then it's going to append, and then this is the code which is responsible for after doing the appending. It does the some jugglery so that you can put these small 8 by 8 boxes or these images, so that you have this grid of 64. So that is done in this loop of I in the range n by n, that means 8 by 8, n is 8 here, so that is 64, and with proper margin calculations and all that, it finally saves here. So that's the final file I have shown you, and it is going to process in from 0 to 63. That's what typically will happen. So that's essentially about this particular demo, where we have understood about what is visualization convolute filter. Now in the next short video, I will explain to you the interpretation of these images. Thank you. Hello friends, welcome to Deep Learning tutorial series. Myself Srirang Korde. So up to now we are studying exception net model, and we also have seen its usage as well as how we go about visualizing the learning ability of a particular layer, and then we have created a grid of various images. So we would like to now interpret the results as part of visualization. So let's get into that. So visualizing the convolute filters we have done. Now we would like to interpret it, and obviously when we are doing it, we are dealing with exception net model. So this is what we have seen, or we have generated rather in our previous practical. That is, this is a image of a particular layer, say block 3 con 1, like that. Okay, so we have done that, and then as part of showing it for the complete 8 by 8, so we have created this 64 various images, and this is what we have seen in our earlier video. Now we would like to interpret this, what, because otherwise it's extremely difficult for someone to make out what exactly is going on. So that means for a particular layer of a model, say exception model here in our example, so what is that that particular this model is trying to achieve, or or it understands. So let's understand it, or let's know more about it. So visualizing convolute filters, and as part of we would like to interpret. So the first visualization tells how convolutes layers see the world. Now this is a very important thing. That means the filter visualizations are there. They are telling how convolute layers see the world. That means now we can see a diagram, or we can see a picture as a picture of cat or a dog or car or something like that. But how these convolute filters are able to see that, so that is what this visualization tells. So then each layer in a convolute learns a collection of filters. Why? Because that's the way the model is defined. So each layer in a convolute learns a collection of filters such that their inputs can be expressed as a combination of the filters. So this is similar the way in which we study normally in our college days, like Fourier transform decomposition. So we have studied like Fourier transform decomposition is like there is a cosine and then there is a sine. So obviously cosine transform is used heavily. So this is similar the way in which how Fourier transform decomposes signals onto a bank of cosine functions. Then the filters in these convolutes get increasingly complex and refined as we go higher in the model. So that means the filters from the first layer in the model, say for example block 1 underscore con1, there are block 2, block 3 like that. So and multiple such are there, and we can always get those details by either plotting the image of the model, and I explained to you in the previous video, or by doing model.summary. So filters from the first layer in the model encode simple directional edges and colors, that means or colored edges in some cases. The filters from the second layer, say block 2 con, encode simple textures. That means we are just going layer by layer. So the filters from block 2 con encode simple textures made from combinations of edges and colors. Then the filters in higher layers begin to resemble features found in natural images, say like feathers, eyes, leaves, and so on. So that's essentially the interpretation about a particular model or a layer can do. Thank you.
Hi everyone, welcome to the deep learning tutorial series. In this video, we are going to talk at one of the very important topic with respect to designing of deep learning model, and the topic name is overfitting, underfitting. So let's get into this topic. So we'll first understand what is overfitting and underfitting. Then we will see what's the impact of network size on that. Then we will see a technique that is used to circumvent a problem. So that technique is called a dropout, and some other side-by techniques we will see. So over/underfitting. So what is overfitting? Let's try to understand that now. So when we typically talk about the performance of the model on a data, then we have seen that that performance has peaked after a few epochs, and then it began to degrade. So we have seen this when we have plotted the graphs using matplotlib. So initially basically the performance of the model on the data, it peaked, and then after that it began to degrade. That means typically it is called as model quickly started to overfit to the training data. That means we have basically defined the model, we have given the data, and then we started the training process, and in that we basically have realized that model quickly started to overfit to the training data. So what exactly is required now? So you basically need a balance between optimization and generalization. That means optimization means you need to adjust the model to get the best performance possible on the training data. That is learning. As a part of learning, I would like my model to be optimized in a very effective way for the best performance possible. However, when we talk about generalization, so the trained model or the optimized model essentially need to perform on the data that it has never seen before. Okay, and then we need to see how well that trained model is performing on the data that it has never seen before. That means we can call it like a test data. So typically when we are say having the data and we have defined the model, so at the start of training, so typically we have, say, let's say we want to do the fitment for say epochs and number of epochs. So typically at the start of training, the optimization and generalizations are correlated. So that means what we basically experience, or what we say to it, is like the lower the loss on the training data, the lower the loss on the test data. So that is the way our thought process is. So that means while training is happening, the model is said to be underfit That means there is still progress to be made. The network has not yet modeled all the relevant patterns in the training data. But after a certain number of iterations on the training data, the generalization stops improving. That means it reaches the saturation sort of thing. And validation metrics, so that means whatever the metrics that we are actually using it to track the performance, basically they begin to saturate or they begin to stall, and then they begin to degrade. That means over a period of time then it basically picks up and then it degrades. That means we say that the model is starting to overfit. So what exactly happens? So essentially in the literature it is said that it is like beginning to learn. That means it started learning the patterns that are specific to training data, but that are irrelevant for new data. Now that is very interesting statement. You are trying to basically give a data to the model, so it is basically learning the patterns. However, it is irrelevant for the new data. That means if my new data that is going to be tested and then those patterns that it is learning, basically it becomes now irrelevant. So how do we deal with this under oblique overfitting? So the one option is you get more training data. So a model trained with more data will generalize better. That is what we normally in common sense we will say, like I have an exam and probably let's say in the exam there are going to be, let's say 10 chapters of a book. Okay, so what I will do initially, I will think, okay, let me probably study only say 6 chapters and remaining 4 probably I will leave it in some whatever, some options in the exam or some pattern of the exam. But then probably if I get time then I will say no, let me try to study all say 8 chapters, or probably somebody may say no, let me try to study all the 10 chapters. So that is in general our thought process. So model trained on more data will generalize better. That means we will be able to handle more questions in the exam. That is what basically our normal thought process is. However, there are cases when we deal with deep learning, so we do not have more training data. So what do? Then you basically modulate the quantity of information that the model is allowed to store, or to add constraints on what information it is allowed to store. That means now it is something like this, that I know that I have basically to appear an exam say after 1 week, and there are let's say 10 chapters, the same example, then probably what I will do is I will pick, I want to take care of all the 10 chapters. However, I will concentrate only on the important topics of each chapter, so that I know that and I'm basically trying to learn, or I'm trying to practice those problems or those say those topics, rather than I'm trying to understand each and everything, or rather than I'm trying to store or learn all the 10 chapters of that particular subject. So that is what, so essentially we are doing modulating the quantity of information that model is allowed to store, or you are basically adding constraint what information is allowed to store. So this process is actually called as regularization. That means the process of fighting overfitting via above steps. That means either you get more training data, or if the training data is not possible, then in that case you modulate the quantity of information. So what are the different regularization techniques? One is you reduce the network size, and another technique is called as adding dropout. So let's see these techniques. So reducing network size. So you basically what you do, you reduce the size of the model. That means the number of learnable parameters in the model. Because essentially what is it? It's all the parameters, like whatever the parameters you have defined which the model is going to learn. Now suppose if you are using it for say temperature forecasting, say you are using it for say stock market forecasting and stuff like that, and essentially you have defined the various learnable parameter. So you are trying to basically reduce the size of model. So number of learnable parameters you are basically trying to reduce. So those parameters, when you talk about these parameters, so typically what you are doing, it is normally referred as model capacity. So it will be decided by the number of layers and the number of units per layer. So that means a model with more parameter has more memorization capacity. So it can easily learn like a perfect dictionary mapping between training samples and the target, that is mapping without any generalization power, because it's like mugging basically. So it, because you have more memory or you have more memorization capacity, so it is learning easily, so it becomes like a dictionary. So like you open a dictionary and you want to see the meaning of that particular word, so it is like for that word this is the meaning, for this word this is the meaning, so it becomes more like a dictionary. However, you are now trying to reduce the network size. So what you are doing is, now if the network has limited memorization resources, now because you are going to, your approach is to reduce the network size. You don't want it to be a bulky or a model with too much of a learnable parameter, or it's like too much of number of layers. And in that case, what will happen? Now you won't be able to learn this mapping easily, because now you do not have that much of memorization capacity. So because of that, because network has now limited memorization resources. So when you have this network with limited memorization resources, so what you do? So to minimize its loss, you basically resort to learning compressed representations. Okay, that means that have predictive ability regarding the targets. So you are now using some techniques, so which will basically minimize its loss, and you basically are going to have techniques which is you are resorting to learning compressed representation. That means instead of literally going in one-on-one, because now you do not have the luxury of more memory, so you are trying to do some sort of processing, or you are trying to do some compressed representation. So, and then also model should have enough parameter that they don't underfit. Now this becomes very important, because if I try to reduce parameters, then my model will start becoming underfit. So I need to basically balance properly. So the question comes is, how many layers oblique right size of the layer? So what you do, you evaluate an array of different architectures, that means on the validation set and not on the data test set, in order to find the correct model size for data. Then you basically start with relatively few layers and parameters, and then you increase the size of layers, or you add new layers till you basically don't see any improvement. So that is called as diminishing returns, okay, with respect to the loss, validation loss. So you are basically compromising between too much capacity and not enough capacity, because this is a very crucial, or this is a very critical design or a decision making that has to be done in a deep learning. So you need to compromise between too much capacity, that means it just memorizes, that is not acceptable. And if it is not able to memorize, then it becomes like it does not have enough parameters, so then you start doing a underfit model. So basically it has to be a compromise. So let us say that I want to do experimentation. So initially I will try to lower the model capacity. So we will use it on the same data, which is a MUI data framework that we are used in earlier videos. So in that model, in that particular thing, we have defined the original model as sequential, obviously, and then the dense layers are, say for example, 16 size. 16 size and 16 size, so these are the 16, 16, 16, activation in ReLU, and then the input shape is say 10,000, and then the final layer is a sigmoid. Now if you want to do with the lower model capacity, then what you do, you reduce this. So instead of 16 you make it 4, and you then finally the decision making layer is 7. So this is with the model with a lower capacity. So if you carry out an experiment with that, then you basically are going to get a data which is say the movie review data as something like this. So you can see the pluses with the original model, and this dots or this bold basically is on this or the smaller model. Okay, so this dots is for the smaller model and pluses is the original model. So now you can see in the graph when we were using original model, so this epochs very quickly before say 5th epoch, or even before 5 epochs, it actually started going toward the validation loss, almost became close to it picked up, and then it started basically going up. Okay, now that is not the case if you try to reduce the the model. Okay, so smaller model essentially. So that means now you have a lower validation loss, that means you have a better model. Okay, so the smaller network starts overfitting later than the reference. So after say 5 epochs or say 6 epochs, whatever, that's what basically I was trying to say. So roughly in this diagram you can say after 6 epochs rather than the 4. So initially it was say before 5, approximately, and now after that it basically started to show its impact. Then the similar experiment can be carried out with a higher model capacity. So we will once again use the movie review, which is in the vectorized format. So then this was my original model 1616.1. Now I am going to use the dense layer with 512, 512 and 1 finally. Okay, and I want to classify the movie reviews either positive or negative. So now in that case, now you can see this was the original model. I am hovering my cursor, so this is the original model, and now in the bigger model, because now I have literally made it 512, so the bigger network starts overfitting immediately after just one epoch. So this is very bad, and it overfits much more severely. So that means its validation loss is now noisier, because you can't make out it. You can see this in the diagram, the validation loss, whatever you are trying to find it out as a validation loss, so it's like a noisier one. So what is basically, so effect on training losses. So what is happening? So if I just use the same this one with for the higher model capacity, so on the training losses, so this is the plus is for the original model, and the bigger model, that means the fat model, you can see the training loss. So the bigger network gets its training loss near zero very quickly. So this is a very, we feel it's wow, it's good. However, the more the capacity the network has, the more quickly it can model the training data, because you know that it starts memorizing. Okay, so it is going to result in a low training loss, but it is susceptible to overfitting. That means resulting in a large difference between the training and the validation loss. So that means whatever the training loss you actually encountered and the validation loss, so there is going to be large difference between that. Okay, so that is what I think, or that is what these slides basically are trying to show. So with the higher model, you can see this validation loss is a noisier one. That is what we have seen. And now when we are basically using it for training losses, or we want to check the training losses, so basically the more the capacity the network has, the more quickly it can model the training data, but it is more susceptible to overfitting. So that means you cannot underfit, you cannot overfit. That is what. So what is the solution? They basically come up in the in the practical or in the reality. So they apply a technique called as dropout. So the dropout is applied. So what is dropout applied to a layer? So they will basically apply to a layer. So it is basically consists of randomly dropping out, that means setting out zero. So please understand, it is like randomly dropping out or setting to a zero a number of output features of the layer during the training. So let's see some details. So let's say a given layer would normally return a vector. Let us say that I have used a softmax not I mean to say not the sigmoid one, because I don't want to classify. Say it is going to return me say 0.2, 0.5, 1.3, 1.8 and 1.1 for a given input sample during training. So what I am going to do now, I am basically going to apply a dropout. So that means I am going to apply 0, I am going to set 0. So this vector now will have few 0 entries distributed at random. Okay, so let's say a first entry is made 0, then say then after that 0.8 is made 0, and that's it. So only two are made 0, that means few are made 0. So they basically come up with something called as a dropout rate. So dropout rate is actually the fraction of features that are zeroed. Usually it will be between 0.2 and 0.5. So normally it will be less, maximum will be 0.5. So less than 0.2 to 0.5. That is what basically it will be between 0.2 and 0.5. That is what the dropout they will apply. So that means you are randomly going to set number of output features of a layer during training to 0. Okay. So little bit of approach. So it is effective and commonly used regularization technique. So it is developed by a person called as Jeff Hinton at the University of Toronto, and he basically was inspired by a bank. Okay, and he basically was inspired by the fraud prevention mechanism used by the bank. So his word is, I went to bank and then the tellers kept changing, that means the person who gives you the money, basically they kept on changing. So teller kept changing, and I asked one of them why. So he said he didn't know, but they got moved around a lot. So that was an instruction. So I figured it must be because it would require cooperation between employees to successfully defraud the bank. So this made me realize that randomly removing a different subset of neurons on each example would prevent conspiracies and thus reduce overfitting. Now this is a very interesting statement, and it has been copied the way in which it is given by Hinton. So there is no change. These are the actual his wordings in the literature. So the core idea is what? So you introduce a noise in the output layer, output values of the layer, and that can break sort of a coincidence. It is called as happenstance. That is coincidence patterns that are not significant, which the network will start memorizing if no noise is present. That means you are now reducing, or you are trying to eliminate the possibility of network trying to memorize, but actually it is giving you the solution, and that means you are not, because the memorization means it is you are moving towards overfitting, and if you are unable to handle, then it is an underfit. So you don't want your network to memorize, however you don't want it to be under also, like basically underfit also. So you basically are ensuring this approach, which is a dropout approach, so which the network, so the core idea is to introduce a noise in the output layer of the output values of the layer, and which can break the coincidence pattern or happenstance pattern that are not significant, which the network will start memorizing if no noise is present. So how do we use this? So Keras has a dropout layer support. So in Keras, dropout in a network can be introduced by a layer called as dropout layer, so which will be applied to the output of the layer right before it. Okay, so what you do, again let's assume that we want to make use of the Mohi reviews data. So that is a simple example. So we are basically defined the layer, dense layer of 16. Then we introduce a layer, dropout layer in between, that is 0.5 values. Then we add a dense layer, say 16. Then we add another dropout layer, say 0.5. Then we add a dense layer, and then which is basically with the sigmoid activation. Okay. So that way you introduce a dropout layer. However, the concept behind dropout layer is actually randomly you make the sample 0, and the thought process is because you avoid the conspiracies. So with the dropout layer, normally the data looks like this. So original model was basically with the plus sign. Then the dropout is like a regularized model. So now you can see, so effect of dropout and validation loss, so improvement over the original network. So we can see that there is a quite significant improvement that happens because we introduce a dropout layer. Then another technique people use is that is called as weight regularization. So in this technique, they basically mitigate overfitting is to put constraints on the complexity of a network. And how do they do? So they basically put some constraint, or by forcing the weights to take only small ranges or small values, which makes the distribution of weight values more regular. So it is called as weight regularization. So it is done by adding to the loss function of the network a cost associated with having large weights. Then in Keras, there is a support for weight regularization. So weight regularization is added by passing weight regularization instances to the layers as key arguments. So you can see we will define the model like that. So you import regularization. So you can see this regularization is imported from Keras. Then you define the model.sequential. Then basically layers dot dense, you have this, and then in the regularization we are adding L2 regularization. So this is like a L1 norm and L2 norm. Okay, so these are the two mathematical norms are there. So people use L2 norm is one of the widely used. So this is activation, ReLU, and then the shape. Then similarly we have added another regularization parameter, say 0.001, then activation, and then the final is a dense layer with the sigmoid activation. So that means the weight regularization can be also added. So just to summarize, so what are the different techniques to manage or to handle this overfitting / underfitting? So you get more training data, that may not be always possible. So then you reduce the capacity of the network. So how do you do that? By using regularization technique. So commonly used technique is a dropout, and then people also think of weight regularization.